Rewind the universe far enough and every star, every atom, even light itself disappears until physics hits a wall. Scientists call it nothing. But this nothing has rules, energy, and a terrifying question built in. If there was truly nothing before the Big Bang, what was it that exploded? And what exactly was there to do the exploding? Some questions don't ask for an answer. They ask what an answer is allowed to mean. And that distinction, quiet as it sounds, is the most important thing we can establish before we go any further. Because the moment you try to think seriously about what existed before the universe, before space, before time, before the laws of physics themselves, you discover something deeply unsettling. The question fights back. It resists the very tools you would normally use to investigate it. Language becomes slippery, intuition becomes unreliable, and even the most sophisticated mathematics eventually raises its hands and admits it cannot continue. This is not a failure of science. This is science doing exactly what it is supposed to do, which is telling you precisely where your knowledge ends and precisely why it ends there. That honesty, that discipline, that willingness to say we do not know rather than invent a comfortable answer, is what separates cosmology from mythology, and it is what makes the question so genuinely fascinating, because the boundary of knowledge is always the most interesting place to stand. We are going to stand at that boundary together. We are going to walk toward it carefully, methodically, following the evidence every step of the way. We are going to map exactly what we know, explain precisely how we know it, and then confront with full intellectual honesty the place where our maps run out. But before we can understand what lies at the edge, we need to understand the journey that brings us there. We need to understand the universe we actually live in, how it behaves, how it has changed, and what its current state tells us about its past. We need to understand the oldest light in existence, what it carries, what it reveals, and why it represents both our most powerful tool and our most fundamental limitation. And we need to understand why the mathematics of general relativity, the same framework that correctly predicts the bending of light around massive objects and the existence of gravitational waves, eventually breaks down when pushed to its absolute extreme. Only then can we honestly engage with the deeper questions. What might have existed before the Big Bang? What does it mean for time to have a beginning? What is the difference between physical nothing and philosophical nothing? And why does that difference matter so much? The answers, or rather the honest attempts at answers, will take us through quantum mechanics and general relativity, through cosmic inflation in the quantum vacuum, through cyclic models and multiverse proposals, and finally to the frontier of quantum gravity, where physicists are trying to build the theoretical bridge that reaches across the gap our current knowledge cannot cross. Along the way, we are going to be very careful about one thing above all others. We are going to keep track of what is measured, what is inferred, what is hypothesized, and what is purely speculative. Those four categories are not the same. They do not carry equal weight. And treating them as interchangeable is how popular accounts of cosmology so often mislead people into thinking we understand far more than we do, or alternatively, far less. The universe is genuinely mysterious at its deepest levels. That mystery does not need to be exaggerated. It is dramatic enough on its own terms. And the terms matter because precision is not the enemy of wonder. Precision is what transforms wonder from a feeling into a fact. So let us begin. Let us begin by dismantling something that seems obvious, something that feels like common sense, something that billions of people have said without a second thought. Let us begin by dismantling the word nothing. When most people say the word nothing, they have a picture in mind even if they do not realize it. It is a dark room with the lights off. It is a vast empty space stretching in every direction without a single object in it. It is a kind of cosmic silence, an infinite blackness, a void so complete that there is not even a shadow to give it shape. The nothing people imagine when they say there was nothing before the Big Bang looks something like outer space on a moonless night, but emptier, darker, more absolute. The problem is that picture is already full of something. Think about it carefully. That dark room has walls, even if they are infinitely far away. That empty space has dimensions, a here and a there, a distance between any 2 points. That vast blackness has duration, a sense of time passing even if nothing is happening. The stage is already set. The theater already exists. The only thing missing is the performance. But if space and time are themselves part of what the Big Bang brought into existence, if the stage is not pre-existing but is itself something that had to be created or that emerged or that began, then the picture of an empty void waiting for the universe to appear is not a picture of nothing. It is a picture of something very specific, a space-time with zero matter in it, a geometry without contents, a framework without events. And that is a very different claim. This is not a philosophical trick. It is a genuine physical distinction that matters enormously for how we think about cosmology. The question of what existed before the Big Bang is not just asking about the absence of galaxies or atoms. It is asking about the absence of the very framework within which absence and presence are defined, and that is a question our intuitions are spectacularly unprepared to handle. Our brains evolved to track objects moving through space over time. We are extraordinarily good at that. We can catch a ball, navigate a forest, recognize a face across a crowded room. All of those abilities depend on the assumption that space and time are fixed backgrounds against which things happen. Our cognitive architecture treats the stage as given. It treats the arena as fundamental, and then it fills that arena with objects and events and causes and effects. Cosmology asks us to question the arena itself, not just what is in the universe, but what the universe is. Not just what happened at the beginning, but what beginning can mean when time is part of the system being described. Not just what created everything, but whether creation is even the right concept when there was no time in which an act of creation could have occurred. These are not easy questions to hold in your mind. They feel slippery because they are slippery. The concepts that work perfectly well in everyday life start to behave like worn tools when you push them to extremes. The word before, which seems completely innocent, starts to do suspicious work the moment you ask it to operate outside of time. The word exist, which seems utterly basic, becomes ambiguous when you ask about things that might not be embedded in a space-time at all. So the first thing we need to do is sort out the different meanings of nothing, because there are at least three importantly different versions, and the conversation around cosmology switches between them constantly without always noticing. The first version of nothing is everyday nothing. This is the absence of objects in a pre-existing space, an empty room, a cleared table, a field with no trees. In this version, nothing means no things, but the background persists. Space is still there. Time is still passing. The laws of physics are still operating. There is just nothing in the room. This kind of nothing is trivial to imagine and completely unproblematic. It is not what cosmologists mean when they talk about the beginning of the universe. The second version of nothing is physical nothing, sometimes called the quantum vacuum. This is the lowest possible energy state of all physical fields, a state in which no particles are present in the usual sense, but in which quantum fields still exist and still fluctuate. The quantum vacuum is deeply strange because it is not truly empty in any intuitive sense. It seethes with activity. Virtual particles appear and disappear. Fields fluctuate at every point. Energy is stored in subtle ways. The quantum vacuum is not a featureless absence. It is a structured physical state with well-defined properties, governed by well-defined laws. It is the ground floor of reality as quantum field theory describes it, but it is emphatically not nothing in the philosophical sense. It is a very specific kind of something. The third version of nothing is philosophical nothing. This is the kind of nothing that means the absolute absence of everything. No space, no time, no laws, no fields, no mathematical structures, no possibilities, no truths. Not even the truth that there is nothing. This version of nothing is so extreme that it is genuinely hard to know whether it is a coherent concept at all. If there are no laws, can there be a law that says nothing cannot become something? If there is no logic, can we even reason about what this state would entail? Philosophical nothing is the target of the deepest version of the question, why is there something rather than nothing? And it is the version that most resists physical description. The mistake that shows up again and again in popular accounts of cosmology is the slide between these three versions. Someone will say the universe came from nothing, meaning the quantum vacuum, and listeners will understand it as philosophical nothing, which is a completely different claim. Or someone will say before the Big Bang there was nothing, meaning our equations cannot describe that era, and it will be heard as confirmation that absolute non-being preceded the universe, which is a philosophical claim our equations cannot support. Keeping these distinctions clear is not pedantry. It is the difference between understanding what science actually claims and misunderstanding it in ways that either overinflate or unfairly dismiss genuine cosmological progress. There is a fourth complication that is less often discussed but equally important. Even when we are careful about which nothing we mean, we still face the problem of the word before. Before is a temporal concept. It means earlier on a timeline. It assumes a timeline exists. It assumes there is a sequence of moments and that one of them can be identified as coming prior to another. In our everyday experience, before is completely unproblematic. Yesterday came before today. The formation of Earth came before the appearance of life. These are statements about a timeline that we assume extends smoothly in both directions, past and future, without any boundary. Our intuition treats time as a road that stretches beyond the horizon in every direction. But there is no physical principle that guarantees this. Time, as we understand it in modern physics, is not a universal backdrop independent of everything else. In general relativity, time is part of spacetime, and spacetime is a physical entity that responds to matter and energy. It curves, it stretches, it contracts. It can have different geometries, and according to our best mathematical descriptions of the very early universe, it may have a boundary. Not a boundary in the sense of a wall you could crash into, but a boundary in the sense that the coordinate system we use to label time cannot be extended further. The concept of earlier simply stops having a definition. If that is the case, then the question of what came before the Big Bang is not a question that has a hidden answer waiting to be found. It may be a question that is using the word before in a context where before does not apply. It would be like asking what is north of the North Pole. That is not a difficult geography question waiting for a better map. It is a question that misuses the concept of north, because north is defined on the surface of a sphere, and the pole is where that coordinate system runs out. The North Pole analogy is imperfect, as all analogies are, but it captures something real. Sometimes the deepest questions turn out to be questions that need to be rephrased rather than questions that need to be answered, and rephrasing them is not giving up. It is the most intellectually honest thing you can do. None of this means the question of cosmic origins is unanswerable or uninteresting. It means the question is harder and stranger than it first appears. It means we need to be careful about what we are actually asking before we celebrate or dismiss any proposed answer. And it means that the most interesting work in this area is happening not just in telescopes and particle accelerators, but in the conceptual foundations of physics, in the attempts to build theories that can describe regimes where our current concepts break down. That is where this story goes. But it goes there by first establishing what we know, because the mystery at the edge of knowledge is only meaningful against the background of what knowledge has already achieved. You cannot appreciate the edge of the map until you have traced the territory it covers. The universe we inhabit is, by any measure, an extraordinary place. Its observable portion alone spans approximately 93 billion light-years in diameter, a number so large that it resists genuine comprehension. It contains somewhere in the range of 2 trillion galaxies, each of which contains billions to hundreds of billions of stars. The total number of stars in the observable universe is estimated to exceed the number of grains of sand on every beach and desert on Earth, combined many times over. And yet, for all its vast population of matter and energy, the universe is also almost unimaginably empty. The average density of matter across the cosmos is extraordinarily low. Space between galaxies contains on average less than 1 hydrogen atom per cubic meter. The cosmic web of filaments and clusters and voids that large-scale surveys reveal is mostly void, with matter concentrated into thin threads and dense nodes that together occupy a small fraction of the total volume. This is the universe as it exists today, roughly 13.8 billion years after the hot, dense early state that cosmologists refer to, somewhat misleadingly, as the Big Bang. And here is the first crucial observational fact. It is expanding. The expansion of the universe is not a hypothesis or a philosophical position. It is a measured fact, confirmed by multiple independent lines of evidence, refined over nearly a century of increasingly precise observation. When we look at distant galaxies and measure their spectra, the light they emit is systematically shifted toward longer, redder wavelengths compared to what we would measure in a laboratory on Earth. This redshift is not random. It follows a pattern. On average, more distant galaxies are more redshifted. The relationship between distance and redshift is remarkably orderly, and it tells us something fundamental about the universe we live in. The most natural interpretation of this pattern, first worked out in detail in the 1920s by figures including Vesto Slipher, Georges Lemaitre, and Edwin Hubble, is that the universe is expanding. Not that galaxies are flying through pre-existing space like shrapnel from a bomb, although that picture is tempting and not entirely wrong for small scales. Rather, that the space between galaxies is itself growing. The metric, the mathematical measure of distance between points in space, is changing over time. Points that are far apart are becoming farther apart, not because anything is pushing them, but because the fabric of space between them is stretching. This is a strange idea. It is worth sitting with it rather than moving past it too quickly. Space is not a passive, fixed container in which the universe's contents move around. Space is a dynamic physical entity that can expand, contract, curve, and respond to what fills it. This is one of the core insights of general relativity, and it is not just a theoretical abstraction. It is confirmed by observation at every scale we can probe. The expansion means that if we run time backward, distances between galaxies decrease. The universe was smaller in the past, and smaller means denser. A smaller volume containing the same amount of matter and energy is a denser, hotter universe. We are not imagining this. We can calculate exactly how density and temperature change with the scale factor, the parameter that describes how much the universe has expanded, and we can test those calculations against observations. This is where the rewind becomes more than a thought experiment. It becomes a predictive framework. If the universe was once much hotter and denser than it is today, then certain things would have been true about it. At high enough temperatures, atoms cannot hold together because energetic photons and particle collisions constantly strip electrons away from nuclei. The universe would have been a plasma, a sea of free electrons and nuclei, opaque to light because photons would scatter off free electrons before traveling any significant distance. As the universe expanded and cooled, atoms would eventually form. And when they did, the universe would have become transparent, releasing a flood of photons that would have been traveling freely ever since. This prediction was made decades before it was confirmed. In 1965, Arno Penzias and Robert Wilson, working at Bell Laboratories on a project entirely unrelated to cosmology, discovered a persistent microwave hiss coming from every direction in the sky. It did not come from any particular source. It did not vary with time of day or season. It was uniform, pervasive, and inexplicable by any known local source. What they had discovered, after some initial confusion and a productive conversation with theorists at Princeton, was the cosmic microwave background, the cooled, redshifted afterglow of the hot early universe, still filling the sky more than 13 billion years after it was released. That discovery is one of the most important in the history of science, and it did not stand alone. The hot early universe also makes a precise prediction about the relative abundances of the lightest elements. In the first few minutes after the Big Bang, when temperatures were high enough for nuclear reactions, but the universe was expanding too fast for those reactions to reach equilibrium, a specific combination of hydrogen, helium, deuterium, and trace amounts of lithium should have been produced. The calculations depend on the density of ordinary matter and the expansion rate during that era. The prediction is that roughly 75% of ordinary matter by mass should be hydrogen and roughly 25% should be helium, with tiny traces of deuterium and lithium. When astronomers measure the chemical composition of old stars and ancient gas clouds that have not been significantly contaminated by later stellar nucleosynthesis, they find precisely those proportions. The agreement between theory and observation is remarkable. It is the kind of agreement that transforms a hypothesis into a confirmed framework. These three pillars, the expansion seen in galaxy redshifts, the cosmic microwave background, and the primordial element abundances, together constitute the observational foundation of Big Bang cosmology. They are not the same observation. They probe different aspects of cosmic history over different timescales and using completely different physical processes. And they all point to the same conclusion. The universe evolved from a hot, dense, early state and has been cooling and expanding ever since. This is what we mean when we say the Big Bang is the best supported model in cosmology, not that we have a photograph of the first moment. Not that we have proven ultimate origins, but that the framework correctly predicts a remarkable range of independent observations with high precision, using a relatively small number of free parameters. That is what a successful scientific theory looks like. But the framework also has a boundary, and that boundary is where things get genuinely strange. To understand where the rewind leads, it helps to think carefully about what the expansion actually describes. The scale factor of the universe, which we might call simply the size measure, changes over time. As we look backward in time, it decreases. The universe was smaller, hotter, denser. As we push further back, those extremes become more extreme. In the standard cosmological model based on general relativity, if you extrapolate the expansion equations backward without modification, the scale factor goes to zero at a finite time in the past. At that point, the density of the universe and the curvature of spacetime diverge. They become infinite. The equations produce nonsense in the sense that physical quantities become undefined. This is called the Big Bang singularity. And it is one of the most misunderstood concepts in all of popular science. A singularity is not a thing. It is not a tiny point of infinite density sitting somewhere in space before the universe began. It is a mathematical statement about the behavior of equations. It says that when you push the equations of classical general relativity to their extreme, they produce outputs that are unphysical, infinite values that cannot correspond to anything in reality. A singularity is where the model breaks down, not necessarily where reality stops. This is a crucial distinction. When a theory predicts infinite values, the standard interpretation in physics is not that reality contains an infinite value. It is that the theory is being applied outside its domain of validity. The theory is giving nonsensical answers because it is being asked to describe a regime it was not designed to handle. This happens in other areas of physics too. Classical electromagnetism predicts an infinite self-energy for a point electron. We do not conclude that electrons actually contain infinite energy. We conclude that classical electromagnetism needs to be replaced by quantum electrodynamics at very small scales. The same logic applies to the Big Bang singularity. Classical general relativity predicts a singular boundary at the earliest moments. The appropriate conclusion is not that the universe literally began from a mathematical singularity of infinite density. The appropriate conclusion is that general relativity is being pushed beyond its domain of validity, and a better theory is needed to describe what actually happens in that regime. That better theory does not yet fully exist, but we have strong reasons to believe it must combine general relativity with quantum mechanics. We have strong reasons to believe it involves what physicists call quantum gravity, and we have good estimates of the scale at which these quantum gravitational effects should become important. That scale is set by the Planck units, constructed from three fundamental constants of nature: the speed of light, which appears in special relativity, Planck's constant, which appears in quantum mechanics, and Newton's gravitational constant, which appears in gravity. When you combine these three constants in the right way, you get a length, a time, and an energy that together define the regime where both quantum mechanics and gravity must be taken into account simultaneously. The Planck length is approximately 16 times 10 to the power of -35 meters. This is incomprehensibly small. It is smaller than an atomic nucleus by a factor of roughly 10 to the 20th power. An atom is to a meter roughly what the Planck length is to an atom. We are talking about scales that no experiment has ever directly probed, and that no foreseeable experiment is likely to probe directly. The Planck time is approximately 54 times 10 to the power of -44 seconds. This is the time it takes light to travel one Planck length. It is the shortest duration that has any meaning within our current theoretical frameworks. Before the Planck time, or rather, at and before the conditions corresponding to Planck scale energies in the very early universe, our current theories are not reliable guides. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics treats physical systems as fundamentally probabilistic with fluctuations at all scales. At Planck energies, these two descriptions are both relevant, and they are fundamentally incompatible in their current forms. We need a theory of quantum gravity to describe this regime, and we do not have a complete one. This is not a minor technical gap. It is the central missing piece in our understanding of cosmic origins. Everything we can say with confidence about the early universe is constrained to the period after the Planck time. What happened before, if before even has a meaning there, is currently beyond the reach of our tested theories. And here is where the word nothing makes its most deceptive entrance. When our equations stop at the Planck boundary, when classical time cannot be extended further back, when our models become unreliable, there is a temptation to fill the gap with nothing, to say there was nothing before because our description gives out. But absence of description is not evidence of absence of reality. The gap in our map is not proof that the territory is empty. It may simply mean the territory requires a different kind of map than any we currently possess. The honest position is this: we do not know what, if anything, preceded or underlies the earliest moments our theories can describe. We have candidate ideas. Some of them are mathematically developed and make testable predictions. Others are more speculative. None of them are confirmed. And the confirmed knowledge we do have ends at a specific boundary, defined by the limits of our tested theoretical frameworks. That boundary is not nothing. It is a threshold, and crossing it, even in imagination, requires the most careful reasoning we can manage. There is another layer to this that goes beyond the mathematics, a layer that has to do with the structure of time itself, and it may be the most important layer of all. We talk about before the Big Bang as if before is an unproblematic concept, as if there is a universal clock that was ticking away before the universe existed, counting down to the moment of creation. Our intuition absolutely insists on this. Something must have come first. Events must have a sequence. The universe must have begun at some point in time, which implies there was time before it began. But this intuition assumes that time is external to the universe, a universal backdrop against which the universe's history plays out. In Newtonian physics, this was essentially correct. Newton's absolute time was a fixed, universal parameter independent of anything physical. Clocks measured this time with varying accuracy, but the time itself flowed on regardless, like an invisible river that everything else swam through. Einstein changed this completely. In general relativity, time is not external to the physical world. Time is part of the physical world. Spacetime, the four-dimensional entity that combines space and time, is a dynamic physical structure that responds to matter and energy, that curves and stretches and evolves. Time in this picture is not a background parameter. It is a component of the arena, and the arena is part of the physics. If time is part of the universe rather than a container for the universe, then the question of what came before the universe starts to look very different. If the universe's expansion created time, or if time emerged along with space and matter in some deeper physical process, then there may be no before in which the universe could have been preceded by anything. Asking what came before becomes like asking what is south of the South Pole. Not a difficult question with a hidden answer, but a question that is using a concept in a regime where it does not apply. Stephen Hawking, working with James Hartle, proposed a concrete model in which this idea has mathematical expression. In the Hartle-Hawking no-boundary proposal, the origin of the universe is described using a mathematical technique in which time takes on imaginary values near the beginning. When you do this, the time dimension behaves like a spatial dimension, and instead of a sharp beginning point where spacetime breaks down, you get a smooth geometry with no boundary. The universe in this description simply has no edge in the time direction, just as the surface of a sphere has no edge. This is a mathematically precise proposal, not a vague metaphor. And it changes the question entirely. Instead of asking what caused the universe or what came before it, you ask about the quantum state that describes the universe's geometry. The universe in this picture is not created from nothing. It is described by a wave function that has a certain form near the apparent beginning. The beginning is not a starting point in the usual sense. It is the smooth southern tip of a geometric shape that has no boundary to fall off. Whether this proposal is correct is a separate question, and it remains contested and unconfirmed. But it illustrates the kind of conceptual shift that is required when we take seriously the possibility that time itself has a beginning or is emergent. The question is not answered by saying before the beginning there was nothing. The question is transformed into a question about what mathematical structure describes the universe at its deepest level. There is one more piece of conceptual groundwork to lay before we can follow the evidence in detail, and it concerns the difference between the Big Bang as a physical model and the Big Bang as a popular idea. In popular culture, the Big Bang is almost always depicted as an explosion. A tiny, impossibly hot, impossibly dense point suddenly bursts outward, expanding into the surrounding emptiness of space, growing from a pinprick to a universe in a fraction of a second. This image is vivid, intuitive, and almost entirely wrong. The Big Bang is not an explosion of matter through pre-existing space. It is the expansion of space itself. There is no center from which everything expanded. There is no surrounding emptiness into which the universe grew. Every point in space was once much closer to every other point. Every region we can name was once much denser and hotter. The expansion is not a movement through space. It is a change in the metric, the measure of distance, everywhere simultaneously. The raisin bread analogy captures part of this. Imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. No raisin is at the center of the expansion. A raisin on the left edge sees all other raisins moving away. A raisin in the middle sees all other raisins moving away. The expansion is in the medium itself, not a movement through a fixed background. The analogy breaks down because the bread has a crust, an edge, and an outside. The universe in the standard model does not. The expansion is not happening inside a larger container. There is no outside in which the universe sits. The universe is all there is, and the expansion is a property of the universe's own geometry. This distinction matters enormously for how we think about origins. If there is no outside, if there is no pre-existing space into which the universe expanded, then the question of what was there before has to be understood differently. It cannot be asking about what occupied the empty space before the universe filled it, because there was no pre-existing empty space. The space is part of what is being described. If the universe's expansion began from an extreme state, if space and time themselves had some kind of origin or boundary, then the question of origins is asking about the nature of that boundary, and what, if anything, lies beyond or beneath it. That is a very different question from what was sitting in the empty space before the bang, and it requires very different conceptual tools to approach. These tools are what the rest of this story explores. The evidence from the cosmic microwave background, refined over decades of increasingly precise measurement, the theoretical framework of inflation, its successes, its challenges, and its relationship to the quantum vacuum, the mathematical structure of general relativity, and the singularity theorems that reveal its limitations. The candidate theories of quantum gravity and what they suggest about the earliest moments, the deeper proposals for cyclic universes, multiverses, and emergent time that try to reframe the question rather than just answer it. Each of these topics brings us closer to the edge, and at the edge, the most important thing is not to pretend we have crossed it when we have not. The most important thing is to be honest about what the edge is, what it tells us about the limits of our knowledge, and what kind of thinking might someday help us see beyond it. Because the boundary of knowledge is not a place to stop. It is a place to think more carefully. And careful thinking is where we are going next, following the oldest light in the universe back to the moment it was born, reading from it everything it can tell us about a universe young enough to be described in minutes and seconds rather than billions of years. The rewind is about to become much more specific. The evidence is about to become much more detailed. And the mystery at the end of the trail is about to become much more precisely located. Before we follow the light, let us establish the most important principle of this entire investigation. It is a principle that sounds simple, but is surprisingly hard to maintain under the pressure of a genuinely fascinating subject. What you observe and what you infer are not the same thing. What you infer and what you hypothesize are not the same thing. What you hypothesize and what you speculate are not the same thing, and none of these are the same as what you know. Observation is what your instruments directly measure. Inference is what you conclude from observations using well-tested physical principles. Hypothesis is a proposed explanation that extends beyond what you can directly infer, motivated by evidence but not yet confirmed. Speculation is an idea that is even further out, motivated perhaps by mathematical elegance or theoretical consistency, but not yet making contact with observation in a decisive way. All of these have a place in science. Speculation today can become hypothesis tomorrow. Hypothesis can become inference, and inference can become observation. The history of science is full of examples. The existence of atoms was once speculation. The existence of gravitational waves was once hypothesis. The expansion of the universe was once observation that needed theoretical explanation, and the theory of general relativity gave that explanation. Science progresses by moving ideas up this ladder, but the ladder has rungs, and they are not all the same height. An idea at the speculation level does not carry the same evidential weight as an observation, no matter how beautiful the speculation or how thorough the calculation behind it. And in a subject as profound as cosmic origins, where the temptation to let imagination run ahead of evidence is enormous, keeping track of where each claim sits on this ladder is essential. Throughout what follows, we will try to be explicit about which rung we are on. This is not because the higher rungs are unimportant. The most important questions often live there. It is because clarity about what we know versus what we think versus what we wonder is what makes genuine understanding possible, as opposed to the comfortable illusion of understanding that comes from treating all claims as equally solid. With that principle firmly in hand, we follow the light. The cosmic microwave background is the universe's oldest photograph. It is not a photograph of the beginning. It is a photograph of a specific moment roughly 380,000 years into the universe's history, when the cosmos first became transparent to light. But it is the earliest electromagnetic image we can obtain, and it is extraordinarily detailed, extraordinarily informative, and extraordinarily beautiful in the way that only a universe photographing its own infancy can be. To understand what the CMB tells us and why it is so powerful, we need to understand the conditions that produced it. And to understand those conditions, we need to follow the rewind back through time with some care. Start with today. The universe is cold, about 725 Kelvin on average in its microwave background, and it is structured. Galaxies cluster in groups and superclusters. Superclusters are connected by filaments. Filaments separate vast, nearly empty voids. This large-scale structure spans hundreds of millions of light-years and represents the accumulated work of gravity over cosmic time, amplifying tiny initial variations in density into the enormous contrasts between rich clusters and empty voids that we observe today. Now move backward. The universe was smaller, denser, hotter. As we go back, the structures that exist today gradually become fainter outlines and then disappear, because the conditions that allowed them to form had not yet been met. The universe becomes smoother, more uniform. The contrast between dense regions and empty regions decreases. Continue back to around 1 billion years after the Big Bang. The first galaxies have just begun to form. The cosmic dark ages, when the universe was filled with neutral hydrogen absorbing starlight and producing no illumination of its own, have just ended. The universe is beginning to be reionized by the ultraviolet radiation from the first generation of massive stars. This is a turbulent, complicated era whose details we are still working out. Go back further, to a few 100 million years after the Big Bang. The dark ages are fully underway. The universe contains no stars yet, no galaxies, no sources of light except for the fading remnant of the microwave background. Neutral hydrogen fills the space between collapsing halos of dark matter. Gravity is slowly drawing matter together, building the seeds of future structure, but nothing has yet ignited. The universe is genuinely dark in the visible spectrum, though the microwave background still fills the sky. Continue to 380,000 years, and we reach a crucial transition. The universe at this point has cooled to roughly 3,000 Kelvin. This might sound hot by everyday standards, but in cosmological terms, it is the critical temperature at which something important happens. It is the temperature at which electrons can successfully combine with protons and helium nuclei to form stable neutral atoms. Below this temperature, the typical photon in the radiation field no longer has enough energy to ionize a hydrogen atom. The equilibrium shifts, neutral atoms become stable, electrons leave the free state and bind to nuclei. With electrons no longer free to scatter photons through Thomson scattering, the universe changes its character in a fundamental way. Before this moment, the universe was opaque. Photons could not travel far without being scattered by free electrons. The mean free path of a photon, the average distance it could travel before bouncing off an electron, was tiny compared to cosmological distances. Light and matter were tightly coupled, exchanging energy constantly, behaving like a single fluid. After this moment, the universe becomes transparent. With electrons bound into atoms, photons suddenly have almost nothing to scatter off. Their mean free path jumps from tiny to effectively infinite. Photons that were part of the plasma are abruptly freed. They can now travel in straight lines across the universe, and they do. They have been traveling ever since. Those freed photons constitute the cosmic microwave background. They left the plasma at recombination and have been streaming freely through an expanding universe for the 13.8 billion years that followed. As they traveled, the expansion stretched their wavelengths. What began as visible and infrared light from a 3000 Kelvin plasma has been redshifted to microwave wavelengths by the enormous expansion factor of the universe. The temperature of the radiation, which inversely scales with the wavelength, has dropped from 3000 Kelvin to 725 Kelvin. That cooling is not just a curiosity. It is one of the most precisely tested predictions in cosmology. The fact that the CMB has a blackbody spectrum at exactly the temperature predicted by the expansion history, consistent with the observed expansion rate and the matter content inferred from independent observations, is a powerful confirmation that the framework is correct. You cannot fake a perfect blackbody spectrum with complicated late-time astrophysics. It is the signature of a system that was once in near-perfect thermal equilibrium, which is exactly what the hot, early plasma would have been. The CMB's most striking feature, though, is not its average temperature. It is the tiny deviations from uniformity that ride on top of it. These anisotropies, temperature variations across the sky at the level of about 1 part in 100,000, are the most scientifically valuable aspect of the signal, and they have been mapped in extraordinary detail by a series of increasingly powerful instruments over the past several decades. COBE, the Cosmic Background Explorer satellite launched in 1989, made the first detection of these anisotropies in 1992 after years of painstaking analysis. The discovery confirmed a prediction that had been made years earlier. The early universe was not perfectly smooth. It contained tiny density variations that would eventually be amplified by gravity into the large-scale structure we observe today. Those variations left their imprint on the CMB as temperature fluctuations, slightly warmer and slightly cooler patches across the sky. WMAP, the Wilkinson Microwave Anisotropy Probe launched in 2001, mapped the CMB anisotropies in much greater detail, producing a full-sky temperature map of remarkable precision that has been used to constrain cosmological parameters with unprecedented accuracy. The Planck satellite, launched in 2009, pushed further still, producing the most detailed map of the CMB anisotropies ever made and refining our knowledge of the universe's composition, age, and geometry to a level that would have seemed implausible a generation ago. What these maps reveal is not random noise. They reveal a structured pattern that encodes the physics of the early plasma in exquisite detail. The pattern can be analyzed statistically by decomposing the temperature variations across the sky into components at different angular scales, a technique called the angular power spectrum. And the power spectrum tells a story that is both physically rich and deeply informative. The story begins before recombination, in the hot plasma when photons and baryons, ordinary matter like protons and electrons, were tightly coupled. In this plasma, gravity and radiation pressure competed. Gravity tried to pull overdense regions together, compressing the plasma. Radiation pressure from the intense radiation field pushed back, resisting compression. The competition between these two forces drove oscillations in the plasma, compressions and rarefactions that propagated as acoustic waves, sound waves in the cosmic fluid. These sound waves traveled through the plasma at a speed that was a significant fraction of the speed of light, set by the balance between the energy density of radiation, which provides pressure, and the total energy density, which provides inertia. The waves set up standing patterns at specific scales determined by how far sound could travel before recombination. The characteristic scale set by this sound horizon, the maximum distance a sound wave could have traveled from the beginning to the moment of recombination, is about 150 megaparsecs in today's comoving coordinates. When recombination occurred and the photons were freed, those acoustic oscillations were frozen into the radiation field. Regions that were at maximum compression at the moment of recombination were slightly hotter than average in the CMB, because compressed regions are denser and hotter. Regions at maximum expansion were slightly cooler. The frozen pattern of oscillations shows up in the CMB power spectrum as a series of peaks and troughs at specific angular scales. The first peak in the power spectrum corresponds to the scale of the sound horizon, the largest fluctuation scale that completed one full compression by the time of recombination. The subsequent peaks correspond to harmonics of this fundamental mode, regions that completed 1.5 cycles, 2 cycles, and so on. The positions of the peaks in the angular power spectrum depend on the geometry of space, the composition of the universe, and the expansion history. Measuring those positions precisely gives us a way to determine those cosmological quantities with great accuracy. The data from Planck and its predecessors tell us that the universe is spatially flat to within about 1%. This means the large-scale geometry of space is Euclidean, neither positively curved like a sphere nor negatively curved like a saddle, but flat in the sense that parallel lines do not converge or diverge. This is a striking observational result, because there is no particular reason a priori that the universe should be flat rather than curved. The flatness is one of the facts about the universe that inflation is proposed to explain, but we are getting ahead of ourselves. The data also tell us the universe's composition with remarkable precision. About 5% of the total energy density is ordinary matter, the atoms, molecules, and ions that make up everything we can see and touch. About 27% is dark matter, a form of matter that interacts gravitationally but does not interact with light, whose nature remains unknown but whose gravitational effects are well established. And about 68% is dark energy, an even more mysterious component that appears to be driving the observed acceleration of the universe's expansion. These fractions are not guesses. They are determined by fitting the CMB power spectrum and other cosmological observations to a model with a small number of free parameters. The fits are remarkably good. The standard cosmological model, called lambda CDM, for the cosmological constant plus cold dark matter, reproduces the observed CMB power spectrum with extraordinary fidelity using just 6 free parameters. This is a stunning compression of information. The universe at its largest scales, a system of almost incomprehensible complexity and size, is described to high precision by a simple model with 6 numbers. The heights of the peaks in the power spectrum carry additional information beyond their positions. The relative heights of the odd and even peaks are sensitive to the amount of ordinary matter, specifically the baryon to photon ratio. This is because baryons add inertia to the oscillating plasma, making compressions more extreme relative to rarefactions. More baryons means a stronger first peak relative to the second. The match between the baryon density inferred from the CMB peaks and the baryon density inferred from the primordial element abundances, two completely independent measurements using completely different physics, is one of the most satisfying consistencies in all of cosmology. Beyond what the CMB tells us, it is equally important to be clear about what it does not tell us. The CMB is a snapshot of the universe at recombination, 380,000 years after the hot dense beginning. It is the earliest electromagnetic view we can obtain. Before recombination, the universe was opaque to light, and no photon from that era can reach us directly. The CMB is not a window into the very beginning. It is a window into a specific moment in the early universe's history, with the earlier period hidden behind an opaque wall of plasma. This is a fundamental observational limitation. It is not a technological limitation that better telescopes or more sensitive instruments can overcome. It is a physical limitation built into the nature of the electromagnetic interaction. Photons from before recombination did not travel freely. They scattered constantly. They carry no directional information about where they came from. They cannot be used to image the earlier plasma. To probe earlier times, we need either different messengers that could have escaped the opaque plasma, or we need theory to reconstruct what the conditions must have been. Neutrinos decoupled from the plasma at a much earlier time, around 1 second after the Big Bang, and a relic neutrino background from that era should exist. But detecting it is extraordinarily difficult with current technology because neutrinos interact so weakly with matter. Gravitational waves, which interact with matter even more weakly, could in principle carry information from the very earliest moments, even from before the Planck time in some proposed models. But detecting a primordial gravitational wave background at cosmological frequencies is a major observational challenge for the coming decades. For now, the CMB marks our direct observational horizon. everything before it must be reconstructed by inference, using well-tested physics and the CMB itself as a boundary condition, and the inference becomes less certain the further back we push. Yet the CMB is not entirely silent about earlier times. The pattern of anisotropies it contains was set by conditions in the early plasma, which in turn were set by the initial conditions of the universe at even earlier times. The spectrum of primordial fluctuations, the statistical pattern of density variations that seeded everything that followed, can be inferred from the CMB power spectrum. And that primordial spectrum has a specific character that demands explanation. The primordial fluctuations are nearly scale invariant. This means that variations occur at roughly the same amplitude across a wide range of physical sizes, from scales that became galaxy clusters to scales that became individual galaxies and smaller structures. There is a slight tilt, meaning the amplitude is not exactly equal across all scales, but is slightly stronger at larger scales and slightly weaker at smaller scales. This slight tilt has been measured precisely, and its value, along with the amplitude of the fluctuations, are among the parameters in the standard cosmological model. Scale invariance is not what you would naively expect. If you started with random fluctuations in the density of matter without any theoretical guidance, there would be no particular reason for them to be scale invariant. Scale invariance is a very specific pattern that suggests a very specific kind of physical process was responsible for generating the initial conditions. And the leading candidate for that process, the one that most naturally and elegantly produces a nearly scale invariant spectrum, is cosmic inflation. This is where the story moves from confirmed framework to theoretical proposal. Inflation is not as firmly established as the CMB or the expansion history. But it is well motivated by the observations. It makes specific predictions that have so far been confirmed, and it connects the observed structure of the universe to the physics of the very early cosmos in a way that is both powerful and testable. It also brings us significantly closer to the question we started with. Because inflation, if it occurred, pushes the story back to a time when the universe was dominated by a very different kind of energy, one that behaves in some ways like nothing while containing within it everything that followed. The tension between something and nothing is about to get much more precise. Let us take stock of where we are before we push further, because the discipline of tracking our position on the ladder of knowledge is especially important here. We know with high confidence based on multiple independent observations that the universe has been expanding and cooling from a hot dense early state. This is observation-level knowledge, confirmed by galaxy redshifts, the CMB, and primordial element abundances. We know with high confidence that the CMB was produced at recombination about 380,000 years into the universe's history, and we know its properties in extraordinary detail. This is observation-level knowledge refined over decades. We know with high confidence that the observed pattern of CMB anisotropies requires an early state of the universe with nearly scale-invariant primordial fluctuations, a flat geometry, and a specific composition of matter and energy. This is inference-level knowledge, firmly grounded in observation. We know that classical general relativity, extrapolated backward through the hot dense early phase, predicts a singularity at a finite time in the past, where the theory breaks down and cannot be extended further. This is a mathematical result, firmly established within the classical theory, but which tells us about the theory's limits rather than about ultimate physical reality. We know that quantum gravity effects should become important at the Planck scale, and that we do not yet have a complete theory of quantum gravity. This is a theoretical understanding of our theoretical limits, which is a very specific kind of knowledge. Beyond these firm points, we enter the realm of theoretical proposals and motivated speculation. The hot dense phase may have been preceded by a period of rapid accelerated expansion called inflation. Inflation may have begun from a quantum fluctuation in a pre-existing field. The universe may be part of a larger multiverse, may be one phase of a cyclically bouncing cosmos, or may have emerged from a quantum state in which time was not yet defined. These are all ideas being taken seriously by physicists. Some of them make predictions that can be tested. None of them are confirmed. That is the honest map. And with the honest map in hand, we can explore the territory beyond the observational horizon with the right kind of intellectual humility. Not the false humility that refuses to speculate, but the genuine humility that labels its speculation clearly and does not confuse it with fact. The question of what came before the Big Bang is still open. It may remain open for a long time, but it is not unscientific. It is not unanswerable in principle. And the work being done to approach it, the development of inflationary theory, the search for quantum gravity, the design of experiments to detect primordial gravitational waves, the construction of ever more precise CMB instruments, is some of the most ambitious and exciting science being done anywhere. This is the frontier, and we are only at the beginning of what the frontier has to teach us. We have established the map. We have traced the universe's history back through billions of years of expansion and cooling, through the formation of galaxies and stars, through the cosmic dark ages, to the moment when the universe first became transparent and released the oldest light we can directly observe. We have identified the observational pillars that support the Big Bang framework, and we have been honest about where those pillars end and where theoretical inference begins. We have located the singularity not as a physical object, but as a mathematical warning sign, a place where our best classical theory admits it cannot continue. Now we push further. We follow the theoretical trail past the observational horizon into the regime where inference must carry us because observation cannot reach. We examine the leading ideas that try to extend the story backward, evaluate what each one claims, what each one assumes, and what each one would need to be true. And we keep asking the central question at every step: when someone says nothing, which nothing do they mean, and does the evidence support that meaning? The first major theoretical proposal we encounter when we push past the CMB horizon is also the most developed, the most widely accepted among cosmologists, and the most consequential for the question of origins. It is called cosmic inflation. And it is simultaneously one of the most successful ideas in modern cosmology and one of the most difficult to confirm definitively. Inflation is not a single specific theory. It is a class of models that share a common core idea. The idea is that the very early universe underwent a period of extraordinarily rapid accelerated expansion, far faster than the expansion we observe today, driven by a form of energy that behaved like a cosmological constant, but was associated with a dynamical field rather than empty space. This rapid expansion happened before the hot dense phase described by standard Big Bang cosmology, and it set the initial conditions for everything that followed. To understand why inflation was proposed and why it has been so influential, we need to understand three specific puzzles that the standard Big Bang model, taken on its own without any additional physics, cannot explain. These puzzles go by the names the horizon problem, the flatness problem, and the origin of structure. Each one is a genuine scientific puzzle, not merely a philosophical discomfort, and inflation solves all three with a single mechanism, which is part of what makes it so compelling. The horizon problem is the most visually striking of the three. When we look at the cosmic microwave background, we see a nearly perfectly uniform temperature across the entire sky. The temperature is the same, to about 1 part in 100,000, in every direction we look. But here is the puzzle. The regions of the early universe that produced the CMB in opposite directions of the sky were, in standard Big Bang cosmology without inflation, causally disconnected at the time of recombination. They were so far apart that light could not have traveled between them in the time available since the beginning of the universe. They had no way to exchange information or energy, and yet they are at the same temperature to extraordinary precision. In everyday life, if you find two regions at the same temperature, the natural explanation is that they were once in thermal contact. They exchanged energy until they reached equilibrium. But in standard Big Bang cosmology, the regions that produced the CMB in opposite directions of the sky were never in causal contact before recombination. How did they come to be at the same temperature? Why should causally disconnected regions have the same temperature to such high precision? Without an explanation, this is a coincidence so extreme that it strains credulity. Inflation solves the horizon problem by proposing that all the regions we can observe in the CMB today were once in causal contact before inflation began. During the inflationary period, those regions were close enough to reach equilibrium. Then inflation stretched them to vastly larger scales, much larger than the observable universe. After inflation ended, the standard hot Big Bang expansion continued. The CMB we observe is the cooled remnant of what was once a small, causally connected region that inflation stretched to enormous size. The uniformity is not a coincidence. It is the memory of pre-inflationary equilibrium. The flatness problem is a quantitative puzzle about the geometry of space. We observe that the universe is spatially flat to within about 1%. This means the total energy density of the universe is very close to a specific critical value. But in the standard Big Bang model, flatness is an unstable configuration. Small deviations from flatness grow over time. If the universe was slightly positively curved at early times, it would have been much more curved by now. If it was slightly negatively curved, it would have been much more curved in the other direction. For the universe to be as flat as we observe it today, it would have had to be extraordinarily close to perfectly flat at early times, with the flatness maintained to astonishing precision. How precise? At the time of nucleosynthesis, a few minutes into the universe's history, the energy density would have had to equal the critical density to within about 1 part in 10 to the 15th power. At the Planck time, the agreement would need to be 1 part in 10 to the 60th power. This is a degree of fine-tuning that cries out for explanation. Why should the universe begin in such an extraordinarily special state? Inflation solves the flatness problem by noting that during the rapid accelerated expansion, the curvature of space is driven towards zero in the same way that a balloon becomes flatter as it is inflated. A small region of space that started with any reasonable curvature would, after inflation, be stretched to such enormous size that the curvature within the observable portion would be negligible. Just as the surface of a balloon looks flat when you are a tiny ant sitting on it, the universe looks flat after inflation stretched it by an enormous factor, regardless of its initial curvature. The origin of structure problem is the one that connects most directly to what we observe in the CMB. The universe today is not perfectly uniform. It contains galaxies and clusters and filaments and voids. These structures grew from tiny initial density variations. The CMB shows us those initial variations, and they have a specific character. They are nearly scale invariant, present at roughly the same amplitude across a wide range of scales, with a slight tilt towards stronger variations at larger scales. Standard Big Bang cosmology without inflation has no natural mechanism to produce this specific pattern. The initial conditions would need to be specified by hand, imposed as a given without any physical explanation. Inflation provides a mechanism. During the inflationary period, the quantum vacuum was not perfectly uniform. Quantum fields, like all quantum systems, fluctuate even in their lowest energy state. These fluctuations are normally microscopic, confined to tiny scales well below anything observable. But during inflation, the rapid expansion stretched those microscopic quantum fluctuations to cosmological scales. This is a remarkable claim. It says that the largest structures in the universe, the galaxy clusters and superclusters spanning hundreds of millions of light years, trace their origin to quantum fluctuations in the very early universe that were smaller than an atomic nucleus. The scale invariant spectrum is a natural prediction of many inflationary models because the rate of expansion during inflation does not change much from moment to moment, so fluctuations produced at different times are stretched by similar factors, giving them similar amplitudes at different scales. The slight tilt away from perfect scale invariance is also predicted. In most inflationary models, the energy driving inflation slowly decreases as inflation proceeds, which introduces a slight preference for one scale over another and tilts the spectrum. The observed tilt is consistent with many inflationary models and rules out others. This is genuinely productive contact between theory and observation, which is what makes inflation scientifically valuable rather than merely philosophically satisfying. Taken together, these three successes, solving the horizon problem, the flatness problem, and the origin of structure problem with a single physical mechanism, explain why inflation has become the dominant paradigm in early universe cosmology. It is not merely an ad hoc addition to the standard model. It is a physically motivated extension that solves multiple problems simultaneously and makes predictions that can be tested. But we need to be careful here about the difference between success and confirmation. Inflation has been successful in the sense that its predictions are consistent with observations. The CMB power spectrum is consistent with inflationary predictions. The flatness of the universe is consistent with inflationary predictions. The scale invariant spectrum of fluctuations is consistent with inflationary predictions, but consistent with is not the same as confirmed by. A theory is confirmed when it makes a prediction that no alternative explanation could easily reproduce, and the prediction turns out to be correct. Inflation has not yet achieved this level of decisive confirmation. The reason is that inflation is a class of models rather than a single specific theory. Many different inflationary models, driven by many different proposed fields with many different energy profiles, make predictions that are consistent with current observations. This flexibility is partly a strength because it means the general idea is robust. But it is also a weakness because it makes it difficult to rule out inflation as a class. You can rule out specific inflationary models, but the general idea of a period of early accelerated expansion accommodates a wide range of observations without being falsified. The most promising observational handle for distinguishing inflationary models from each other and from alternative proposals is the search for primordial gravitational waves. Inflation should produce not only the density fluctuations that seed galaxies, but also fluctuations in spacetime itself, gravitational waves produced during the inflationary period. These primordial gravitational waves would leave a specific imprint on the polarization of the CMB, producing a pattern called B-mode polarization that cannot be produced by density fluctuations alone. The amplitude of this B-mode signal depends on the energy scale at which inflation occurred. High-energy inflation, occurring near the Planck scale, would produce a detectable B-mode signal. Lower-energy inflation would produce a signal too small to observe with current instruments. Current observations have placed upper limits on the B-mode signal, which constrains the energy scale of inflation, but no primordial B-mode signal has been definitively detected. This rules out the highest-energy inflationary models, but leaves a large class of models viable. Next-generation CMB polarization experiments are being designed with the sensitivity to either detect a primordial B-mode signal at a level consistent with many viable inflationary models, or to push the upper limits down to a level that would rule out a large fraction of the remaining models. This is the observational frontier of inflation research, and its outcome in the coming decade or two will significantly sharpen our picture of what, if anything, drove the early universe's rapid expansion. Now we need to discuss what drives inflation, because the answer is where the connection to the question of nothing becomes explicit and where the concept of the quantum vacuum becomes central. Inflation is driven by a field. Not matter in the usual sense, not radiation, not any of the familiar particles of the standard model of particle physics, but a scalar field, a field that has a value at every point in space but no preferred direction, sometimes called the inflaton. The inflaton's defining property is its potential energy, a function that describes how the field's energy changes as its value changes. For inflation to work, the inflaton must start at a high potential energy value and slowly roll down toward a lower value. During this slow roll, the potential energy dominates over the kinetic energy, and the potential energy has a property that is crucial. It acts like a cosmological constant, driving accelerated expansion. The universe inflates. As the inflaton rolls slowly down its potential, inflation continues. When the inflaton reaches the bottom of its potential and begins to oscillate, it converts its energy into particles and radiation, reheating the universe and initiating the hot Big Bang phase that we know from observation. The key property of the inflaton's potential energy that drives inflation is that it behaves like a constant energy density distributed throughout space. This kind of energy, sometimes called vacuum energy or dark energy in the context of the current universe's acceleration, has a very unusual property. Unlike matter and radiation, which cause spacetime to decelerate its expansion through gravitational attraction, a constant energy density causes spacetime to accelerate its expansion through what is effectively gravitational repulsion. This counterintuitive behavior comes directly from general relativity. The expansion of the universe is governed by both the energy density and the pressure of whatever fills it. Ordinary matter and radiation have positive pressure that, along with their positive energy density, decelerates the expansion. A cosmological constant or inflaton-like field has negative pressure, equal in magnitude to its energy density, and this combination of positive energy and negative pressure results in net acceleration of expansion. The field that drives inflation is thus a very unusual form of matter. It is not nothing. It has energy. It occupies space. It evolves over time. It interacts with gravity in a specific way. It is a fully physical entity described by equations and making predictions, but it is also, in a meaningful sense, unlike anything in our everyday experience or in the standard model of particle physics. No particle corresponding to the inflaton has ever been detected in a laboratory. The inflaton, if it exists, is a hypothetical field whose existence is inferred from the conditions it would have produced rather than from direct observation. This brings us to an important question. Where did the inflaton come from? What set its initial value? Why was it at a high potential energy value rather than a low one? In other words, what were the conditions before inflation? This is where the story becomes genuinely hard, because we do not have a confirmed answer. Different theoretical proposals give different answers, and the evidence does not yet discriminate between them decisively. One class of answers invokes eternal inflation, the idea that inflation never completely stops everywhere, but only ends in localized regions, producing a vast collection of pocket universes or bubble universes embedded in an eternally inflating background. In this picture, our observable universe is one bubble, one region where inflation happened to end and the hot Big Bang proceeded. Inflation is eternal because once it starts somewhere, quantum fluctuations ensure it continues in most of the volume even as it ends in some regions. Eternal inflation changes the question of cosmic origins in an interesting way. Instead of asking what came before the Big Bang, which refers to the beginning of our specific bubble, you ask what is the nature of the eternally inflating background. And that background in many formulations is itself a physical entity with fields and dynamics. It is not nothing. It is a quantum field in a specific state, eternally inflating, governed by physical laws that we can in principle describe mathematically even if we cannot directly observe them. The eternal inflation picture also generates the concept of the multiverse, the idea that our observable universe is just one of an enormous, perhaps infinite, number of pocket universes, each with potentially different physical laws, constants, or initial conditions, depending on the specific version of the theory. The multiverse is one of the most debated ideas in modern cosmology, partly because of its potential scientific content, and partly because of the question of whether it is even in principle testable. The testability question is not trivial. A claim about other universes that we can never observe, even in principle, cannot be directly confirmed by observation. Some physicists argue that this places the multiverse outside the domain of science entirely. Others argue that the multiverse is a prediction of physical theories that are testable in other ways, and that if those theories are confirmed, the multiverse prediction should be taken seriously, even if the individual universes are unobservable. This debate is ongoing and unresolved. What we can say with confidence is that eternal inflation and the multiverse are theoretical proposals that push the question of origins further back without fully resolving it. They replace the question of what came before the Big Bang with a question about the nature of the eternally inflating background, which is itself a physical entity requiring explanation. They do not reach absolute philosophical nothing. They reach a different kind of physical something, one that is less familiar than the hot, dense plasma of the early universe, but is still governed by fields, laws, and dynamics. Before we discuss the quantum vacuum in detail, it is worth pausing to confront a claim that is frequently made in popular accounts of cosmology, and that requires very careful handling. The claim is that the universe came from nothing, and that modern physics has explained or is close to explaining how this could have happened. This claim is often associated with the concept of quantum fluctuations. The argument goes roughly like this. Quantum mechanics tells us that even in a perfect vacuum, energy can spontaneously fluctuate. Particles can appear from nowhere and then disappear again. This happens constantly at the quantum level. Perhaps the entire universe began as a quantum fluctuation of this kind, a temporary borrowing of energy from the vacuum that grew instead of disappearing because of some mechanism that inflation provides. This is not a crazy idea. It has been proposed and developed by serious physicists, including Edward Tryon, who in 1973 suggested that the universe might be a quantum fluctuation of the vacuum. The idea has been refined and developed since then. And there is something genuinely suggestive about the fact that the total energy of the universe, when you add together the positive energy of matter and radiation and the negative energy of gravity, might be close to zero, consistent with a universe that arose from a vacuum fluctuation in which no net energy was created. But here is the critical point that almost every popular account gets wrong. When physicists talk about the vacuum from which the universe might have fluctuated, they do not mean nothing. They mean the quantum vacuum, a specific physical state that is the lowest energy configuration of all the fields that exist. The quantum vacuum is not empty in any intuitive sense. It is filled with quantum fields. It has a definite structure. It obeys specific physical laws. It is a very specific kind of something, not nothing. When a particle and antiparticle appear spontaneously from the quantum vacuum and then annihilate, they do not appear from literal nothingness. They appear from a fluctuation of the quantum fields that are always present in the vacuum. The fields are there even when no particles are present. They are the fundamental entities. Particles are excitations of those fields, and the vacuum is the state in which those excitations are at their minimum, but the fields themselves are always present. So the claim that the universe came from nothing, if it is based on quantum fluctuations, is really the claim that the universe came from the quantum vacuum, which is a very specific kind of physical something. This is a meaningful scientific claim and potentially an important one. But it is not the same as explaining how the universe arose from absolute philosophical nothing. It presupposes the existence of quantum fields and the laws that govern them. It does not explain where those laws came from or why any fields exist at all. To be clear about this is not to diminish the scientific achievement. Explaining how a universe full of matter and radiation could arise from a vacuum state governed by quantum field theory, if that explanation can be made rigorous, would be an extraordinary scientific advance. But it would not answer the deepest version of the question, why is there something rather than nothing, because the something it starts from, the quantum vacuum with its fields and laws, is itself not nothing. The deepest version of the question asks why there are physical laws at all, why there are fields, why the vacuum has any particular structure, why mathematics describes reality, why anything exists rather than the absolute absence of everything, including logic and possibility, and the concept of existence itself. These questions are currently beyond the reach of physics, not because physics is incomplete, though it is, but because they may be asking for a kind of explanation that the scientific method is not designed to provide. This is not a defeat for science. It is an honest recognition of what science is for. Science explains how the universe works by building models that make testable predictions. When those models are confirmed, we understand more about the universe. But every scientific explanation assumes a framework, a set of laws, a set of mathematical structures, a set of physical entities within which the explanation operates. Science cannot explain its own framework from within itself without circularity. The question of why any framework exists at all is a question that currently sits at the boundary between physics and philosophy, and it is not obvious that it has an answer of the kind science provides. This does not mean the question is meaningless. It means it is genuinely open, genuinely hard, and genuinely worthy of serious intellectual engagement. The honest response to it is not a quick dismissal and not a confident answer, but a careful, humble acknowledgement that we are at the limit of what current human understanding can reach. Now let us go deeper into the quantum vacuum itself, because it is genuinely fascinating, and because understanding it properly is essential to evaluating any proposal about cosmic origins. The quantum vacuum is the state of lowest energy in quantum field theory. It is the ground state, the equilibrium configuration to which quantum fields tend when there is no input of energy. In classical physics, the lowest energy state of a system is the one in which everything is at rest. A ball at the bottom of a bowl is in its lowest energy state when it is sitting still at the very bottom with no motion at all. Quantum mechanics changes this picture fundamentally. The Heisenberg uncertainty principle says that you cannot know both the position and momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you can know the other. This is not a statement about the limitations of measurement. It is a statement about the nature of reality. Quantum systems genuinely do not have definite values of both position and momentum simultaneously. Position and momentum are not properties that are just unknown. They are properties that do not simultaneously exist with definite values. Applied to fields rather than particles, this uncertainty has a profound consequence. Even in the vacuum state, fields cannot simply be zero everywhere at all times. A field value of exactly zero with exactly zero rate of change would constitute a perfectly definite state of both the field amplitude and its rate of change, which is analogous to knowing both position and momentum exactly. The uncertainty principle forbids this, so even in the vacuum, fields must fluctuate. They cannot be perfectly still. These fluctuations are not just a theoretical curiosity, they have measurable physical effects. The Casimir effect is one of the most famous examples. If you place two uncharged, parallel metal plates very close together in a vacuum, the quantum fluctuations of the electromagnetic field between the plates are restricted by the presence of the plates, which act as boundary conditions. The fluctuations outside the plates are not similarly restricted. The result is that there is a tiny pressure pushing the plates together, caused by the difference in vacuum fluctuation energy between the inside and outside of the plates. This effect has been measured in the laboratory and agrees with theoretical predictions. The Lamb shift is another example. In the hydrogen atom, two energy levels that classical quantum mechanics predicts should have identical energies turn out to differ by a tiny amount. This difference is caused by the interaction of the electron with the vacuum fluctuations of the electromagnetic field. The electron is constantly being jostled by the quantum vacuum, and this jostling produces a tiny but measurable shift in its energy levels. The Lamb shift was a crucial test of quantum electrodynamics, and its confirmation gave physicists confidence that vacuum fluctuations are a real physical phenomenon. These effects establish that the quantum vacuum is not nothing. It is a seething, active state filled with quantum fluctuations that have real physical consequences. The vacuum is the lowest energy state of the universe's fields, but it is not a state of zero activity. It is a state of minimum activity, constrained by the uncertainty principle to be as quiet as quantum mechanics allows, which is not very quiet at all. The vacuum also has an energy. This is one of the most puzzling aspects of quantum field theory and one of the most consequential for cosmology. Every quantum field contributes a zero-point energy to the vacuum, an irreducible minimum energy that exists even when no particles are present. In quantum mechanics, even a harmonic oscillator in its ground state has a non-zero energy equal to half the energy of one quantum of oscillation. Applied to fields, every mode of every quantum field contributes a half quantum of energy to the vacuum. When you add up these contributions across all modes and all fields, you get a formally infinite result. This is one of the famous infinities of quantum field theory, and it is handled in practice through a procedure called renormalization, which amounts to measuring energy differences relative to the vacuum, rather than trying to assign an absolute value to the vacuum energy. For most purposes in particle physics, the absolute value of the vacuum energy does not matter because only energy differences are physically observable. But for cosmology, the absolute value of the vacuum energy matters enormously. In general relativity, all forms of energy contribute to the curvature of spacetime and hence to the expansion rate of the universe. If the quantum vacuum has a non-zero energy density, that energy density curves spacetime and affects the expansion. The observed accelerated expansion of the universe suggests that something is causing gravitational repulsion on large scales, something behaving like a positive vacuum energy or cosmological constant. This observation is consistent with the vacuum energy having a small positive value. The problem is that when physicists try to calculate the vacuum energy from first principles using the known fields of particle physics, they get a result that is enormously larger than what cosmological observations allow. The theoretical estimate exceeds the observed value by a factor of somewhere between 10 to the 60th and 10 to the 120th power, depending on what cutoff you use for the calculation. This discrepancy, the cosmological constant problem, is one of the deepest unsolved problems in all of physics. The problem is not that the vacuum energy is predicted to be too large and observed to be small. A vacuum energy of exactly zero might be explained by some symmetry, and indeed some physicists hoped for this. The problem is that the observed vacuum energy is small but not zero. It has a specific measured value that is extraordinarily small compared to theoretical expectations, but not zero. This precise small non-zero value has no natural explanation in any current theoretical framework. The cosmological constant problem is relevant to the question of nothing because it illustrates how profoundly the quantum vacuum resists being treated as empty. Even our best attempt to describe the lowest energy state of the universe comes out with a vacuum energy that is either irreducibly infinite, requiring renormalization to make sense of, or small but non-zero, requiring explanation for why it is the specific value it is. The vacuum is a physical object with a physical energy. It is the ground floor of a building with an enormous number of floors above it, but it is still part of the building. It is not empty space. It is not nothing. There is a further aspect of the quantum vacuum that is particularly relevant to inflationary cosmology and to the question of where the universe's structure came from. The quantum vacuum fluctuates, and during inflation, those fluctuations were stretched from microscopic to cosmological scales. To understand why this matters, think about a quantum field in its vacuum state. The field is not at zero everywhere. It fluctuates with typical fluctuation amplitudes at each scale, determined by the uncertainty principle and the field's dynamics. Normally, these fluctuations are confined to tiny scales, far smaller than anything directly observable. They are constantly appearing and disappearing on timescales set by the uncertainty principle. The more energetic the fluctuation, the briefer its existence. During inflation, the rapid expansion of the universe changes the fate of these fluctuations. As the universe expands, the physical wavelength of each fluctuation is stretched. If the expansion is fast enough, a fluctuation can be stretched to a scale larger than the horizon. The distance light can travel in the age of the universe at that moment. Once a fluctuation is stretched beyond the horizon, it is frozen. It cannot oscillate away because no causal process can operate on scales larger than the horizon. The fluctuation becomes a fixed classical perturbation in the density of the universe. As inflation ends and the standard hot Big Bang phase begins, these frozen perturbations persist. As the universe expands and the horizon grows, these superhorizon perturbations come back within the horizon and begin to evolve again. But they are now classical density variations, real differences in the density of matter and radiation across space. Gravity then amplifies these variations over billions of years, turning tiny differences into the galaxies, clusters, and cosmic web we observe today. This mechanism is one of the most profound connections in modern cosmology. The largest structures in the visible universe originated as quantum fluctuations of a field in the very early universe, stretched to cosmic scales by the rapid expansion of inflation. The statistical properties of these fluctuations, including their near-scale invariance and their Gaussian distribution, are predictions that can be tested against the CMB and large-scale structure observations. The prediction of Gaussian fluctuations is particularly important and particularly testable. Quantum fluctuations in the simplest inflationary models produce density perturbations whose statistical distribution is very close to Gaussian, meaning they are described by a normal distribution with no strong correlations between different scales. This is a specific prediction that can be checked. More complex inflationary models and alternative scenarios can produce non-Gaussian fluctuations. Current observations are consistent with Gaussianity, but searches for deviations from Gaussianity, called primordial non-Gaussianity, are an active area of research because detecting such deviations would discriminate between different models of the early universe. What this quantum origin of structure means for the question of nothing is interesting. It means the universe's structure, all the complexity of galaxies and stars and planets and life, traces its origin to quantum fluctuations of a field in a near-vacuum state. It did not come from nothing in any absolute sense. It came from the quantum vacuum with its fluctuating fields, but it came from a state that, by everyday standards, might reasonably be called as close to nothing as physics permits, and yet that state was not nothing. It was a quantum field in a specific low-energy state, governed by specific physical laws, embedded in a spacetime that was rapidly expanding. It was a very particular kind of something, defined by its relationship to the laws of quantum mechanics and general relativity. The laws themselves remain unexplained by this picture. They are assumed. They are not derived from anything more fundamental within the inflationary framework. So inflation, for all its explanatory power, does not reach philosophical nothing. It reaches the quantum vacuum, which is a structured physical state, and it derives the universe's structure from that state using well-defined physical processes. This is an extraordinary achievement if it is correct, but it is not an explanation of ultimate origins. It is an explanation of how certain observed properties of our universe follow from a specific physical state and a specific physical mechanism. The state and the mechanism are themselves assumed, not explained. Let us now think carefully about what the singularity really tells us, because it is the most direct mathematical statement about where our description of the universe runs out, and it is the place where the word nothing is most temptingly inserted into the story. The Penrose-Hawking singularity theorems, proved in the 1960s and 1970s, established that singularities in general relativity are not mathematical artifacts of special symmetric solutions. Under broad physical conditions, singularities are generic features of the classical theory. The conditions required are reasonable in the context of the universe: positive energy density, the causal structure of a sufficiently large expanding universe, and the absence of certain exotic matter that could violate energy conditions in specific ways. The conclusion is rigorous. Classical spacetime under these conditions contains an incomplete geodesic in the past direction. A geodesic is the path of a freely falling observer, the closest thing to a straight line in curved spacetime. If a geodesic is incomplete, it means the path of a freely falling observer cannot be extended arbitrarily far into the past within the classical spacetime. There is a boundary. The history simply stops. This is not the same as proving that nothing existed before the boundary. It is proving that classical spacetime, described by general relativity, cannot be extended beyond the boundary. The difference is subtle but crucial. The theorem is a statement about a mathematical theory, not a statement about physical reality. It says that classical general relativity, applied to the conditions of the early universe, predicts its own breakdown. It does not say what, if anything, replaces it. To make the point with an analogy, Newtonian mechanics, applied to the interior of a black hole, would also give nonsensical predictions. But we do not conclude from this that the interior of a black hole is physically nothing. We conclude that Newtonian mechanics is the wrong theory to use there. General relativity replaces it and gives better answers. Similarly, the singularity theorems tell us that general relativity is the wrong theory to use at the boundary of the early universe. They do not tell us what the right theory gives. They leave that as an open question. The open question is quantum gravity. If we had a complete working theory of quantum gravity, we could in principle ask what it predicts for the state of the universe near and at the epoch when classical general relativity breaks down. We might find that the singularity is replaced by a smooth quantum geometry with no boundary. We might find that the universe bounces from a previous contracting phase. We might find something else entirely that we cannot currently anticipate. We do not know because we do not have the theory. What we do have are candidate theories, frameworks that have been developed to some degree, but are not complete and not confirmed. Loop quantum cosmology, string cosmology, and the Hartle-Hawking no-boundary proposal are among the most developed. Each one handles the singularity differently, and each one gives a different picture of what happens at and before the Planck era. Each one deserves careful examination, because they illustrate how different theoretical choices lead to different answers to the question of before and nothing. Loop quantum cosmology is an application of loop quantum gravity, a candidate theory of quantum gravity that attempts to quantize spacetime itself, rather than treating spacetime as a fixed background on which quantum fields live. In loop quantum gravity, the geometric properties of space, its area and volume, are quantized. They come in discrete units, like energy in quantum mechanics. Space is not a smooth, continuous fabric. It has a granular structure at the Planck scale, like a digital image that looks smooth from a distance but reveals individual pixels when you zoom in sufficiently. Applied to cosmology, loop quantum gravity modifies the equations that govern the expansion of the universe at very high densities. In standard general relativity, the expansion equations blow up as density increases without bound. In loop quantum cosmology, the discreteness of space introduces a quantum correction that becomes important at Planck densities. This correction effectively introduces a repulsive term that prevents the density from becoming infinite. The result is striking. In loop quantum cosmology, as you trace the history of the universe backward and the density approaches the Planck density, the standard equations of expansion are modified. Instead of the density diverging to infinity and the expansion rate reaching a singularity, the universe bounces. The contraction, which in the standard picture would lead to a singular point, instead transitions to expansion. The universe cycles through a sequence of expansions and contractions, with each contraction ending in a bounce rather than a singularity. This bounce replaces the classical singularity with a smooth quantum transition. The word before regains a meaning because there was a previous phase of the universe before the bounce. The question of origins is pushed back to asking about the nature of the contracting phase that preceded the bounce, which in turn raises the same questions about its origin. Loop quantum cosmology makes specific predictions that distinguish it from standard cosmology. The bounce produces modifications to the primordial power spectrum at scales comparable to the Planck length that are stretched to observable scales by subsequent inflation. The modifications are small and depend on the parameters of the bounce, but they are in principle observable in the CMB. Current observations are consistent with loop quantum cosmology in a range of parameter space, but no distinctive prediction of loop quantum cosmology has been confirmed in a way that would rule out the standard picture. The honest assessment of loop quantum cosmology is that it is a mathematically developed framework that modifies the singularity in an interesting way and makes testable predictions. It is not a confirmed theory. The underlying loop quantum gravity, from which it derives, has not been confirmed as the correct theory of quantum gravity, and the specific predictions of loop quantum cosmology for the CMB require a level of precision in observations that may or may not be achievable in the coming decades. String cosmology draws on string theory, which is currently the most mathematically developed candidate for a unified theory that includes quantum gravity. String theory replaces point particles with one-dimensional vibrating strings and requires extra spatial dimensions beyond the three we observe. The different vibrational modes of strings correspond to different particles, including a massless spin-2 particle that corresponds to the graviton, the quantum of gravity. In string cosmology, the singularity is handled differently from loop quantum cosmology. String theory has a property called T-duality, which relates small compactified dimensions to large ones. A string theory compactified on a circle of radius r is equivalent to a theory compactified on a circle of radius proportional to 1 over r. This duality means that as you shrink a dimension to zero size, the physics is equivalent to a theory with a growing dimension, effectively preventing the singular collapse to zero size. Applied to cosmology, T-duality suggests that the pre-Big Bang scenario might be possible. In the pre-Big Bang scenario proposed by Gabriele Veneziano and Maurizio Gasparini in the early 1990s, the universe before our Big Bang was in a state of perturbative string vacuum, slowly contracting and becoming more and more curved. T-duality then connects this collapsing phase to the expanding, high-curvature phase we identify as the Big Bang. The singularity is replaced by a transition between two phases related by T-duality. This is a beautiful idea, but it faces significant challenges. The transition between the contracting and expanding phases, the bounce that would connect them, requires physics beyond what T-duality alone provides. String theory at high curvature involves corrections from higher dimensional branes and other stringy phenomena that are not fully under theoretical control. The detailed modeling of the bounce is an ongoing challenge that has not been fully resolved. String cosmology more broadly has produced many interesting ideas about the early universe, including the ekpyrotic scenario proposed by Paul Steinhardt and Neil Turok, in which two large extra dimensions collide along a third, generating the energy and density of our Big Bang. But these scenarios face similar challenges. They require high-curvature string physics that is not fully controlled, and their specific predictions for the CMB have not been confirmed or ruled out definitively. The overall state of string cosmology is that it provides a rich mathematical framework with many interesting possibilities for the early universe, but it has not yet made decisive predictions that have been confirmed and that distinguish it from alternatives. The framework is compelling because string theory is the most developed candidate for quantum gravity, but compelling frameworks are not the same as confirmed theories. The Hartle-Hawking no-boundary proposal is perhaps the most conceptually distinctive of the quantum gravity approaches to cosmology, and it is the one that most directly addresses the question of the universe's beginning in a new way, rather than simply pushing it back further. The proposal was developed by James Hartle and Stephen Hawking in 1983 using a mathematical technique called the path integral, borrowed from quantum mechanics and applied to quantum gravity. In quantum mechanics, the probability of a system evolving from one state to another is calculated by summing over all possible paths between those states, each weighted by a factor involving the action, a measure of the path's physical content. This is Feynman's path integral formulation of quantum mechanics. Applied to gravity, the path integral sums over all possible geometries of spacetime, each weighted by a factor involving the gravitational action. Hartle and Hawking proposed that the wave function of the universe, a quantum mechanical description of the universe's state, could be defined by this gravitational path integral with a specific choice of boundary conditions. Crucially, they proposed using a no-boundary condition. The geometry summed over should have no boundary in the past. To implement this mathematically, they used a technique called Wick rotation, in which time is replaced by imaginary time in the equations. When you do this, the distinction between time and space blurs. A dimension that was temporal becomes effectively spatial. In Euclidean quantum gravity, which is what you get after Wick rotation, there is no fundamental distinction between past and future, and the geometry can be smooth and closed without a boundary. The picture that emerges from the no-boundary proposal for the origin of the universe is something like the following. Imagine the time dimension of the universe near its beginning becoming like a spatial dimension. The geometry of the early universe is then like the surface of a sphere, smooth, closed, without any boundary or edge. Just as the surface of a sphere has no north pole in the sense of a special singular point where the geometry breaks down, the universe in the no-boundary proposal has no singular beginning. Time near the beginning is not really time as we usually understand it. It is more like another spatial direction. The universe begins in a sense, but without a singularity, without a first moment where conditions are infinite, and without requiring any prior state or cause. The no-boundary proposal has attracted enormous attention and generated significant debate. It provides a specific quantum mechanical calculation for the probability of different possible universes, and it predicts that the most likely universe is the one with the simplest, smoothest initial conditions consistent with the observed universe. In principle, it gives a concrete answer to the question of why the universe has the initial conditions it does, rather than some other set. But the proposal also faces significant challenges. The Euclidean path integral over geometries is difficult to define precisely. The sum over all geometries is mathematically ill-defined unless you restrict it in some way, and different choices of restriction give different answers. There have been debates about whether the no-boundary wave function predicts a universe like ours with high probability or low probability, with different calculations giving different answers depending on how the sum is regulated and interpreted. These are not merely technical quibbles. They go to the heart of whether the proposal is well-defined as a physical theory. More fundamentally, the no-boundary proposal uses quantum mechanics and general relativity in a regime where neither has been tested. It applies the path integral to gravity at Planck scale energies, where the rules of quantum field theory on a fixed background spacetime do not apply, and where even the concept of a smooth spacetime geometry may break down. The proposal is an extrapolation of known physics into a regime of unknown physics. Whether the extrapolation is valid is something we cannot currently determine. What the no-boundary proposal achieves conceptually, regardless of its ultimate correctness, is to show that the question of what came before the Big Bang can be genuinely dissolved rather than merely pushed back. If time near the beginning is not really time in the usual sense, if the geometry is smooth without a boundary, then there is no before to ask about. The question is not answered. It is shown to be based on a mistaken assumption about the nature of time near the beginning. This is the kind of conceptual shift that the most profound physics sometimes requires. Rather than finding the answer to a question, it changes what the question means. Whether this particular version of the shift, the no-boundary proposal, is the correct one is unknown. But the possibility that the question of before the Big Bang is a malformed question, based on importing concepts of time that do not apply near the beginning, is a genuine scientific possibility that must be taken seriously. There is another class of proposals that deserves careful attention: cyclic models. These are proposals in which the universe does not have a single beginning, but goes through a sequence of expansions and contractions, each cycle potentially producing a universe similar to our own, with the beginning of our current expansion being the latest in a potentially infinite series of cycles. The appeal of cyclic models is obvious. They avoid the need to explain a singular beginning because there is no beginning. The universe has always existed in some form, cycling through phases of expansion and contraction. The question of what came before the Big Bang has a simple answer in cyclic models: a previous cycle. But this answer immediately raises further questions. Were all cycles identical? If not, what determines how they differ? What drives the cycling? What ensures the universe survives the bounce from contraction to expansion without collapsing to a singularity? And if the cycles have been going on forever, what determines the properties of the cycles, including why our current cycle has the particular properties it does? The oldest and simplest cyclic models, dating back to early cosmology in the 20th century, imagined a universe that expands, then contracts due to gravity if the density is high enough, then bounces and expands again. These models faced immediate problems. The entropy of the universe increases with each cycle, as required by the second law of thermodynamics, meaning each successive cycle must be longer than the previous one. If you trace this backward in time, the cycles get shorter and shorter, and you eventually reach a cycle so short it is effectively a singular beginning. The cycling does not eliminate the need for an initial state. It pushes it back but does not remove it. More sophisticated cyclic models have been developed that try to avoid this problem. The ekpyrotic model mentioned earlier, in its cyclic version developed by Steinhardt and Turok, involves two membranes in a higher dimensional space periodically colliding. The collision generates the energy of the Big Bang. After expansion, the universe eventually settles into a quiet state, and the membranes slowly drift together again for another collision. This model attempts to address the entropy problem by having the entropy per unit volume decrease during the quiet phase between cycles, because the volume of space grows while entropy production pauses. The cyclic ekpyrotic model is a serious theoretical proposal that addresses the same cosmological puzzles as inflation. It can potentially explain flatness, homogeneity, and the origin of scale-invariant fluctuations. It makes predictions for the CMB that differ from inflationary predictions in specific ways, particularly regarding the primordial gravitational wave background. Inflation generally predicts a detectable level of primordial gravitational waves. Simple cyclic ekpyrotic models tend to predict a primordial gravitational wave background too small to detect with near-term experiments. This means the detection of primordial gravitational waves through CMB B-mode polarization would favor inflation over simple ekpyrotic cycling, while non-detection would keep the cyclic option alive. This is a real scientific contest with observable consequences, which is exactly what makes it scientifically valuable. The contest has not yet been decided because neither a detection nor a sufficiently strong non-detection has been achieved. What cyclic models illustrate, perhaps more clearly than any other class of proposals, is that the question of cosmic origins is not equivalent to the question of cosmic beginning. If the universe cycles, there may be no beginning in the sense of a first moment, but there are still deep questions about the nature of the cycling, the laws that govern it, and why those laws are what they are. The question shifts from when did it start to why does it cycle and what determines the properties of the cycles. These are different questions, but they are equally deep. At this point in the investigation, a pattern has emerged that is worth making explicit. Every theoretical proposal that tries to extend the story of the universe back past the classical Big Bang singularity does one of two things. Either it replaces the singularity with a transition to a previous physical state, as in the cyclic models and some versions of loop quantum cosmology, or it dissolves the singularity by showing that the concept of time near the beginning is not what we thought it was, as in the no-boundary proposal. In the first case, the question of origins is pushed back further. We now need to explain the previous state. In the second case, the question of origins is reframed. We now need to understand what it means for time to be emergent, or for geometry to be smooth without a boundary. In neither case do we reach philosophical nothing. We reach either a different physical state or a different conceptual framework. This is the fundamental result of all serious theoretical work on cosmic origins. Every proposal either posits a previous state or changes what origins means. None of them derive the universe from absolute philosophical nothing, from the complete absence of laws, fields, space, time, and possibility. This is not a failure of imagination or ambition. It is a reflection of a deep logical point. To derive something, you need a framework within which derivation operates. You need laws, mathematics, logic, some set of prior conditions or structures. Any derivation that claims to start from truly nothing must smuggle in at least the logical framework that makes derivation possible. This does not mean the origin of the universe is mysterious in an indefinite or vague way. The mystery is specific. We do not know the correct theory of quantum gravity. We do not know which, if any, of the proposed extensions of standard cosmology is correct. We do not know whether time has a beginning in any physical sense or whether it is emergent from a more fundamental description. We do not know whether the inflationary field exists and what its properties are. We do not know whether the universe is part of a larger multiverse. These are specific, identifiable gaps in our knowledge. Some of them may be closed by future observations. Others may require theoretical breakthroughs. A few may require new conceptual frameworks that we cannot currently envision. But they are not gaps in knowledge that permit the confident assertion that before the Big Bang there was nothing, because that assertion, in its philosophical sense, is not supported by any evidence and is not implied by any theoretical proposal. There is one more topic that belongs in this examination of theoretical proposals: the question of physical laws themselves. Even if we accept that the universe emerged from a quantum vacuum state driven by inflationary dynamics, or bounced from a previous cycle, or emerged from a no-boundary quantum geometry, we still face the question of where the laws that govern these processes came from. Physical laws are not objects. They do not occupy space or carry energy. They are the rules that describe how physical objects behave. And yet they are extraordinarily specific. The laws we observe are not just any laws. They are laws with very particular mathematical structures and very particular values for the constants they contain. Why these laws? Why these values? This is the question of fine-tuning, and it has been discussed in cosmology and philosophy of physics for decades with no consensus resolution. Some constants of nature appear to be extraordinarily fine-tuned for the existence of complex structures like atoms, stars, and ultimately life. The strength of gravity relative to electromagnetism, the masses of quarks and electrons, the magnitude of the cosmological constant, all of these have specific values that, if changed even slightly, would produce a universe with no stars, or no stable atoms, or no chemistry of any kind. The universe appears, in this sense, to be exquisitely adjusted for the existence of complexity. This observation has been used to motivate several different theoretical responses. The anthropic principle, in its weak form, notes that we can only observe the universe from within, which means we can only observe a universe that permits our existence. If a parameter has a range of possible values, we necessarily find ourselves in a universe where the parameter has a value compatible with our existence. This is not a deep explanation. It is a selection effect, but it does mean that the apparent fine-tuning need not be as mysterious as it first appears, because we should not be surprised to find ourselves in a universe where conditions permit our existence. The anthropic principle becomes more powerful if there are many universes with different values of the fundamental constants, because then our observation of a finely tuned universe is explained by the fact that we exist in one of the rare universes where the constants permit complexity and observers. The multiverse provides the ensemble of universes over which the anthropic selection operates. This is the anthropic multiverse argument, and it is genuinely controversial. Critics of the anthropic multiverse argument make several points. First, it requires accepting the existence of an enormous number of unobservable universes on the basis that they are predicted by a theory, which is itself not directly confirmed. Second, it is not clear that the argument is predictive in any useful sense, because if almost any value of a constant is realized somewhere in the multiverse, then observing any value tells us little about the theory. Third, even with the multiverse, you still need to explain why the laws of quantum mechanics and general relativity, which govern the multiverse itself, are what they are. The multiverse pushes the fine-tuning problem back but does not eliminate it. Proponents of the anthropic multiverse counter that it does make predictions in some cases, particularly for the value of the cosmological constant, which was predicted to be small but non-zero before the discovery of cosmic acceleration confirmed this prediction. Whether this counts as a successful prediction of the multiverse or a successful prediction of the anthropic principle is debated. An alternative response to fine-tuning is to search for a deeper theory from which the values of the constants can be derived. If the constants are not fundamental, but are determined by a deeper physical mechanism, then the fine-tuning is explained by that mechanism rather than by anthropic selection. String theory has been proposed as a candidate for such a deeper theory, but so far it has not succeeded in deriving the values of the standard model parameters from first principles. Instead, string theory appears to have a vast landscape of possible solutions with different values of the constants, which some physicists see as supporting the multiverse picture and others see as a failure of the theory's predictive power. There is also a more radical philosophical response, which is that the question of why these laws rather than others may not have an answer of the kind we expect. Physical laws may not be the kind of thing that can be explained by reference to prior causes or deeper structures. They may be the terminus of all explanation, the bedrock beneath which no further bedrock exists. In this view, asking why the laws are what they are is like asking why mathematics is logical or why logic is consistent. These may be questions that reach the absolute limit of what explanation can mean. This is a genuinely uncomfortable conclusion for anyone who believes that every question has an answer, but intellectual honesty requires acknowledging it as a possibility. Not every question that can be posed in grammatically correct English has a physically meaningful answer, and the question of why the laws of physics are what they are may be one of the questions that reaches the edge of what it is possible to explain. The honest summary of where we stand is this. We have traced the universe's history back through 8 billion years of expanding, cooling evolution with high confidence based on multiple independent observations. We have identified the earliest moment we can directly observe with electromagnetic radiation, the cosmic microwave background, and we have extracted from it a remarkably detailed picture of the universe's composition, geometry, and initial conditions. We have shown that the standard Big Bang model, combined with the framework of cosmic inflation, provides a powerful and coherent account of the universe's observed properties. We have been honest that inflation is not yet decisively confirmed, that alternative proposals exist, and that they make different predictions that future observations can in principle discriminate between. We have identified the classical singularity as a breakdown of the theory rather than a physical object, and we have explained why this breakdown points to the need for quantum gravity. We have surveyed the leading proposals for what quantum gravity implies for the earliest moments, including loop quantum cosmology, string cosmology, and the no-boundary proposal. We have been honest that none of these are confirmed, and that the correct theory of quantum gravity remains unknown. We have examined cyclic models and the multiverse, and assessed their scientific status carefully. Throughout, we have kept track of which version of nothing each proposal is invoking. The quantum vacuum is not philosophical nothing. The no-boundary geometry is not empty space. The pre-bounce contracting universe is not absolute non-being. Every serious scientific proposal about the early universe starts from some physical state or structure, not from the complete absence of everything. This is the honest scientific position. It is not a failure, it is a finding. The finding is that science can trace the universe's history back to extraordinary extremes and can identify with precision the boundary of its current knowledge. It can propose and evaluate and test theories that try to extend that knowledge further. And it can be honest about where the boundary is and what kind of thinking would be needed to cross it. The boundary is not nothing. It is the limit of our current best theories, pressed against a regime of physics we do not yet fully understand. Beyond that boundary, something may lie, something that a future theory of quantum gravity may describe. What that something is, we do not know. And that genuine not knowing, that specific, precisely located ignorance, is one of the most important things science can tell us. It tells us not just what we know but what we do not know, and it tells us where to look and what we would need to find to know more. That is not a failure. That is the method. The question we started with was whether there was truly nothing before the Big Bang. The honest answer, after following the evidence as far as it reaches and examining the theoretical proposals that try to reach further, is that we do not know. But we know more precisely than ever before what we do not know. And we know that the nothing that might have preceded the universe, if that concept applies at all, is not the simple darkroom emptiness our intuition imagines. It is not a void waiting to be filled. It is not an empty stage before the performance. It may be a quantum state of spacetime. It may be a no-boundary geometry where time is not yet time. It may be a previous cycle of cosmic expansion. It may be a deeper physical description that we do not yet have the vocabulary to articulate. Or it may be that the question itself is malformed, asking for a before that does not exist in any physical sense. Each of these possibilities is genuinely different. Each carries different implications for how we understand existence, time, causality, and the nature of physical law. Each is being taken seriously by serious physicists, and none of them is confirmed. The mystery at the beginning of everything is real. It is not a mystery that ignorance has inflated beyond its proper size. It is a mystery that knowledge has located with increasing precision, revealing its true shape and its true depth. It is a mystery at the intersection of physics and philosophy, where the most fundamental questions about the nature of reality live. And it is a mystery that the ongoing work of science, guided by observation, constrained by evidence, and disciplined by honesty, continues to illuminate one carefully measured step at a time. What lies at the beginning of everything? We do not know, but we know far more than our ancestors did about what the question means. We know which approaches work and which fail. We know where the map ends, and we know that the map is still being drawn. The universe, at its deepest level, remains an open question. And an open question, honestly held, is not a failure of understanding. It is the most honest possible expression of the state of knowledge at the frontier of what human beings have yet managed to figure out about the world they inhabit. The work continues. The observations accumulate. The theories are tested, and the mystery, precisely because it is real, drives the best minds in physics forward with the same relentless curiosity that built the map we have so far. That is where we leave it, not at an answer, at the edge, which is, for now, exactly where the truth is. We have followed the evidence back to its limit, and we have surveyed the theoretical landscape that lies beyond that limit. Now we go deeper into the specific ideas, the specific mathematics, and the specific physical intuitions that drive the most serious attempts to understand what the universe's beginning actually means. We have been careful, and we will remain careful, but careful does not mean timid. The ideas in this part of the story are among the most ambitious and most consequential in all of human thought, and they deserve to be engaged with the full weight of what they are actually claiming. We begin with a question that sounds philosophical, but turns out to be precisely scientific. What is time? Not what does a clock measure, not how do we experience its passage, but what is time in the most fundamental physical sense? What is the nature of the thing we call time when we strip away all our intuitions about it and look at what physics actually says? The answer, it turns out, is far stranger than almost anyone suspects, and the strangeness is not speculative. It is built into our best confirmed theories. It was already there in Einstein's work a century ago, and it has been deepened and complicated by every subsequent development in fundamental physics. Understanding what time actually is, in the physical sense, is essential to understanding why the question of what came before the Big Bang is so genuinely difficult, and why the answers that serious physicists propose are so different from the answers that common sense would suggest. In Newtonian physics, time was absolute. It flowed at a uniform rate everywhere in the universe simultaneously. Every clock, if perfectly constructed and undisturbed, would measure the same time. Events had a definite sequence that every observer would agree on. The past was fixed, the future was open, and the present was a universal now that divided them. This picture of time felt so obviously correct that Newton took it as a given, a background assumption so fundamental it barely needed stating. Time was the river in which everything else swam, and the river flowed at a constant rate regardless of what was in it. Einstein's special theory of relativity demolished this picture in 1905. The revelation came from taking seriously a single experimental fact. The speed of light is the same for all observers regardless of their motion. This fact, confirmed by experiment and resistant to all classical explanations, forced Einstein to abandon the assumption of absolute simultaneity. If two observers moving relative to each other both measure the same speed for the same light beam, then their measurements of time and space must differ in systematic ways. Events that are simultaneous for one observer may not be simultaneous for another. Time passes at different rates for observers in relative motion. The river of time is not universal. It flows at different rates for different travelers. This is not a small correction. It is a fundamental change in what time is. Time in special relativity is not a universal background. It is a local quantity, measured by a particular observer's clock, dependent on the observer's state of motion. Two observers who travel different paths through spacetime between the same two events will in general measure different elapsed times. The total time elapsed on a path depends on the geometry of the path, not just on the start and end points. Time is path-dependent. General relativity extended this revolution by showing that gravity curves spacetime, and spacetime curvature means that the rate at which time passes depends on the gravitational potential. Clocks tick slower in stronger gravitational fields. This is not a metaphor. It is a measured fact. GPS satellites have to correct for this effect, because they are in a weaker gravitational field than clocks on Earth's surface, and therefore run slightly faster. Without the correction, GPS would accumulate position errors of kilometers per day. So even in confirmed, well-tested physics, time is not universal and absolute. It is local, relative, path-dependent, and affected by gravity. The intuition of a universal clock ticking away independent of everything else is already wrong, not at the level of speculation, but at the level of tested physics that underpins our technological infrastructure. Cosmological time, the time coordinate used to describe the evolution of the universe as a whole, is a special case that works because of the universe's large-scale symmetry. On the largest scales, the universe looks the same in every direction and at every location. This symmetry means there is a natural set of observers, called comoving observers, who are at rest with respect to the average matter flow of the universe. These observers all measure the same elapsed time since the Big Bang, and this shared elapsed time becomes the cosmic clock. It is the time we use when we say the universe is 13.8 billion years old, but this cosmic clock is a consequence of symmetry, not a fundamental property of time. It works because the universe happens to be sufficiently homogeneous and isotropic on large scales. Near the very beginning, where conditions were more extreme and quantum effects may have dominated, this symmetry may have been absent, or the concept of a comoving observer may not have been well defined. The cosmic clock may have had no meaning in the earliest moments, not because nothing was happening, but because the physical conditions that make the clock tick were not yet established. This is a more subtle version of the same point made by the North Pole analogy. Cosmic time is defined in terms of the large-scale structure of the universe. Near the beginning, if the universe did not yet have that large-scale structure, the concept of cosmic time may not apply. Asking what happened before time began may be asking for the value of a quantity that was not yet defined, like asking for the temperature of a system before the concept of temperature applies to it. In statistical mechanics, temperature is a property of systems with many degrees of freedom in equilibrium. A single particle does not have a temperature. A small collection of particles may not be in sufficient equilibrium for temperature to be a useful concept. Temperature is an emergent property that applies when certain conditions are met. If those conditions are not met, the question of what temperature the system has is not unanswerable. It is inapplicable. Something analogous may be true of time in quantum gravity. Time as we know it, as a smooth, continuously flowing parameter that orders events and is measured by clocks, may be an emergent concept that applies when certain physical conditions are met. Those conditions include the existence of classical spacetime, which is itself an approximate description valid only when quantum gravitational effects are small. In the extreme conditions of the very early universe, or in the regime described by a complete theory of quantum gravity, time as we know it may simply not apply. The question of what came before may be like asking what temperature a single particle has, not hard to answer. Inapplicable. This possibility, that time is emergent rather than fundamental, is one of the deepest and most radical ideas in contemporary theoretical physics. It is not a fringe speculation. It appears in multiple serious research programs, including loop quantum gravity, string theory, and holographic approaches to quantum gravity. And it has a profound implication for the question of cosmic origins. If time is emergent, then the question of what came before the Big Bang is not just hard to answer. It may be a question that presupposes the existence of something, a temporal framework within which before has meaning, that did not exist in the regime we are trying to describe. To understand how time can be emergent, we need to look at one of the strangest results in quantum gravity, the Wheeler-DeWitt equation. In the 1960s, John Wheeler and Bryce DeWitt developed an equation that was intended to be the quantum mechanical equivalent of Einstein's field equations. Just as Einstein's equations describe how the geometry of spacetime evolves, the Wheeler-DeWitt equation was intended to describe the quantum state of spacetime as a whole. It is, in a rough sense, the Schrödinger equation of the universe. The Wheeler-DeWitt equation has a property that is deeply strange and deeply significant. It does not contain time. Unlike the Schrödinger equation in ordinary quantum mechanics, which describes how a quantum state changes over time and therefore has time as an explicit variable, the Wheeler-DeWitt equation is static. The wave function of the universe that it governs does not evolve. It simply exists as a timeless mathematical object that encodes the quantum state of all possible geometries. This is called the problem of time in quantum gravity, and it has been discussed and debated for decades. In ordinary quantum mechanics, time is a background parameter, an external variable against which quantum states evolve. You describe a quantum state at time t and calculate its state at a later time t prime. The background time is taken for granted. But in a theory of quantum gravity, there is no background spacetime. Spacetime is itself the dynamical variable. You cannot take time for granted when time is part of what you are trying to describe. The Wheeler-DeWitt equation captures this difficulty directly. In the resulting formalism, time as an external parameter simply does not appear. The wave function of the universe is a function of three-dimensional geometry, the spatial geometry of the universe at each moment, but not of a time variable. How then does time emerge? How does the universe that we experience, with its clear sense of past and future, and its clocks that tick and its events that have duration, arise from a timeless quantum state? One answer, developed by Don Page and William Wooters in the 1980s, and subsequently developed by many others, is called the conditional probability interpretation, or relational time. The idea is that time emerges from correlations between different parts of the universe. Consider a universe described by the Wheeler-DeWitt equation, a timeless quantum state of all the matter and geometry in the universe. Now pick one part of the universe and call it the clock. It could be a particular quantum field, or a particular degree of freedom that behaves like an oscillator. The question is not what is the state of the rest of the universe at time t, because there is no external time t. The question is what is the state of the rest of the universe, given that the clock reads t. This is a conditional probability, not an unconditional one, and the remarkable result is that this conditional probability evolves in a way that looks exactly like the evolution described by the usual time-dependent Schrödinger equation. Time in this picture is not a fundamental property of reality. It is a relational property, defined by the correlation between different parts of the universe. If this picture is correct, then the question of what came before the Big Bang takes on a very different meaning. There is no absolute time within which the universe exists. There are only correlations between different parts of the universe, and the apparent flow of time emerges from those correlations. Near the Big Bang, in the regime described by the full Wheeler-DeWitt equation, those correlations may not give rise to a well-defined sense of time. The Big Bang is not a moment in a pre-existing time. It is a region of the universe's quantum state, where the correlations that produce the experience of time are not established in the usual way. This is deeply counterintuitive, but it is a logical consequence of taking seriously the absence of a background time in quantum gravity. If you take the Wheeler-DeWitt equation seriously as a description of the universe at the most fundamental level, then time is not given to you for free. You have to construct it from the physics. And the construction may fail near the beginning, not because nothing is happening, but because the conditions that make time a useful concept are not yet met. The idea of emergent time connects to a broader theme in modern theoretical physics, the idea that the fundamental description of reality may not use the concepts we are most familiar with. Space, time, particles, and fields may all be emergent, approximate descriptions that apply in certain regimes and break down in others. The more fundamental description may use different mathematical structures that do not have straightforward interpretations in terms of the concepts of our everyday experience. This idea appears most powerfully in the framework called holography, which has emerged from string theory and has become one of the most active areas of research in theoretical physics. The holographic principle, motivated by the work of Jacob Bekenstein, Stephen Hawking, Gerard 't Hooft, and Leonard Susskind in the 1970s and 1990s, proposes that the information content of a region of space is not proportional to its volume, but to its surface area. The interior of a region, in some sense, is encoded on its boundary. The most concrete realization of this principle is the anti-de Sitter conformal field theory correspondence, or AD-SCFT, discovered by Juan Maldacena in 1997. This is a mathematical equivalence between two very different-looking theories. On one side is a theory of quantum gravity in a spacetime with a specific geometry called anti-de Sitter space, a negatively curved spacetime. On the other side is an ordinary quantum field theory without gravity living on the boundary of that spacetime, one dimension lower. The equivalence is remarkable because the two theories are completely different in their apparent content. One has gravity and one does not. One lives in a higher dimension and one in a lower dimension. Yet they are mathematically equivalent in the sense that any calculation in one theory has a corresponding calculation in the other, and the results match. This is not an approximation or an analogy. It is an exact equivalence between two theories. What AD-SCFT implies for the nature of space, time, and gravity is profound. Space and time in the gravitational theory emerge from the quantum field theory on the boundary. They are not fundamental, they are derived. The gravitational bulk space, including its geometry and its dynamics, including the dynamics of objects moving through it, is encoded in correlations and quantum information in the boundary theory. Spacetime is constructed from quantum entanglement. This has been demonstrated in specific calculations. The geometry of space in the bulk theory is related to the pattern of quantum entanglement in the boundary theory. Regions that are highly entangled in the boundary theory correspond to regions of space that are connected in the bulk. Regions that are less entangled correspond to regions that are more distant. Spacetime connectivity, the sense in which nearby regions of space are neighbors, emerges from the entanglement structure of the quantum state. If space emerges from entanglement in this way, then time might as well. The dynamics of the boundary theory, the way quantum states evolve over time in the boundary theory, corresponds to the dynamics of the bulk spacetime, including the propagation of fields and particles through it. The time of the boundary theory is not the same as the time of the bulk gravity theory. They are related but distinct, and the bulk time is in some sense derived from the boundary dynamics. This is a stunning inversion of the usual picture. Instead of quantum fields living in a fixed spacetime emerges from quantum fields. The geometric concepts we use to describe gravity, the curvature of space, the flow of time, the structure of horizons and singularities, are all derived from a more fundamental description in terms of quantum information and quantum entanglement. What does this imply for the Big Bang singularity? In the AD-SCFT framework, singularities in the bulk spacetime correspond to specific features of the quantum state on the boundary. A singularity is not a physical point where density is infinite and physics breaks down. It is a feature of a specific quantum state that in the dual description looks like a singularity when you try to describe it in terms of smooth spacetime geometry. In the boundary theory, there is no breakdown. The quantum state is well defined. The singularity is a limitation of the geometric description, not a limitation of physics. This suggests that the Big Bang singularity might be resolved in a similar way in a fully developed theory of quantum gravity based on holographic principles. Instead of a genuine physical breakdown, the singularity might be a limitation of the classical geometric description that quantum gravity replaces with a smoother, more complete account. The universe at the beginning is not a point of infinite density where physics stops. It is a state of maximum quantum entanglement, or some other quantum gravitational configuration, that the classical geometric language cannot adequately describe. The boundary theory in AD-SCFT does not have a singularity. It is a well-defined quantum field theory at all times, evolving smoothly according to its equations. The singularity exists only in the bulk gravitational description, which is an approximate description valid when the quantum state has a classical geometric analog. When that approximation breaks down, when the quantum state is such that no smooth geometry corresponds to it, the geometric description fails and is replaced by the more fundamental boundary description. Applying this logic to cosmology requires care, because the universe we live in is not anti de Sitter space. Our universe has positive cosmological constant, corresponding to de Sitter space, and the holographic principle for de Sitter space is far less well understood than for anti de Sitter space. The application of holographic ideas to cosmology is an active research area with significant technical challenges. But the conceptual lesson from AD-SCFT is clear. Spacetime, including its singularities, may not be fundamental, and a more complete description may resolve those singularities naturally without requiring the singularity to be a physical reality. Let us now think about what all of these ideas, quantum gravity, emergent time, holography, and the various proposals for the early universe, imply for the concept of nothing. Because this is what the whole investigation has been building. Not a final answer, but a precise characterization of what the question means and why it is so hard. The philosophical concept of nothing, absolute non-being, the complete absence of everything including laws and logic and possibility, is genuinely difficult to think about coherently. It is so extreme that it is not clear the concept is even well formed. If there are no laws, can anything happen? If there is no logic, can we even reason about the state? If there is no possibility, is there a difference between this nothing and the statement that it is impossible for anything to exist? Some philosophers have argued that the question of why there is something rather than nothing is itself confused. If nothing were the case, there would be no one to ask the question and nothing to answer it. The very act of posing the question presupposes a thinker, a language, a logical framework, and therefore something. The question may be self-defeating in a deep sense, not merely in the trivial sense that we exist and therefore something must exist, but in the deeper sense that the concept of nothing is incoherent from the standpoint of any coherent inquiry. This is not to say the question is uninteresting. It is to say that the question may need reformulation before it can be fruitfully pursued. The reformulated question might be, given that physical laws exist and that a quantum vacuum exists, why do they have the specific form they have? Or, is there any sense in which the laws and the vacuum are necessary rather than contingent? Or what is the minimum conceptual framework required to describe a state that gives rise to a universe like ours? These reformulations are more tractable than the original question, even if they are still very hard, and they connect to what physicists actually work on when they work on the problem of cosmic origins. They are asking why the quantum vacuum has the properties it has, why inflation occurred if it did, what determines the spectrum of the inflatton's potential, why the dimensionality of space is 3 rather than some other number, and what the correct theory of quantum gravity is. Each of these questions is specific, technical, and in principle answerable by a combination of theoretical reasoning and empirical evidence. None of them is the question of why there is something rather than nothing in the most absolute sense, but they are the questions that physics can actually make progress on, and making progress on them is what moves us closer to understanding the universe's origins, even if it does not reach the philosophical terminus. There is a concept in physics that comes closer than anything else to the idea of nothing that can do something, and it is the concept of the false vacuum. A vacuum, as we have discussed, is the lowest energy state of a quantum field, but the definition is local rather than global in an important sense. A vacuum is the lowest energy state within a particular configuration space, the space of field values accessible from the current state. It is possible for there to be a state that is locally minimal in energy, a dip in the energy landscape, but not globally minimal. There might be a deeper dip elsewhere in field space, connected to the current state by a path that goes uphill in energy before going down to the global minimum. Such a locally minimal but not globally minimal state is called a false vacuum. It is stable against small perturbations, because any small change increases the energy. But it is unstable against quantum tunneling, a quantum mechanical process by which a system transitions between states by tunneling through an energy barrier rather than going over it classically. Given enough time, a false vacuum will quantum tunnel to the true vacuum, the global energy minimum. The decay of a false vacuum is one of the most dramatic events that could occur in the cosmos. When a false vacuum decays, it does so by nucleating a bubble of true vacuum at some location. Inside the bubble, the field has transitioned to the lower energy state. The bubble then expands at close to the speed of light, converting the false vacuum to the true vacuum as it grows. Any observers inside the bubble would experience this as a dramatic change in the physical laws, because the properties of particles and forces depend on the vacuum state of the underlying fields. For cosmology, the false vacuum concept is central to inflationary models. The inflatoned field in many inflationary models starts in a state of high potential energy that is not the global minimum of the inflaton's potential. This is a kind of false vacuum, stable against small perturbations but not globally minimal. The energy stored in this state drives inflation. As the field slowly rolls toward the minimum of its potential, inflation gradually ends. When the field reaches its minimum and oscillates around it, it decays into particles and radiation, producing the hot Big Bang. Now consider what the false vacuum actually is. It is a state with high energy density distributed uniformly through space. It has no particles in the conventional sense, no radiation, no matter. It is, in some everyday sense, empty, yet it has energy, and that energy drives the dynamics of spacetime. The false vacuum is a kind of energetic nothingness, an emptiness that is full of potential in the most literal sense. This connects to the concept of the quantum vacuum fluctuation as the origin of the universe. In some models, the universe did not begin with a large false vacuum that then slowly rolled to its minimum. Instead, a small patch of false vacuum appeared via quantum fluctuation from a state that was even more vacuum-like, a state of even lower energy, and then inflation took over and expanded that small patch into a full universe. The quantum fluctuation that started the process was, in this picture, as close to nothing as physics can describe, while still being something governed by quantum mechanical laws. The language here is seductive but must be handled carefully. A quantum fluctuation from the vacuum is not a fluctuation from nothing. It is a fluctuation of a quantum field from its vacuum state. The field exists. The vacuum state exists. The quantum mechanical laws that govern the fluctuation exist. The fluctuation is a change in the state of something that already exists, not the spontaneous appearance of something from absolute non-being. This distinction is sometimes blurred in popular accounts by the observation that the energy of the universe might sum to zero. The positive energy of matter and radiation and the negative energy of gravity might cancel exactly, making the universe a zero-energy system that could arise from a zero-energy vacuum without violating conservation of energy. This is an interesting observation, and it has been made seriously by physicists including Alan Guth, one of the founders of inflationary theory. But even a zero-energy system is not nothing. Zero energy is a property of something. A universe with total energy zero is not the same as a universe that does not exist. The quantity of energy is one property among many that a physical system has. Setting that one property to zero does not eliminate all the other properties. The universe still has spatial extent, temporal duration, quantum fields, laws, and structure. It is a very particular kind of something with total energy zero, not a conversion of nothing into something. Now let us think about a question that is rarely asked clearly in popular accounts, but that is essential to the whole investigation. When we ask why the universe exists rather than nothing, what kind of answer are we looking for? In everyday explanations, we typically explain things by reference to prior causes. The vase broke because it fell. It fell because the table was bumped. The table was bumped because someone walked into it. This chain of explanation goes backward in time, connecting later events to earlier ones through causal relationships. The explanation is satisfying because it embeds the event to be explained into a causal structure that we understand. But this kind of explanation requires a temporal framework. It requires that the event to be explained has a before, a time in which a cause could operate. If the universe's existence includes time itself, if time is part of what needs to be explained, then a causal explanation of the universe's existence cannot use a temporal framework, because the temporal framework is what is being explained. The explanation would be circular. The universe exists because of causes that operated before the universe existed, but before the universe existed, there was no time in which causes could operate. This circularity suggests that the kind of explanation we are looking for must be different from ordinary causal explanation. It cannot be a story of what happened before. It must be some other kind of account. What other kinds of explanation are there? One option is what philosophers call a sufficient reason. There is a deeper description of reality from which the universe's existence necessarily follows. The universe exists because it has to, because the deeper structure of mathematics or logic or possibility demands it. If this is the right kind of explanation, then the question becomes, is there a mathematical or logical structure from which the existence of a universe like ours follows necessarily? Some physicists and philosophers have pursued this idea seriously. Max Tegmark's mathematical universe hypothesis proposes that all mathematically consistent structures exist as physical realities, and our universe is one of them. We observe this universe rather than others, because only certain universes contain observers capable of asking why the universe exists. The universe's existence needs no further explanation because all possible universes exist, and existence is the default state of mathematical structures rather than an exception that requires justification. This is a bold and provocative idea. It has the virtue of taking the question seriously and proposing an answer that, in principle, could be tested indirectly by examining the predictions it makes about which kind of universe we should find ourselves in. But it also has deep problems. The claim that all mathematical structures physically exist is itself in need of justification. Why should mathematical existence and physical existence be the same thing? What does it even mean for a mathematical structure to physically exist? These questions are not obviously easier than the original question of why there is something rather than nothing. Another option is what might be called the anthropic terminus. The question of why the universe exists has no answer, not because the answer is unknown, but because existence is simply a given. The laws of physics describe how the universe evolves and what properties it has. They do not explain why it exists rather than not existing. Existence is not itself a property that can be explained by physics. It is the precondition for physics. To ask why the universe exists is to ask physics to explain its own precondition, which it cannot do any more than a dictionary can define itself. In this view, the question of why there is something rather than nothing is not a deep physical question waiting for a deep physical answer. It is a question that reaches the absolute limit of what explanation can mean. It is not unanswerable because of ignorance. It is unanswerable in principle, because the form of the question asks for something that no answer can provide. This might seem like a defeat, but it is not. Understanding why a question cannot be answered in a particular way is genuine progress. If the question of cosmic origins cannot be answered by finding a prior cause, because that would require a prior time, and cannot be answered by a sufficient reason from mathematics, because mathematical existence and physical existence may not be the same, then we have significantly narrowed the space of possible answers. We have shown that any genuine answer, if one exists, must be of a different kind from anything we currently understand. That is not nothing. It is a map of our ignorance that is precise enough to guide where we should look next. The relationship between mathematics and physical reality is one of the deepest and least resolved questions in the philosophy of physics, and it cannot be avoided in any serious discussion of cosmic origins. The unreasonable effectiveness of mathematics in describing the physical world, as Eugene Wigner famously called it, is genuinely puzzling. The laws of physics are written in the language of mathematics with extraordinary precision and power. General relativity is a theory about the geometry of a four-dimensional pseudo-Riemannian manifold. Quantum mechanics is built on Hilbert spaces and self-adjoint operators. The standard model of particle physics is based on a gauge theory with a specific symmetry group. These are not approximate descriptions or useful metaphors. They are precise mathematical structures that make exact predictions confirmed to many decimal places. Why should this be? Why should the universe be mathematical? Why should the abstract structures that mathematicians develop, often with no thought of physical application, turn out to describe physical reality with such accuracy. The history of physics is full of cases where mathematics developed for purely abstract reasons turned out to be exactly what was needed to describe newly discovered physical phenomena. Complex numbers, developed to solve polynomial equations, turned out to be essential in quantum mechanics. Non-Euclidean geometry, developed as a mathematical curiosity, turned out to describe the geometry of spacetime in general relativity. Lie groups, developed by mathematicians in the 19th century, turned out to be the language of particle physics symmetries. One response is that mathematics is simply the language that humans use to describe precise relationships, and the universe has precise relationships, so of course mathematics describes them. On this view, the effectiveness of mathematics is not surprising, because mathematics is whatever kind of precise formal language turns out to be needed. Different universes with different laws would be described by different mathematics. The specific mathematics needed is determined by the specific laws that happen to hold, and we develop the mathematics to fit the laws we observe. Another response, closer to Tegmark's view, is that mathematics is not a human-invented language, but a structure that has independent existence. Physical reality is a mathematical structure, and the reason physical laws are mathematical is that they are, at the most fundamental level, mathematical relationships. On this view, the question of why the laws are what they are might have an answer in terms of which mathematical structures are most natural or fundamental, though what natural or fundamental mean in this context is itself unclear. A third response is that we simply do not know why mathematics is effective, and we should be honest about that. The unreasonable effectiveness of mathematics is one of the genuine deep mysteries at the intersection of physics and philosophy, and we should not pretend we have resolved it when we have not. It is a clue that points in the direction of a deeper understanding that we have not yet reached. What is clear is that any serious proposal about cosmic origins must grapple with the role of mathematics. Every physical theory is a mathematical structure. Every proposed mechanism for cosmic origin, whether quantum fluctuation, inflationary tunneling, cyclic bounce, or no-boundary geometry, is expressed in mathematical terms. The mathematics is not decoration. It is the substance of the proposal, and the success or failure of the proposal is judged by whether the mathematical structure makes correct predictions about observable quantities. This means that even the most radical proposals about cosmic origins are not proposals about absolute nothing. They are proposals about specific mathematical structures, about which structures describe the physical world and which physical processes follow from those structures. The structures themselves are presupposed. Their existence, whether in some Platonic sense or as contingent physical facts, is not explained by the proposals. It is assumed. The deepest question, then, is not which mathematical structure describes cosmic origins. It is why there are any mathematical structures at all, and why some of them correspond to physical reality. This question reaches a level of abstraction that current physics cannot address. It may require new conceptual tools that we have not yet developed. It may require a revision of what we mean by existence, by physical reality, and by mathematical truth. Or it may turn out to be a question that simply has no answer in any framework we can build. Let us turn to a different angle on the same set of problems, one that is more concrete and more directly connected to the observations we have discussed. The question of fine-tuning and the anthropic principle, which we touched on earlier, deserves deeper examination because it connects the abstract question of why there is something to the specific question of why the something that exists has the particular properties it has. The universe has specific physical laws with specific constants. The speed of light has a specific value. The electron has a specific mass and charge. The strength of the strong nuclear force has a specific value. The cosmological constant has a specific value. The proton-to-electron mass ratio has a specific value. These constants are not derived from any deeper theory. They are measured empirically and then inserted into the equations. The equations correctly predict the outcomes of experiments, but they do not explain why the constants have the values they do. Several of these constants appear to be extraordinarily fine-tuned in the sense that small changes in their values would produce a universe radically different from our own, often in ways that would prevent the formation of complex structures, including stars, planets, and life. The most famous example is the cosmological constant, which appears in the equations of general relativity as a constant energy density of the vacuum. Its observed value is about 10 to the negative 123 in natural units, a number so close to zero that it seems extraordinary that it is not exactly zero, and yet so far from the theoretically expected value that it is equally extraordinary that it is as large as it is. If the cosmological constant were much larger, the universe would have expanded so rapidly that no structures could have formed. If it were much more negative, the universe would have collapsed before stars and galaxies could develop. The observed value is in the narrow range that allows the universe to evolve complex structure over billions of years. The same kind of fine-tuning argument applies to the strength of gravity, the masses of the quarks, the strength of the strong nuclear force, and several other fundamental parameters. Whether this fine-tuning is genuinely remarkable or whether it is an artifact of our failure to understand the underlying theory is debated. Some physicists argue that the fine-tuning reveals that there is a deeper theory yet to be discovered that will explain the values of the constants, possibly even showing that they could not have been otherwise. Others argue that the fine-tuning is evidence for a multiverse, where many values of the constants are realized in different regions, and we find ourselves in a region where the constants permit our existence because we could not exist elsewhere. The anthropic principle, as noted earlier, makes the observation that our existence as observers is itself a constraint on what we can observe. We can only observe a universe in which observers can exist. If the constants had values that prevented the formation of stars or atoms or chemistry, there would be no one to observe those constants. The fact that we observe fine-tuned constants is therefore not surprising, given that we exist, even if it would be extraordinary in the absence of an anthropic selection effect. The problem with this argument, applied naively, is that it is consistent with any observation. Whatever constants we observe, we can say they must be compatible with our existence because we. This makes the argument unfalsifiable, which is generally a sign that it is not doing real explanatory work. The anthropic principle explains why we observe what we observe, but it does not explain why the constants have specific values rather than a continuous range of values, and it does not explain why there is a universe at all. The multiverse strengthens the anthropic argument by providing a mechanism. If there are genuinely many universes with different constants, then the anthropic selection has a physical basis. We are not just noting that we must find ourselves in a compatible universe. We are proposing a specific physical process that produces many universes with different constants, and within that ensemble, anthropic selection explains why we observe the particular constants we do. But the multiverse itself requires physical mechanisms and physical laws to produce and maintain it. The inflationary multiverse, for example, is produced by a quantum field with a specific potential energy landscape that allows different regions to tunnel to different vacuum states. That field, that landscape, and those tunneling rates are all described by physical laws. The multiverse does not explain the physical laws, it presupposes them. It shifts the question from why do the constants have these values to why does the inflaton potential have the specific shape that allows eternal inflation to produce a vast ensemble of universes with different vacuum energies. This is not obviously a simpler or more fundamental question. The honest position on fine-tuning is that we do not know whether it has a physical explanation, an anthropic explanation, no explanation at all, or some combination. It is a genuine puzzle that points toward a gap in our understanding, but it is a gap that we cannot yet clearly see across. The gap may be filled by a deeper theory that explains the constants. It may be filled by a better understanding of the multiverse and its physical basis. It may turn out that the fine-tuning is less extreme than it appears because some of the apparent sensitivity is an artifact of holding other parameters fixed while varying one, or it may genuinely be a brute fact about our universe that admits no further explanation. Now let us address a question that has been lurking beneath the surface of the entire investigation. What would count as an answer to the question of why there is something rather than nothing? What kind of evidence, what kind of theoretical structure, what kind of argument would satisfy us that the question has been answered? This is a question about the standards for explanation, and it matters enormously because without it, we cannot distinguish a real answer from a story. Any proposal for the origin of the universe will be assessed against some standard, and different people have different standards. Some will be satisfied by a quantum mechanical story that shows how a universe could arise from a vacuum state. Others will insist that the vacuum state itself needs to be explained. Some will accept a mathematical necessity argument. Others will demand a physical mechanism. The standards we use to evaluate explanations are themselves a subject of inquiry, not a given. In ordinary science, the standard is predictive success. A theory is good if it makes predictions that are confirmed by observation, and if those predictions are specific enough to be falsifiable. This standard works well for theories that describe phenomena within the universe. It is less clearly applicable to theories about the origin or totality of the universe, because the universe is not just another phenomenon that can be observed from outside. When we try to explain the origin of the universe, we are in the unusual position of trying to explain the existence of the system within which all our observations are made. This is not impossible in principle, but it is methodologically challenging. Any observation we make is made from within the universe. Any evidence we gather about the universe's origin comes to us through the universe's history. We cannot stand outside the universe and observe its creation. This does not mean the question is unanswerable. It means we need to be creative about what counts as evidence for theories of cosmic origin. And physicists have been creative. The CMB provides evidence about the initial conditions of the universe that any theory of its origin must reproduce. The primordial element abundances do the same. The flatness of the universe constrains the mechanism that set the initial conditions. The scale invariance of the primordial fluctuation spectrum constrains the physical process that generated them. These are indirect evidences about the origin, filtered through 8 billion years of cosmic evolution, but they are genuine evidences. Future observations could provide even more direct evidence. Detection of primordial gravitational waves in the CMB polarization would be powerful evidence for inflation at a specific energy scale. A non-detection, pushing the upper limit below the predictions of the simplest inflationary models, would significantly constrain or challenge those models. Specific signatures in the CMB, such as particular patterns of non-Gaussianity or specific features in the power spectrum, could discriminate between inflationary models, cyclic models, and other proposals for the early universe. These are real tests with real discriminating power, and they are being pursued with real instruments. The science of cosmic origins is not mere speculation. It is an active research program constrained by data and capable of making and testing predictions. The data so far are consistent with inflationary cosmology and inconsistent with some alternatives. More data will sharpen these conclusions. But the ultimate question, why there is anything at all, is almost certainly beyond direct empirical test. No observation can tell us why the laws of physics are what they are, or why any laws exist at all. This is not a limitation of our current technology. It is a limitation of the kind of question it is. It asks for an explanation of the framework within which empirical tests are possible, and no empirical test can reach outside that framework. This means the deepest version of the question of cosmic origins is genuinely philosophical as well as scientific. It requires not just better data and better theories, but better concepts, better understanding of what explanation means, better clarity about the relationship between mathematical structures and physical reality, and perhaps genuinely new ideas that have not yet been thought. The boundary between physics and philosophy is not a clear line here. It is a gradient with firmly empirical questions at one end and firmly conceptual questions at the other, and most of the interesting territory in the middle where science and philosophy must work together. There is one more concept that deserves careful attention in this deep dive into the nature of nothing and origins, the concept of causality itself. We typically explain events by reference to their causes. The universe exists because something caused it to exist, or it existed uncaused. These seem like the only options. Either there is a cause for the universe's existence, or the universe is an uncaused brute fact. But causality, like time, is not a fundamental feature of reality that all physical theories must presuppose. It is a concept that works well in classical physics and in everyday experience, and that may break down at the quantum level and certainly breaks down in the ways we expect in extreme regimes. Causality, as we normally understand, it requires a temporal framework. A cause precedes its effect in time. If time is part of what needs to be explained, then causality in its ordinary sense cannot be the right concept to apply to the universe's origin. Quantum mechanics already complicates causality. In quantum mechanics, outcomes are probabilistic rather than determined by prior causes in the classical sense. The measurement of a quantum system does not have a classical cause in the sense that the prior state of the system uniquely determines the outcome. The prior state determines only probabilities. Whether a specific outcome occurs is, in some interpretations, genuinely indeterministic. The outcome happens, but there is no prior fact that caused this specific outcome rather than another. This is not a violation of causality in the sense of effects preceding causes. Events still happen in a temporal sequence in quantum mechanics. But it is a weakening of the classical concept of causality in the sense that prior states do not uniquely determine later states. There is irreducible randomness. In quantum field theory, the vacuum decays by producing particle-antiparticle pairs without any prior classical cause. The decay happens because quantum mechanics permits it, not because a prior event triggered it. In quantum gravity, causality may break down even more fundamentally. If spacetime is not fundamental, if it is emergent, then the causal structure of spacetime, which specifies which events can influence which others, is itself emergent. In the fundamental description, there may be no well-defined causal order. The concept of cause and effect, which presupposes a temporal order, may not apply at the most fundamental level. This is deeply counterintuitive. We are accustomed to thinking of causality as one of the most fundamental aspects of reality, but that intuition is formed by experience in a regime where classical spacetime provides a well-defined causal structure. In the extreme regime of quantum gravity, that causal structure may not be given. It may have to be constructed from more fundamental elements, just as time itself may have to be constructed. If causality is not fundamental, then the question of what caused the universe to exist may be as malformed as the question of what came before time began. It may be asking for a causal account in a regime where causality does not apply. The universe may exist not because something caused it to exist, but because the most fundamental description of reality, whatever it turns out to be, simply is as it is, and from that description the appearance of a causal history emerges as an approximation valid in certain regimes. This is a radical possibility, but it is consistent with the direction in which fundamental physics has been moving for over a century. Every time we have pushed to a more fundamental level of description, familiar concepts have turned out to be approximate and emergent. Newtonian mechanics gave way to quantum mechanics, where classical trajectories became probability amplitudes. Classical spacetime gave way to general relativity, where the geometry of space and time became dynamical. If the pattern continues, and there is no guarantee that it does, the next step may show that causality itself is emergent, a feature of the approximate description but not of the fundamental one. Let us now step back from the technical details and think about what kind of intellectual posture serves us best in the face of these questions. This is not a retreat from rigor. It is a recognition that rigor requires not just mathematical precision, but also clarity about what we know, what we infer, what we assume, and what we merely hope. The temptation in cosmology, as in all areas where the questions are profound and the audience is large, is to reach for certainty that the evidence does not support. To say the universe came from nothing because it sounds dramatic and simple. To say the multiverse is confirmed because inflation is well motivated. To say quantum gravity solves the singularity because we expect it to. These overclaims are understandable because the true state of affairs is complicated and the true uncertainties are uncomfortable. But overclaiming does not serve the science or the public. It creates a false impression of understanding that makes genuine understanding harder to achieve. The opposite temptation is to retreat into excessive skepticism. To say we know nothing about cosmic origins because the earliest moments are beyond our observational horizon. To dismiss theoretical proposals as mere speculation because they have not been confirmed. To refuse to engage with ideas that are not yet testable because testability is the only criterion that matters. This excessive skepticism is also wrong because it fails to recognize the genuine progress that has been made and the genuine constraints that theory and observation impose even in the absence of direct confirmation. The right posture is what might be called disciplined engagement. Take the questions seriously. Follow the evidence carefully. Engage with the theoretical proposals honestly, evaluating their strengths and weaknesses without either dismissing them because they are speculative or accepting them because they are elegant. Keep track of where you are on the ladder from observation to speculation. And remain genuinely open to the possibility that the questions may need to be reformulated as much as answered. Disciplined engagement means being willing to say that inflation is well motivated and consistent with observations but not confirmed, that the multiverse is a genuine possibility but not established, that quantum gravity is expected to resolve the singularity but we do not know how, and that the question of why there is something rather than nothing may be beyond the reach of physical explanation as we currently understand it. These are not satisfying stopping points. They do not give us the closure that a complete story provides, but they are honest, and honesty is what keeps the inquiry on track. The history of science is full of cases where prematurely accepted answers turned out to be wrong, and where the questions that seemed settled turned out to be open. The history of cosmology especially is a story of continual revision and refinement, of confident claims that had to be updated as new data arrived and new theories were developed. The universe is under no obligation to be simple. It is under no obligation to provide answers that fit human intuitions. It has been structured, as far as we can tell, according to mathematical laws that we can discover and understand, which is itself extraordinary and not at all guaranteed. But those laws operate in ways that often violate the intuitions we developed in a world of everyday objects and human-scale events. Expecting the origin of the universe to be comprehensible in terms of everyday concepts is expecting more than we have any right to expect. What we have built over the course of this investigation is not an answer to the question of cosmic origins. It is something more valuable than a premature answer, a precise map of what we know, what we do not know, and what we need to find out. We know the universe has been expanding and cooling from a hot, dense early state for about 13.8 billion years, confirmed by multiple independent observations. We know the earliest light we can directly observe was released at recombination, about 380,000 years into that history, and we have mapped that light in extraordinary detail. We know the pattern of that light is consistent with inflation having set the initial conditions of the universe, though inflation is not confirmed. We know that classical general relativity predicts a singularity at the beginning of the hot dense phase, and that this singularity is a breakdown of the classical description rather than a confirmed physical event. We know that quantum gravity should resolve this breakdown, but we do not have a complete theory of quantum gravity. We have candidate theories. Loop quantum cosmology replaces the singularity with a bounce. String cosmology provides a rich landscape of possibilities for the pre-Big Bang era. The no-boundary proposal dissolves the singularity by changing what time means near the beginning. Cyclic models replace the beginning with a previous cycle. Each of these makes different predictions and has different strengths and weaknesses. None is confirmed. We know that the quantum vacuum is not nothing. It is a structured physical state with energy, fields, and fluctuations. We know that time may be emergent rather than fundamental, and that the concept of before may not apply in the regime where quantum gravity is essential. We know that causality may be an emergent concept as well, applicable in classical spacetime, but not at the most fundamental level. We do not know what, if anything, preceded the classical Big Bang in any physical sense. We do not know whether time had a beginning, whether it is emergent, or whether it has always existed in some form. We do not know whether the universe is part of a larger multiverse, whether it is the result of a quantum fluctuation from a more fundamental vacuum, or whether it arises from a more basic description in which space and time and matter all emerge together. We do not know why the physical laws are what they are, or why any laws exist at all. These are not small gaps. They are large, central, fundamental gaps in our understanding of the deepest aspects of reality. And filling them will require not just more data, though more data will help, and not just more powerful theories, though more powerful theories are needed. It will require new concepts, new ways of thinking about space and time and causality and existence that we have not yet developed. The mystery at the beginning of everything is real. It is not a mystery that ignorance has manufactured or that comfort requires. It is a mystery that knowledge has revealed by pushing far enough back in cosmic history to reach the limit of our current frameworks and to see with some precision what lies beyond those frameworks and what kind of thinking would be needed to go further. This is the state of the art. This is where the science actually stands. And standing here with honest eyes and disciplined engagement is not a failure. It is the right place to be while the work continues. The work that continues is genuinely exciting. The next generation of CMB experiments is being designed to search for primordial gravitational waves with sensitivity that will decisively test a wide range of inflationary models. Gravitational wave detectors are being extended to lower frequencies that could, in principle, detect relic gravitational wave backgrounds from early universe processes. Pulsar timing arrays are accumulating evidence of a gravitational wave background at very low frequencies whose origin is not yet clear. Large-scale galaxy surveys are measuring the distribution of matter across cosmic time with ever-increasing precision, testing the growth of structure that inflation predicts. Particle colliders are pushing to higher energies, probing the physics of fields and interactions at scales closer to those relevant for the early universe. None of these experiments will directly observe the Big Bang singularity or what preceded it. The observational horizon is fixed by the opacity of the early plasma. But each of them can constrain theories of the early universe by measuring quantities that those theories predict, and by ruling out or supporting specific mechanisms for generating the universe's initial conditions. On the theoretical side, the development of quantum gravity continues along multiple fronts. Loop quantum gravity is being extended and refined. String theory continues to produce new insights, particularly through AD-SCFT and related holographic frameworks. Attempts to understand the emergence of spacetime from quantum information are producing new mathematical tools and new conceptual frameworks. The problem of time in quantum gravity is being attacked from multiple angles. Each advance is incremental, but incremental advances in understanding can accumulate into conceptual revolutions over the course of decades. The question of why there is something rather than nothing will not be answered by any single experiment or any single theoretical breakthrough. It may never be answered in the absolute philosophical sense, but it is being narrowed, refined, and clarified. Each advance in our understanding of the early universe, each new measurement that constrains the initial conditions, each new theoretical framework that handles the singularity differently, each new conceptual tool for thinking about emergent time and emergent space, moves us closer to understanding what the question really means and what kind of answer could possibly satisfy it. That is the adventure. Not the pretense of a final answer, but the genuine, ongoing, methodical, beautifully disciplined work of figuring out what the universe is, how it works, and where it came from. The universe has been kind enough to leave us evidence of its early history. It has been organized according to mathematical laws that our minds can grasp, at least partially. It has been persistent enough to still carry the light and the relics and the structures that encode its past. We owe it the respect of taking its evidence seriously, following it wherever it leads, and being honest about where it stops. The universe at its beginning remains a mystery, not a vague romantic mystery, but a specific, technically defined, precisely located mystery that science is actively working to resolve. The boundary of knowledge is not a comfortable place to rest. But it is the only honest place to stand when the question is as deep as this one, and the question is as deep as any question can be. Why is there something rather than nothing? Why is there a universe at all? Why does it have a history that includes the kind of complexity that can ask about its own origins? We do not know, but we know better than ever before what we do not know, and knowing that precisely and honestly is the beginning of knowing more. We have mapped the territory of cosmic knowledge with care, traced the evidence to its limits, surveyed the theoretical proposals that reach beyond those limits, and been honest about the distance between what we know and what we merely hope. Now we go to the places that the previous parts have prepared us to enter. We go into the specific physical ideas that are most actively being developed, most seriously being debated, and most likely to shape the next chapter of our understanding. We go into the details that popular accounts almost always simplify past the point of usefulness, and we do so because the details are where the real insight lives. The first detail worth inhabiting fully is the inflationary story itself, because inflation is the cornerstone of modern early universe cosmology, and because its implications are far stranger and far more profound than most accounts convey. Inflation is not just a mechanism for solving the horizon and flatness problems. It is a proposal about the nature of the universe at the most fundamental level, a proposal that, if correct, changes what we mean by the universe itself. Alan Guth proposed the basic idea of inflation in 1980, building on earlier work by Alexei Starobinsky. The proposal was motivated directly by the puzzles we have discussed: the horizon problem, the flatness problem, and the origin of the magnetic monopoles that grand unified theories predicted should be abundant in the early universe but are not observed. Guth showed that a brief period of exponential expansion, driven by the energy of a field stuck in a false vacuum state, could solve all three problems simultaneously. The original version of inflation, now called old inflation, had a problem. The false vacuum decays by nucleating bubbles of true vacuum, and for inflation to work, those bubbles need to collide and merge, releasing their energy into the hot Big Bang. But Guth's model produced an inhomogeneous universe because the bubbles could not merge efficiently enough before inflation ended in any given region. The graceful exit problem, as it came to be called, was a serious flaw. New inflation, developed by Andre Linde and independently by Andreas Albrecht and Paul Steinhardt in 1982, solved the graceful exit problem by changing the mechanism. Instead of a field tunneling from a false vacuum to a true vacuum through bubble nucleation, the inflattened field rolls slowly down a gentle slope of its potential energy landscape. During the slow roll, the universe inflates. When the field reaches the bottom of its potential and oscillates, it decays into particles and reheats the universe. The transition from inflation to the hot Big Bang is smooth and complete, producing a homogeneous universe. Chaotic inflation, proposed by Andre Linde in 1983, generalized the picture further. Instead of requiring a very special initial configuration, where the field starts near the top of a potential hill, chaotic inflation starts from a random distribution of field values. In a large enough region of space, some locations will have the field at a value suitable for inflation to begin. Those locations will inflate and dominate the volume of the universe. The initial conditions do not need to be specially prepared. Inflation selects for itself from generic initial conditions. This is an important conceptual shift. Earlier versions of inflation required explaining why the universe started in a special configuration that allowed inflation to begin. Chaotic inflation argues that if you start with a large enough region with random initial conditions, inflation is essentially guaranteed to begin somewhere, and once it begins, it dominates. The specialness of the initial conditions is replaced by a selection argument. we observe an inflated universe because we live in a region where inflation happened. The chaotic inflation picture leads naturally to eternal inflation. Once inflation begins in some region, quantum fluctuations in the inflated field mean that in some subregions, the field fluctuates up the potential rather than rolling down. Those subregions have more inflation rather than less. They expand faster, they dominate the volume. The overall volume of the inflating region grows without bound even as individual subregions exit inflation and produce hot big bangs. Inflation, once started, never ends globally. It keeps producing new regions, each of which becomes a potential new universe after inflation ends locally. The picture that emerges from eternal inflation is of a vast, potentially infinite, self-reproducing cosmos. Different regions exit inflation at different times and with different field configurations, depending on which vacuum state the inflaton ends up in. If the potential energy landscape has many different minima, different regions can end up in different vacua, with different values of the physical constants, different numbers of large spatial dimensions, different particle content, and different laws of physics in the effective sense that the constants and symmetries of the effective low-energy theory differ from region to region. This is the string theory landscape combined with eternal inflation, and it is one of the most controversial and most discussed ideas in modern cosmology. The landscape of string theory, the enormous collection of possible vacuum states that string theory allows, could contain anywhere from 10 to the 100 to 10 to the 500 different vacua, each corresponding to a different set of effective physical laws. Eternal inflation could realize all or many of these vacua in different regions of a larger cosmos. Our observable universe, with its specific constants and laws, would be one bubble among an enormous number of others, selected by the fact that its particular constants are compatible with our existence. The landscape multiverse is both deeply compelling and deeply problematic. It is compelling because it potentially explains fine-tuning through anthropic selection in a physical framework rather than just a philosophical observation. It is problematic because it is almost impossible to make precise predictions within it, because the space of possibilities is so vast that almost any observation can be accommodated somewhere in the landscape, and because it relies on theoretical structures, string theory and eternal inflation, that are themselves not confirmed. The most serious scientific criticism of the landscape multiverse is the measure problem. To make probabilistic predictions within the multiverse, you need a way to assign probabilities to different regions or different observations. In an infinite multiverse with infinitely many regions of every type, naive counting does not work because infinity divided by infinity is undefined. You need a measure, a way of weighting different possibilities, and different choices of measure give dramatically different predictions. The measure problem has not been solved, and without solving it, the landscape multiverse cannot make precise predictions that could be tested. This does not mean the landscape multiverse is wrong. It means it is incomplete as a scientific theory. The idea is physically motivated and mathematically grounded in string theory, which is itself a substantial theoretical framework. But until the measure problem is solved, or until some other way of making predictions within the landscape is found, the landscape multiverse remains in the category of well-motivated theoretical proposal rather than testable scientific theory. The multiverse idea appears in several different forms that are often conflated, and it is worth distinguishing them carefully because they have very different physical bases and very different levels of theoretical support. The simplest form of the multiverse is simply the rest of the universe beyond our observable horizon. Our observable universe is the region from which light has had time to reach us since the Big Bang. Beyond that horizon, there is in principle more universe, with the same laws and constants as our own, but with different specific conditions, because it began with different random fluctuations in density. This is not speculative in any meaningful sense. It is the straightforward implication of standard cosmology applied to a sufficiently large universe. If inflation happened, and the universe is much larger than the observable portion, then there is more universe beyond our horizon. This is sometimes called the level I multiverse. The level II multiverse is the eternal inflation landscape, where different regions beyond our horizon have ended up in different vacuum states and have genuinely different physical constants and laws. This is speculative but physically motivated. It requires both eternal inflation, which is a well-motivated but unconfirmed extension of inflationary theory, and a landscape of different vacuum states, which string theory suggests may exist. The level III multiverse comes from the many worlds interpretation of quantum mechanics, in which every quantum measurement leads to a branching of the universe into multiple branches, each corresponding to a different measurement outcome. On this interpretation, All possible quantum outcomes are realized in different branches, and the multiplicity of branches constitutes a multiverse. This is a proposed interpretation of quantum mechanics, not an additional physical theory on top of standard quantum mechanics, and whether it is the right interpretation is debated among physicists and philosophers. The level IV multiverse is Tegmark's mathematical universe hypothesis, where all mathematically consistent structures exist as physical realities. This is the most speculative and most philosophical of the multiverse proposals. It rests on the philosophical position that mathematical existence and physical existence are the same, which is a claim that goes well beyond anything physics itself can establish. These four forms of the multiverse are very different in their theoretical basis and in the degree to which they are connected to confirmed physics. Level I is essentially certain given standard cosmology. Level II is possible if eternal inflation and the string landscape are correct. Level III depends on an interpretation of quantum mechanics that is debated. Level IV is a philosophical position that makes it difficult to assess scientifically. Treating them as equivalent, as popular accounts often do, is misleading. For the question of cosmic origins, the relevant multiverse is level II, the eternal inflation landscape, and the relevant question is whether it genuinely addresses the question of why the universe exists or merely pushes it back. The answer, as we have noted, is that it pushes it back. The eternal inflation landscape does not explain why the laws of quantum mechanics and general relativity exist. It does not explain why there is an inflated field with a specific potential landscape. It assumes these things and then derives the ensemble of universes from them. The question of why the fundamental laws are what they are remains open. Let us now go deeper into the specific physics of the quantum vacuum, because the details reveal something important that popular accounts almost universally miss. The quantum vacuum is not a single, simple thing. It is a rich, structured entity whose properties depend on the physical context and whose relationship to the concept of nothing is deeply non-trivial. In quantum field theory, every type of particle corresponds to a quantum field that pervades all of space. The electron field, the photon field, the quark fields, the gauge fields of the weak and strong forces, all of these fields are present everywhere at all times. Particles are not independent objects. They are excitations of these fields, like ripples on an ocean. The ocean is always there. The ripples are what we call particles. The vacuum state of a quantum field is the state with no excitations, the state of minimum energy. But as we have discussed, quantum mechanics forbids perfect stillness. Even in the vacuum, fields fluctuate. These fluctuations can be described in terms of virtual particles, particle-antiparticle pairs that appear and disappear on timescales consistent with the energy-time uncertainty relation. The more energetic the pair, the briefer its existence. But the concept of virtual particles must be handled carefully because it is often misunderstood. Virtual particles are not real particles that briefly pop into existence. They are a mathematical tool for organizing calculations in quantum field theory. When physicists calculate the probability of a physical process, they use a technique called perturbation theory, which involves summing over increasingly complex diagrams called Feynman diagrams. Each diagram represents a contribution to the probability amplitude, and some diagrams involve internal lines representing particles that are not in the initial or final state of the process. These internal lines are the virtual particles. Virtual particles are off-shell, meaning they do not satisfy the usual relationship between energy and momentum that real particles obey. They are mathematical artifacts of the perturbative expansion, not independently existing entities that you could in principle detect. The Casimir effect and the Lamb shift, which are often cited as evidence for virtual particles, are real effects, but they are evidence for quantum field fluctuations, not for virtual particles as literal objects. The effects can be calculated without any reference to virtual particles, using a different approach to the same quantum field theory. This matters for the discussion of cosmic origins, because the claim that the universe was created by a quantum fluctuation of the vacuum needs to be understood carefully. If it means a fluctuation of a quantum field from its vacuum state, that is a physical process that might be describable within quantum field theory combined with some quantum gravity framework. If it means the spontaneous appearance of something from absolute nothing, it is claiming something that quantum field theory does not actually support. The quantum field theory vacuum is not nothing. It is the ground state of a set of fields, and those fields are always there. The vacuum energy density is another concept that requires careful treatment. As noted earlier, every quantum field contributes a zero-point energy to the vacuum, and summing these contributions gives a formally infinite result. After renormalization, which subtracts the infinite contribution in a systematic way, you are left with a finite vacuum energy. But the value of this finite vacuum energy depends on the renormalization scheme, and different schemes give different answers. For most purposes in particle physics, the absolute value of the vacuum energy does not matter because only differences in energy between states are physically observable. But in general relativity, the absolute value of the vacuum energy does matter because all forms of energy contribute to the curvature of spacetime. This is the source of the cosmological constant problem. The vacuum energy predicted by particle physics, even after renormalization, is enormously larger than the observed dark energy density. The discrepancy is one of the deepest problems in all of physics. The vacuum energy from quantum field theory should be at the Planck scale or at the scale of the highest energy process in the Standard Model. The observed dark energy density is about 120 orders of magnitude smaller. This is not a small discrepancy. It is the largest discrepancy between theory and observation in the history of physics. Several approaches to the cosmological constant problem have been proposed. Some invoke a symmetry that sets the vacuum energy to exactly zero, and then argue that dark energy is something else on top of that zero. Supersymmetry, which pairs each fermion with a boson, cancels the vacuum energy contributions of fermions against those of bosons. But supersymmetry must be broken in our universe because we do not observe the required boson partners of known fermions, and the breaking of supersymmetry generically reintroduces a large vacuum energy. Some proposals invoke the anthropic principle and the landscape multiverse. If the vacuum energy varies across different bubbles in the multiverse, then the value we observe is selected by the requirement that structures can form. The most celebrated result in this line of thinking is Steven Weinberg's 1987 prediction that if the cosmological constant varies and is selected anthropically, it should be small enough to allow galaxy formation, but not so small as to be effectively zero. The subsequent discovery of cosmic acceleration and the measurement of a small positive dark energy density is sometimes cited as a successful prediction of this argument. Whether this counts as a genuine scientific prediction or a post hoc rationalization is debated. The argument required accepting the multiverse before making the prediction, which is itself not confirmed. And the prediction was qualitative rather than quantitative. It said the cosmological constant should be small but non-zero, which is a wide target. Others argue that without the anthropic argument, the value would have been expected to be either exactly zero or extremely large, so the observed value does constitute a prediction in a meaningful sense. What the cosmological constant problem reveals, regardless of how it is eventually resolved, is that our understanding of the quantum vacuum is deeply incomplete. We know that the quantum vacuum has structure, energy, and physical effects. We do not understand why its net energy density has the specific, extraordinarily small but non-zero value that drives cosmic acceleration. This gap in understanding is directly relevant to the question of cosmic origins because it means we do not understand the most basic property of the state from which the universe is proposed to have emerged. Now let us turn to one of the most profound and least discussed aspects of the early universe story, the question of initial conditions. Every physical theory describes how a system evolves from one state to another. Given the state of the system at one time, the laws of physics predict what the state will be at later times. In classical mechanics, this is deterministic. In quantum mechanics, it is probabilistic. But in both cases, the theory requires initial conditions as input. The laws of physics do not tell you what the initial conditions were. They tell you how initial conditions evolve. This creates an immediate challenge for any theory of cosmic origins. If we want to use the laws of physics to explain the universe, we need initial conditions from which to start. But where do those initial conditions come from? If they are explained by earlier conditions, we have the problem of infinite regress. If they are taken as given, we have admitted that something exists that is not explained by physics. If the theory somehow generates its own initial conditions, we need to explain how that is possible. In standard Big Bang cosmology with inflation, the initial conditions of the observable universe are set by inflation. The CMB anisotropies, the flatness, the homogeneity, all of these are outcomes of the inflationary process rather than inputs to it. But inflation itself has initial conditions. The inflatoned field must start in a configuration suitable for inflation to begin. Where do those conditions come from? This regress is sometimes handled by appeal to chaotic inflation, as mentioned earlier. The argument is that if the universe is large enough and the initial conditions are sufficiently random, some regions will always be in a state suitable for inflation. But this argument presupposes a large universe with random initial conditions, which is itself an initial condition that needs explanation. Chaotic inflation does not eliminate the need for initial conditions. It shifts the initial condition from a special state to a generic one, but it still needs a state to start from. The Hartle-Hawking no-boundary proposal is the most direct attempt to address the initial condition problem. Instead of specifying initial conditions and then evolving them forward, the proposal specifies the quantum state of the universe through a specific mathematical rule, the no-boundary path integral, that does not require initial conditions in the usual sense. The wave function of the universe is determined by the no-boundary condition, and that wave function can in principle be calculated and its predictions compared with observation. The no-boundary proposal has been the subject of intensive calculation and debate. The original proposal suggested that it would prefer a universe with low initial curvature and small scale factor, consistent with a universe that starts in a state suitable for slow-roll inflation. More recent work, including calculations by Neil Turok and collaborators, has argued that the no-boundary wave function actually predicts that the most likely universe is one that starts with maximal curvature and is barely large enough to exist, not the universe we observe. This is a significant challenge to the proposal. Defenders of the no-boundary proposal have responded that the calculation of probabilities within the no-boundary framework is more subtle than it appears, and that the choice of how to define the path integral significantly affects the results. This is a genuine technical debate among serious physicists, not a settled matter. The difficulty of making precise calculations in quantum gravity is part of what makes these debates so hard to resolve. The initial condition problem is deeply connected to the question of whether the laws of physics can explain everything, or whether there must always be something that is taken as given. Every physical theory takes some things as given: the form of the laws, the values of the constants, the initial conditions, and the mathematical framework within which the laws are expressed. Some of these givens might be explained by a more fundamental theory, which would then have its own givens. Whether this regress terminates in a truly self-explanatory theory, or whether it goes on forever, or whether it terminates in something that is genuinely just given without explanation, is one of the deepest open questions in all of physics and philosophy. The concept of symmetry is one of the most powerful in all of physics, and it plays a crucial role in any discussion of the early universe and cosmic origins. Symmetry, in the physical sense, means that the laws of physics look the same under certain transformations. The laws are the same everywhere in space, which is the symmetry of spatial translation. They are the same in all directions, which is the symmetry of rotation. They are the same at all times, which is the symmetry of time translation. And they are the same for all observers in uniform motion, which is the symmetry of Lorentz transformations in special relativity. These symmetries are not just aesthetic preferences. They have profound physical consequences through a theorem proved by Emmy Noether in 1915. Noether's theorem states that every continuous symmetry of the laws of physics corresponds to a conserved quantity. Spatial translation symmetry gives conservation of momentum. Rotational symmetry gives conservation of angular momentum. Time translation symmetry gives conservation of energy. Lorentz symmetry gives a set of conservation laws for the combination of energy and momentum. Conservation of energy, one of the most fundamental principles in all of physics, is therefore not an independent axiom. It is a consequence of the fact that the laws of physics do not change over time. If the laws were different at different times, energy would not be conserved. The conservation law and the symmetry are two sides of the same coin. This has an interesting implication for the very early universe and for the question of cosmic origins. If the universe had a beginning in time, and if the laws of physics came into existence with the universe, then the symmetry of time translation would not apply in the same way near the beginning. The laws would be different at different times, in the sense that the very early universe may have been governed by different effective laws than the later universe. This could mean that conservation of energy, as we normally understand it, did not hold near the beginning. This is one reason why some physicists are comfortable with the idea that the universe could have arisen from a state with very different energy properties than we are accustomed to. If conservation of energy is a consequence of time translation symmetry, and if that symmetry was not present in the earliest moments, then the total energy of the universe is not a fixed quantity that was always there. It is a quantity that emerged along with the symmetry that defines it. The role of symmetry in the early universe goes beyond conservation laws. The forces of nature we observe today, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, appear to be very different from each other. They have different strengths, different ranges, and different mathematical structures. But theoretical physics suggests that at sufficiently high energies, some or all of these forces may be unified into a single force with a higher symmetry. The distinct forces we observe at low energies are the result of that symmetry being broken as the universe cooled. Electroweak unification, confirmed by experiment, shows that electromagnetism and the weak nuclear force are aspects of a single electroweak force that becomes apparent at energies above about 100 GeV. The electroweak symmetry is spontaneously broken at lower energies by the Higgs mechanism, giving the W and Z bosons their large masses and making the weak force short-ranged, while leaving the photon massless and electromagnetism long-ranged. This is a thoroughly confirmed piece of physics, tested at particle accelerators. Grand unified theories propose that the electroweak force and the strong nuclear force are further unified at much higher energies, around 10 to the 15 GeV, in a single force with an even larger symmetry. This unification is not yet confirmed because the required energies are far beyond current accelerators, but there is indirect evidence from the observed running of coupling constants, which approach each other at high energies in a way consistent with unification. Supersymmetric grand unified theories predict that the coupling constants converge more precisely than they do in non-supersymmetric theories, which was one of the original motivations for supersymmetry. Whether this convergence is evidence for grand unification or a suggestive coincidence is debated. The ultimate unification would include gravity, incorporating it into the same framework as the other forces. This is what string theory and loop quantum gravity attempt with different approaches. If gravity is unified with the other forces at the Planck scale, then in the earliest moments of the universe, all forces were a single unified force with a single high symmetry. The distinct forces and laws we observe today would all be the result of symmetry breaking as the universe cooled and expanded. In this picture, the laws of physics as we know them are not fundamental. They are the broken symmetry, remnants of a more unified and more symmetric set of laws that govern the earliest moments. The standard model of particle physics, as powerful as it is an effective theory valid at low energies, not the fundamental theory that would apply in the extreme conditions of the very early universe. This is relevant to the question of nothing because it means the question of why the laws of physics are what they are may be replaced, in part, by the question of why the unified law has the specific form it has, and why it breaks to give the standard model we observe. These are still hard questions, but they are more tractable than asking about the laws as they appear to us, because they involve fewer seemingly arbitrary choices. A highly symmetric unified theory has less apparent arbitrariness than the standard model with its 20 or so free parameters. The symmetry breaking that produces the standard model could, in some models, be calculable from the unified theory. Now let us think about something that is rarely addressed in popular cosmology, but that is essential to the deepest version of the origin question, the nature of mathematical existence, and whether it is the right framework for thinking about ultimate origins. Physics is expressed in mathematics. The laws of physics are mathematical equations. The structures described by those laws, fields, particles, spacetime geometries, are mathematical objects. When we say the universe evolved from a hot, dense early state, we mean the mathematical description of the universe, in terms of a Friedmann-Robertson-Walker metric and quantum fields, evolved from initial conditions corresponding to high density and temperature. The universe itself is the physical reality that corresponds to this mathematical description. But what is the relationship between the mathematical description and the physical reality? This is the question of scientific realism, and it is one of the oldest and deepest questions in the philosophy of science. There are several possible positions. Scientific realism holds that the entities described by our best scientific theories, including electrons, quantum fields, and spacetime curvature, are real entities that exist independently of our descriptions. The mathematical description is not the thing itself, but a representation of it that is accurate to the degree that the theory is confirmed by observation. Instrumentalism holds that scientific theories are tools for predicting observations and should be judged solely by their predictive success. The question of whether the entities they describe are real is meaningless or unanswerable. What matters is that the predictions work. Structural realism, a more nuanced position developed by several philosophers of science, holds that what our theories reveal about the world is not the intrinsic nature of things, but the structural relations between them. The mathematical structure of a theory captures the real structural relations of the world, even if we cannot know the intrinsic nature of the relata. For the question of cosmic origins, the relevant question is whether the mathematical framework of quantum, field theory, and general relativity is a representation of a physical reality that exists independently of the mathematics, or whether the mathematics is in some sense constitutive of the reality. If the former, then asking why the universe exists is asking why a particular physical reality exists, and the mathematics is just our way of describing it. If the latter, then asking why the universe exists might be asking why a particular mathematical structure is instantiated as physical reality, and perhaps the answer has to do with the nature of mathematical existence itself. Tegmark's mathematical universe hypothesis takes the most extreme form of the latter position. Mathematical existence and physical existence are the same. All mathematically consistent structures exist as physical realities, and our universe is one of them. On this view, the question of why the universe exists has a simple answer, because it is a mathematically consistent structure, and all mathematically consistent structures exist. The deeper question is why all consistent structures exist, to which the answer might be that this is simply what mathematical existence means. The mathematical universe hypothesis is provocative and has attracted serious attention. It removes the explanatory gap between mathematics and physics by identifying them. It potentially explains fine-tuning through anthropic selection among all possible mathematical universes. And it is in a sense the most parsimonious proposal. Instead of asserting that only one universe exists, ours, it asserts that all consistent universes exist, which requires only one postulate. Mathematical existence implies physical existence, rather than the specific postulate that this particular universe exists. But the hypothesis faces serious challenges. It is not clear what it means for a mathematical structure to be physically real without any connection to observation or experience. A mathematical structure that contains no observers is no different from any other mathematical structure. The hypothesis does not explain why we are observers in this particular universe rather than any other. It does not explain why the mathematical structures that are physically real include observers who are conscious and who can ask questions about their existence. And it has no clear empirical implications that could confirm or refute it, which makes it difficult to assess scientifically. The mathematical universe hypothesis illustrates a general feature of ultimate origin proposals. They tend to either explain everything, which means they make no specific predictions, or to explain some things by assuming others, which means they push the question back rather than answering it. A truly satisfying explanation of cosmic origins would explain why this universe exists, why it has the specific properties it has, and why we are here to observe it, without assuming anything else that requires equally deep explanation. No current proposal achieves this. Let us now address something that runs through the entire discussion, but has not been explicitly confronted: the role of consciousness and the observer in quantum mechanics and in the question of cosmic origins. Quantum mechanics is the most precisely tested theory in all of physics. Its predictions agree with experiment to more decimal places than any other theory, and yet, nearly a century after its formulation, there is no consensus on what it means. The interpretation of quantum mechanics, the question of what quantum mechanics is actually telling us about the nature of reality, remains one of the most actively debated questions in physics and philosophy of physics. The core issue is the measurement problem. Quantum mechanics describes the state of a physical system as a superposition of different possible states, each with a specific probability amplitude. Before measurement, the system is in this superposition. After measurement, the system is in a specific state, one of the possibilities. The question is, what happens during measurement that collapses the superposition to a specific outcome? What counts as a measurement? And what role, if any, does the observer play? The Copenhagen interpretation, the most historically influential and still widely used in practice, takes a pragmatic approach. It says that the wave function is a tool for calculating probabilities of measurement outcomes. Before measurement, the system is in a superposition. After measurement, the wave function collapses to a specific state. The measurement process is not described by quantum mechanics itself, which is an apparent inconsistency that Copenhagen sidesteps by treating the measurement apparatus and the observer as classical entities standing outside the quantum description. The many-worlds interpretation, proposed by Hugh Everett in 1957, takes a different approach. It says that the wave function never collapses. Instead, every time a quantum measurement occurs, the universe branches into multiple branches, each containing a different measurement outcome and a different version of the observer. All outcomes are realized, but they are in separate, non-interacting branches of a continuously branching universe. This eliminates the collapse and the measurement problem by making everything, including the observer, part of the quantum description. The many-worlds interpretation has attractive features. It is mathematically clean and avoids the apparent inconsistency of the Copenhagen approach, but it raises profound questions. What determines how the universe branches? Why do we experience a single definite outcome rather than all outcomes simultaneously? And the multiplicity of branches constitutes the level III multiverse, an enormous number of copies of reality, which some find physically extravagant. Decoherence, the process by which quantum superpositions become effectively classical through interaction with the environment, has helped clarify why we experience a classical world despite living in a quantum universe. When a quantum system interacts with a large number of environmental degrees of freedom, the different branches of the superposition become correlated with different environmental states and effectively cease to interfere with each other. The system behaves classically without any collapse, but decoherence does not fully solve the measurement problem. It explains why different branches do not interfere, but it does not explain why we observe a single definite outcome rather than experiencing all branches simultaneously. It makes the superposition into an effective mixture, but the mixture still contains all outcomes. Selecting one specific outcome as the one that is observed is not explained by decoherence alone. For cosmic origins, the measurement problem is relevant because it affects how we understand quantum cosmology. In quantum cosmology, there is no external observer and no external measurement apparatus. The universe is a closed system. The wave function of the universe evolves according to the Wheeler-DeWitt equation, but there is no external observer to collapse it. The many-worlds interpretation is the most natural framework for quantum cosmology because it does not require an external observer, but it comes with all the interpretational questions that the many-worlds interpretation raises. The no-boundary proposal is typically formulated in the framework of quantum cosmology, where the wave function of the universe is a specific quantum state calculated using the path integral. But what this wave function means, what it is telling us about the actual state of the universe, depends on the interpretation of quantum mechanics we adopt. In the Copenhagen interpretation, the wave function tells us the probabilities of different outcomes when the universe is observed. But who observes the universe as a whole? In the many-worlds interpretation, the wave function describes all possible universes simultaneously branching, and we exist in one branch. But why this branch? These interpretational questions are not merely philosophical. They affect what predictions we extract from quantum cosmological models and how we evaluate them. A calculation in quantum cosmology that predicts the probability of different initial conditions is meaningful only if we have a coherent interpretation of what probability means in the context of a single universe with a single history. This is the quantum cosmological version of the measure problem mentioned in the context of the multiverse. The relationship between consciousness and quantum mechanics adds another layer of complexity that is often raised in discussions of cosmic origins. Some interpretations of quantum mechanics, notably the von Neumann-Wigner interpretation, give consciousness a special role in wave function collapse. On this view, consciousness is required for measurement, and measurement is required for collapse. The universe exists in superposition until a conscious observer makes a measurement. This interpretation is not widely accepted among physicists, partly because it is difficult to define consciousness precisely, partly because it seems to assign a special status to biological organisms that is hard to reconcile with physics as we know it, and partly because decoherence and many worlds provide alternative explanations for the appearance of classical reality that do not require consciousness. For cosmic origins, the consciousness collapse interpretation creates an obvious problem. If consciousness is required for wave function collapse, and if consciousness did not exist before the first observers evolved, then the universe existed in superposition until relatively recently in cosmic history. What collapsed it? The problem is sometimes called the pre-observational universe problem, and it is one of the reasons most physicists prefer interpretations that do not give consciousness a special role. The anthropic principle, distinct from consciousness collapse interpretations, does give observers a special role, but in a different sense. It notes that our observations are conditioned on our existence. We can only observe the universe from within a region that is compatible with our existence. This is a selection effect, not a collapse mechanism. The universe does not need consciousness to be real. It needs consciousness to be observed by beings like us. Whether other regions are real in the same sense as our observed region depends on the interpretation of quantum mechanics, but the anthropic selection effect is independent of interpretation. The concept of information has emerged in recent decades as potentially fundamental to the understanding of physical reality, and it appears in multiple contexts relevant to cosmic origins. The holographic principle, mentioned earlier, suggests that the information content of a region is proportional to its surface area rather than its volume. This is a profound constraint that connects thermodynamics, quantum mechanics, and gravity in a way that is not yet fully understood. The holographic principle emerged from the study of black hole thermodynamics. Jacob Bekenstein showed in the early 1970s that black holes have entropy proportional to the area of their event horizons. Stephen Hawking showed that black holes emit thermal radiation, subsequently called Hawking radiation, with a temperature inversely proportional to their mass. These results were derived from a combination of general relativity and quantum field theory, and they suggest that black holes are thermodynamic objects with well-defined temperature and entropy. The entropy of a black hole is proportional to the area of its horizon in units of the Planck length squared, not to the volume of the black hole. This is surprising because for ordinary matter, entropy is proportional to the volume. A large container of gas has entropy proportional to the number of molecules times the volume, but a black hole's entropy is determined by the area of its boundary, not the volume of its interior. The holographic principle generalizes this observation. It proposes that the maximum information content of any region of space is proportional to the area of its boundary, not its volume. A region of space cannot contain more information than the Bekenstein-Hawking entropy of a black hole that would fill that region. This is a profound limitation on how much reality the interior of a region can contain. If information is bounded by area rather than volume, then the interior of a region is, in some sense, redundant with its boundary. All the information needed to describe the interior is also present on the boundary. This suggests that the interior description, with its three-dimensional structure and local physical laws, might be a derived description, a holographic projection of a more fundamental two-dimensional description on the boundary. This is the intuition behind AD-SCFT and holographic approaches to quantum gravity. For cosmic origins, the holographic principle is relevant because it suggests that the question of what existed inside the very early universe might be reframed in terms of boundary conditions rather than interior states. If the interior is holographically encoded on the boundary, then the initial conditions of the universe might be understood as properties of a boundary state rather than as a specification of a three-dimensional interior state. This changes both the mathematical form of the problem and the conceptual framework for thinking about it. The connection between information and physical reality goes deeper than holography. In quantum mechanics, the state of a system is a wave function, which is an information-theoretic object. It specifies the probabilities of all possible measurement outcomes. Physical processes are described by the evolution of this information state. The laws of quantum mechanics are laws about how information evolves. Some physicists and philosophers have suggested that information is not just a tool for describing physical reality, but is itself fundamental. John Archibald Wheeler, one of the most influential theoretical physicists of the 20th century, coined the phrase "it from bit" to express the idea that every physical entity and every physical phenomenon ultimately derives its existence from information, from yes or no answers to binary questions. Wheeler took this idea seriously not as a metaphor, but as a proposal about the ultimate nature of reality. If information is fundamental, then the question of why there is something rather than nothing might be reframed as, why is there information? Why is there a bit rather than nothing? This reformulation is no easier to answer than the original, but it changes what kind of answer we are looking for. Instead of asking why there are particles or fields or space, we ask why there are distinctions, differences, bits of information. And perhaps asking about distinctions is getting closer to something that can be analyzed in terms of mathematics or logic without presupposing a physical substrate. The informational approach to physics connects to recent work on quantum error correction and the structure of spacetime. It has been shown that the holographic correspondence in AD-SCFT has deep connections to quantum error correction codes, mathematical structures used in quantum information processing to protect information against noise and errors. Spacetime geometry in the bulk appears to encode the logical structure of an error-correcting code operating on the boundary theory. If spacetime geometry is connected to quantum error correction, then the geometry of spacetime is in some sense a representation of the information structure of the underlying quantum state. Spacetime does not precede the information. It is constructed from it. This is another way in which space and time might be emergent rather than fundamental, with quantum information playing the role of the more fundamental ingredient from which spacetime is assembled. What this might mean for the very early universe is speculative, but it suggests an interesting direction. Perhaps the earliest moments of the universe, the regime where classical spacetime breaks down, are better described in terms of quantum information than in terms of geometry. Perhaps the Big Bang singularity is a feature of the geometric description that dissolves in the information-theoretic description. And perhaps the question of what preceded the Big Bang is a question about the quantum information state from which the geometric description of the universe emerged, not a question about what was in a pre-existing space and time. We are now in a position to think carefully about what a complete theory of quantum gravity would need to achieve, not just technically, but conceptually, to genuinely address the question of cosmic origins. This is not about listing the technical requirements for a theory of quantum gravity, although those are important. It is about understanding what conceptual shifts would be required for the theory to genuinely resolve the mystery rather than just pushing it back. A complete theory of quantum gravity would need to handle the Planck scale regime, where classical spacetime breaks down. It would need to resolve the Big Bang singularity in a physically meaningful way. It would need to make predictions that can be tested against observations, at minimum, by reproducing the known physics of the post-Planck era, and at best by making new predictions for observable quantities. And it would need to address the problem of time, explaining either how time emerges from a more fundamental description, or why the timeless description of quantum gravity gives rise to the apparent flow of time we experience. Beyond these technical requirements, a genuinely satisfying theory of quantum gravity would need to change our understanding of what space, time, matter, and law are. The history of physics suggests that each major theoretical advance has not just solved specific problems, but has revealed that familiar concepts are approximations of something deeper. Newtonian mechanics was not just superseded by quantum mechanics. Quantum mechanics revealed that classical trajectories are emergent approximations of quantum amplitudes, that determinism is an approximation valid in certain limits, and that the physical world is fundamentally probabilistic. The conceptual shift was as important as the technical advance. A theory of quantum gravity that merely fixes the singularity without changing our understanding of space, time, and causality would be technically valuable but conceptually insufficient. What is needed, and what many physicists believe is coming, is a theory that reveals spacetime and matter, and perhaps even the laws themselves as emergent phenomena, arising from a more fundamental level of description in which these concepts do not. What that more fundamental level looks like, what its basic elements are, and what its laws say is currently unknown. This unknown is the frontier. It is the place where the mystery of cosmic origins actually lives, not in the question of what was there before the Big Bang, which is a question about a time, but in the question of what the most fundamental level of reality is, what its structure is, and why it exists at all. These questions are connected, but they are not the same. Answering what the fundamental level is would be an enormous advance, even if it did not explain why that fundamental level exists. And understanding why it exists, if such understanding is possible at all, would be the deepest achievement of human intellectual history. There is a conversation that happens frequently at the boundary between physics and philosophy, and it is a conversation about what questions physics can answer and what questions it must leave to other forms of inquiry. This conversation is sometimes hostile, with physicists dismissing philosophical questions as confused and philosophers accusing physicists of naive scientism. But at its best, the conversation is productive, and it is worth having explicitly here. Physics is extraordinarily good at answering questions of the form. Given that certain things exist and obey certain laws, what happens? This is the question that all physical theories answer. Given electrons and photons obeying quantum electrodynamics, what is the scattering amplitude for electron-electron scattering? Given a universe with initial conditions consistent with inflation and containing dark matter and dark energy, what does the large-scale structure look like today? Given a black hole of a certain mass, what is the rate of Hawking radiation? Physics is less good at answering questions of the form. Why do these particular things exist rather than others? Why do they obey these particular laws rather than different ones? And physics is essentially silent on questions of the form. Why does anything exist at all? This is not a failure of physics. It is a feature of what physics is. Physics describes the regularities of the physical world, and it does so with extraordinary precision and power. But describing regularities requires a framework, and the framework itself is not described by the physics. You cannot use the laws of physics to explain why the laws of physics are what they are without circularity. You cannot use the mathematical framework of physics to explain why mathematical structures exist without assuming that mathematical existence is its own explanation. Philosophy, at its best, can help with these boundary questions. Not by providing answers that physics cannot, but by clarifying what the questions mean, identifying what kind of answer would be satisfying, and examining whether the questions are coherent at all. The question of why there is something rather than nothing has been examined by philosophers for millennia, and they have made progress, not necessarily in answering it, but in understanding its structure. One important insight from philosophy is that the question assumes a contrast between something and nothing, and that this contrast is meaningful. But if nothing is truly nothing, if it is the complete absence of everything including possibility and logic, then it is not clear that nothing is a coherent alternative to something. If there can be no logically possible state of affairs, then nothing is not a possible state of affairs. And asking why we have something rather than nothing is asking why something rather than an impossible alternative. The question might be revealed as incoherent. Another philosophical insight is that if there is no possible state of nothing, then something is necessarily the case. The existence of something would then not need to be explained by reference to anything else. It would be necessarily true, like a mathematical theorem, not contingently true, like a historical fact. Some philosophers have argued for this position, holding that existence itself is necessary, and that the universe or some necessary entity exists necessarily. Whether the universe or the laws of physics or anything physical could be necessarily existent in this philosophical sense is deeply uncertain. Necessary existence is a concept developed primarily in the context of logic and mathematics. Mathematical truths are necessary because they follow from axioms in a framework where the axioms cannot consistently be denied. Whether physical truths are necessary in the same sense is not established. The laws of physics might have been different as far as we know. The constants might have had different values. The universe might not have existed, or they might not. We simply do not know whether physical existence is contingent or necessary, whether the laws could have been different or are somehow fixed by deeper necessities. This is one of the questions that sits at the intersection of physics and philosophy, requiring the tools of both and currently answerable by neither. As we approach the end of this deep investigation, let us take stock not just of what we know and do not know, but of why the question matters. Not in the sense of practical utility, because understanding cosmic origins has no obvious practical application, but in the sense of what the question reveals about us, about the kind of beings we are, and about the relationship between our minds and the universe we inhabit. We are, as far as we know, the only part of the universe that asks questions about the universe's origin. The universe has existed in some form for nearly 14 billion years. For almost all of that time, there were no minds to wonder about it, no consciousness to be puzzled by it, no curiosity to drive the investigation. And then in the last few 100,000 years, on a small planet around an ordinary star in an unremarkable galaxy, beings evolved with the capacity to ask why, to wonder, to build theories and test them, to map the universe from the inside. This is extraordinary regardless of the answer to any specific cosmological question. The universe produced something that can wonder about itself. Whether that is the result of a chain of physical causes stretching back to the Big Bang, whether it is a selection effect of the multiverse, whether it is somehow connected to the holographic structure of quantum gravity, or whether it is simply what happens when matter organizes itself in certain ways over billions of years, the fact of it is remarkable. And the wondering itself reveals something about the relationship between minds and reality. Minds did not come with an owner's manual telling them which questions are meaningful and which are confused. The question of why there is something rather than nothing felt meaningful long before anyone thought carefully about whether it could be answered. It felt meaningful because something in the structure of consciousness finds it meaningful. The question arises naturally in minds capable of abstract thought and self-reflection. It is not forced on us by observation. It is generated by the mind's own encounter with existence. Whether that sense of meaningfulness is a reliable guide to the question's answerability is itself uncertain. We have many examples in intellectual history of questions that felt deeply meaningful but turned out to be confused. Questions about what the universe is at rest with respect to felt meaningful before special relativity showed that absolute rest is meaningless. Questions about the ether, the medium through which light propagates, felt meaningful before Maxwell's equations, and the Michelson-Morley experiment showed that the ether does not exist. The sense of meaningfulness is not infallible. But we also have examples of questions that initially seemed absurd or confused, but turned out to be the most productive questions in the history of science. The question of what matter is made of at the smallest scales seemed impossibly small to address, and yet led to atomic physics, quantum mechanics, and the Standard Model. The question of the origin of species seemed impossibly grand to address, and yet led to evolutionary biology. The question of what gravity is seemed to require no more than a description of its effects, and yet led to general relativity and the discovery that spacetime is curved. The question of why there is something rather than nothing might be in either category. It might be confused and dissolve on analysis, revealing itself to be based on a faulty concept of nothing or a faulty concept of explanation. Or it might be the deepest productive question in the history of human thought, the one that forces us to the most fundamental revision of our understanding of reality. We cannot know which it is until we engage with it fully and follow the consequences wherever they lead. That engagement is what physics and philosophy together are doing, slowly and carefully, at the frontier where the questions are hardest and the tools are least adequate. It is the most ambitious intellectual project in human history, and it is ongoing. Let us close this part of the investigation with a careful statement of where things stand, not as a conclusion, but as an honest map of the current frontier. The universe has a history that we can trace with high confidence back to the first fraction of a second after the hot, dense early state. That history is described by a consistent framework, the standard model of cosmology with inflation, that reproduces a wide range of observations. The framework is well established, and its central claims are not seriously contested. At the boundary of this framework, where quantum gravity becomes essential and where classical spacetime cannot be trusted, we have candidate theories but no confirmed theory. Loop quantum cosmology suggests a bounce. String cosmology suggests rich pre-Big Bang possibilities. The no-boundary proposal suggests that time itself becomes spatial near the beginning, dissolving the question of what came before. Cyclic models suggest a periodic universe without a first moment. Each of these is a serious theoretical proposal with mathematical content and some connection to observation. None is confirmed. The quantum vacuum from which the universe may have emerged is not philosophical nothing. It is a specific physical state with fields, energy, and fluctuations. The laws that govern it are assumed rather than explained. The question of why those laws exist is not answered by any current proposal. The question of why there is something rather than nothing in the most absolute sense is not addressed by physical theories, which always assume some framework is given. Time may be emergent rather than fundamental. Causality may be emergent rather than fundamental. Spacetime itself may be emergent, arising from quantum entanglement or quantum information in a more fundamental description. These ideas are motivated by theoretical considerations and are actively being developed, but they have not been confirmed. The fine-tuning of the physical constants is a genuine puzzle. It may be explained by a deeper theory that derives the constants, by anthropic selection in a multiverse, or it may be a brute fact without explanation. We do not know which. The question of cosmic origins sits at the intersection of physics and philosophy, requiring the tools and the standards of both. It is not a question that physics alone can answer, because the deepest version of the question asks about the existence of the physical framework itself. And it is not a question that philosophy alone can answer, because answering it requires knowing what the physical framework actually is, which requires physics. The honest summary is that we are making progress. The progress is real and significant. The map of the early universe has become vastly more detailed and more precise over the past century. The theoretical proposals for extending that map beyond the observable horizon are becoming more specific and more testable. The conceptual tools for thinking about emergent spacetime, quantum gravity, and the nature of time are becoming more developed. The question of what came before the Big Bang is being transformed from a purely philosophical speculation into a scientific research program with real theoretical content and real observational implications. But the deepest question, why there is anything at all, remains genuinely open. It may always remain open. It may be the kind of question that drives scientific and philosophical progress indefinitely without ever being fully resolved. Or it may be the kind of question that, when the right framework is found, turns out to have an answer that we cannot currently imagine. We do not know which it is. What we know is that the question is worth asking, that the asking drives some of the most important scientific and philosophical work of our time. That the tools we have developed in pursuit of it, from quantum mechanics to general relativity to quantum field theory to holography to the study of emergent spacetime, have transformed our understanding of reality in ways that go far beyond the specific question of origins, and that the frontier where the question lives is the most interesting place in all of human intellectual life. The universe, as far as we can tell, began, or it bounced. Or it emerged from a quantum state where time was not yet time, or it is one bubble in an eternal inflationary sea. We do not know which, but we are, slowly, carefully, and with disciplined attention to what the evidence allows, finding out. We have covered enormous ground. We have traced the observable universe back to its earliest accessible moments, examined the theoretical proposals that reach beyond the observational horizon, explored the nature of the quantum vacuum, confronted the problem of time and causality in quantum gravity, and been honest throughout about the distance between what observation confirms and what theory proposes. Now we arrive at the final chapter of this investigation, and its purpose is different from what has come before. The previous parts built the foundation. They established what we know, mapped what we do not know, and characterized the frontier where the deepest questions live. This final part does something harder and more important. It asks what it all means. Not in a vague, inspirational sense, but in a precise, intellectual sense. What does the investigation of cosmic origins reveal about the nature of scientific explanation? What does it reveal about the relationship between mathematics and physical reality? What does it tell us about the limits of human understanding, and about whether those limits are permanent or temporary? And what does it suggest about how we should think, individually and collectively, about questions that resist easy answers? These are not afterthoughts. They are the point. The universe's origin is interesting not only as a physical question, but as a test case for human understanding at its absolute limits. How we handle questions at the frontier, whether we are honest about uncertainty or reach for false comfort, whether we maintain the discipline of evidence or let imagination run ahead of data, whether we recognize when a question needs reformulation rather than an answer, all of this matters far beyond cosmology. It matters for how we approach any hard question in any domain. Let us begin this final part by being very specific about something that has been present throughout the investigation, but never stated as baldly as it deserves to be. The question of why there is something rather than nothing is not one question. It is at least 5 distinct questions that are often conflated, and they have very different characters and very different prospects for answers. The first question is empirical and scientific. What were the initial conditions of the observable universe, and what physical process set them? This question is being actively addressed by cosmological observation and inflationary theory. It has real answers, partially known, and real prospects for becoming better known. It is a hard question, but it is the kind of question that science is built to answer. The second question is theoretical and scientific. What is the correct theory of quantum gravity, and what does it say about the regime where classical spacetime breaks down? This question is being addressed by theoretical physics research in loop quantum gravity, string theory, and other frameworks. It does not yet have a confirmed answer, but it is a well-posed scientific question with clear criteria for what a correct answer would look like. The third question is foundational and partly philosophical. Why do the laws of physics have the specific form they have, and why do the constants of nature have the specific values they do? This question sits at the intersection of physics and philosophy. Some aspects of it may be addressable by physics, specifically by finding a deeper theory that explains the observed constants. Other aspects may be irreducibly philosophical, particularly the question of whether the laws are contingent or necessary. The fourth question is metaphysical. Why does anything exist at all? Why is there a physical reality rather than pure emptiness or pure absence? This question is genuinely philosophical in the deepest sense. It may not be answerable by physics because it asks about the existence of the physical framework itself, which physics assumes as given. It may or may not have an answer, and determining whether it has an answer requires the tools of conceptual analysis that philosophy provides. The fifth question is psychological and cultural. Why do we find the question of cosmic origins so compelling, and what does our fascination with it reveal about human nature? This question is interesting in its own right, but it is a different kind of question from the others, one that belongs to psychology, anthropology, and the philosophy of mind, rather than to physics or metaphysics. Conflating these 5 questions produces confusion. When a physicist says the universe came from nothing, they are usually addressing questions 1 and 2, proposing that the universe emerged from a quantum vacuum state through a process described by physics. When a philosopher hears this and objects that the quantum vacuum is not nothing, they are pointing out that the physicist has not addressed question 4. When a religious thinker hears it and says this still does not explain ultimate origins, they are raising question 4 again. And when a psychologist notes that the question feels compelling regardless of any proposed answer, they are asking question 5. None of these parties is wrong. They are asking different questions and failing to notice that they are doing so. The most productive conversations about cosmic origins happen when the participants are clear about which question they are addressing and do not pretend to have answered a question they have not touched. With this clarification in place, let us revisit each of the major theoretical proposals we have discussed and assess them against each of the 5 questions. This is not a summary, but a sharper evaluation, a more precise accounting of what each proposal achieves and what it does not. Cosmic inflation, the proposal that the universe underwent rapid accelerated expansion in its earliest moments, addresses question 1 directly and successfully. It explains why the observable universe is so uniform, why it is spatially flat, and why the primordial fluctuations have the observed scale-invariant spectrum. These are real achievements that make inflation the most successful framework for understanding the initial conditions of the observable universe. Inflation does not address question 2 because it is formulated within the framework of general relativity and quantum field theory and does not require or provide a theory of quantum gravity. It does not address questions 3 or 4, because it assumes the laws of quantum mechanics and general relativity and the existence of the inflated field without explaining any of these. It does not address question 5. The quantum vacuum picture, the idea that the universe emerged from a quantum vacuum fluctuation, addresses question 1 partially. It provides a mechanism for how a universe could arise from a near-vacuum state if the vacuum is governed by appropriate quantum mechanical laws. But it does not address question 2, because it does not specify what quantum gravity does near the Planck scale. It does not address questions 3 or 4, because it assumes the laws of quantum mechanics and the existence of quantum fields, and it inadvertently raises a confusion between the physical vacuum, which is something, and philosophical nothing, which is truly nothing. This confusion has been a source of much public misunderstanding. The no-boundary proposal addresses question 2 directly by proposing a specific quantum gravitational description of the universe's wave function that does not require initial conditions in the usual sense. It changes what question 1 means by dissolving the question of what came before rather than answering it with a specific prior state. Whether it successfully addresses question 2 depends on whether it can be made mathematically precise and whether its predictions are consistent with observation, both of which are contested. It does not address questions 3 or 4 because it assumes the mathematical framework of quantum gravity and the laws governing the wave function without explaining them. Loop quantum cosmology addresses question 2 partially by providing a specific quantum gravitational model in which the singularity is replaced by a bounce. It makes predictions for question 1, specifically predictions about modifications to the primordial power spectrum near the bounce scale. Whether these predictions are correct is testable in principle and the subject of ongoing research. It does not address questions 3 or 4 because it assumes the framework of loop quantum gravity and the specific form of its equations without explaining them. The multiverse in its inflationary form addresses question 3 partially by providing a mechanism for why the universe has the specific constants and laws it does through anthropic selection among a large ensemble of universes with different properties. Whether this counts as a genuine answer to question 3 is debated. It does not address question 4 because the multiverse itself requires the laws of quantum mechanics and the inflated field to exist and operate, which is an assumption rather than an explanation. It also faces the measure problem, which prevents it from making precise probabilistic predictions. Cyclic models address questions 1 and 2 by replacing the singular beginning with a bounce and proposing a specific physical mechanism for the cycling. They make predictions for question 1 that differ from inflationary predictions, particularly for the primordial gravitational wave background. They do not address questions 3 or 4 because they assume the laws governing the cycling without explaining them. Holographic approaches and the emergence of spacetime from quantum information address question 2 in a deep and potentially transformative way. They suggest that the question of what happened at the Big Bang singularity might be dissolved by moving to a more fundamental description in which spacetime is not fundamental. They are still far from making specific predictions for question 1. They do not address questions 3 or 4. The mathematical universe hypothesis addresses question 4 directly by proposing that mathematical existence and physical existence are the same, so the universe exists because it is a mathematically consistent structure. Whether this is a satisfying answer to question 4 is contested, and the proposal does not address question 3 in any standard sense, because in the mathematical universe all consistent structures exist and there is no specific explanation for why this particular structure has these particular constants. Having assessed the proposals against the 5 questions, it is worth reflecting on the overall structure of the situation. Question 1 is being addressed successfully, progressively, and with real prospect of further progress through observation and theory. Question 2 is being actively addressed, but is far from resolved, requiring a complete theory of quantum gravity that we do not yet have. Question 3 is partially addressable by physics and partly requires philosophy. Question 4 is currently beyond physics and may always be. Question 5 is interesting, but belongs to a different domain. This structure reveals something important about the relationship between scientific progress and philosophical depth. Scientific progress, the accumulation of confirmed knowledge, the development of tested theories, the refinement of measurements, has been spectacular over the past century in cosmology. We know enormously more about the universe's history and structure than we did 100 years ago. The progress on question 1 has been extraordinary, but scientific progress on question 1 does not translate into philosophical progress on question 4. Knowing more about how the universe evolved does not, by itself, answer why the universe exists. These are genuinely different questions, and the distinction between them should be preserved even when, perhaps especially when, the scientific achievements are spectacular. This is not a criticism of science. It is a description of what science is. Science is the most powerful tool ever developed for answering how questions. It excels at describing mechanisms, identifying regularities, making predictions, and testing them. It is not primarily designed to answer why questions in the deepest philosophical sense, and holding science to that standard is unfair to both science and philosophy. The most intellectually honest position is one that celebrates scientific achievement for what it is, acknowledges philosophical depth for what it is, and does not pretend that one resolves the other when it does not. This requires a kind of intellectual humility that is harder in practice than it sounds. When the scientific achievements are as dazzling as those in modern cosmology, the temptation to claim they have resolved the deepest philosophical questions is strong. Resisting that temptation is essential to maintaining the integrity of both the science and the philosophy. Let us now turn to something that has been implicit throughout the investigation but deserves explicit treatment: the relationship between the limits of human understanding and the limits of human cognitive architecture. Our brains evolved to solve specific problems in a specific environment. The problems were tracking objects in three-dimensional space, predicting the behavior of other organisms, planning sequences of actions over time, and communicating through language. The environment was the scale of everyday human experience, from millimeters to kilometers, from seconds to years, from the movement of individual objects to the behavior of small groups. None of the cognitive tools that evolution gave us were selected for their ability to understand quantum mechanics, general relativity, or the very early universe. Those tools are entirely outside the environment in which our cognitive architecture was shaped. The fact that we can understand these domains at all is remarkable, and it is due not to biological evolution, but to cultural and intellectual evolution, the development of mathematics, logic, controlled experiment, and the collective enterprise of science over thousands of years. But the fact that we can understand quantum mechanics and general relativity in the sense of developing mathematical theories that make correct predictions does not mean we can intuitively understand them. The double-slit experiment, in which a single particle seems to pass through two slits simultaneously, remains counterintuitive to every physicist who has ever lived, including the physicists who developed the theory that describes it. The fact that time passes more slowly for a moving observer than a stationary one remains deeply strange even to physicists who use this fact routinely in calculations. Understanding in physics often means being able to calculate correctly rather than being able to visualize intuitively. The very early universe and the question of cosmic origins push this disconnect between calculation and intuition to its extreme. The mathematics of quantum gravity, to the extent that we have it, involves structures that have no intuitive analog in everyday experience. The path integral over geometries, the wave function of the universe, the entanglement structure of holographic duals of spacetime, these are mathematical objects that expert physicists can work with but that bear no resemblance to anything in ordinary experience. This creates a genuine challenge for understanding. When we say we understand something, we usually mean we can form a mental model of it, a simplified representation that captures the essential features and allows us to reason about it intuitively. We understand falling objects because we have a mental model of gravity as a pull toward the ground. We understand light switches because we have a mental model of electricity flowing through circuits. But what is the mental model of the wave function of the universe? What is the mental model of spacetime emerging from quantum entanglement? What is the mental model of a regime in which time is not yet time? We do not have good mental models for these things, and we may not be able to have them. Our cognitive architecture may simply lack the internal structure needed to represent these concepts intuitively. This is not a failure of intelligence or imagination. It is a limitation of the kind of minds evolution gave us, minds suited for navigating a world of medium-sized objects at medium speeds in 3 dimensions, not for intuitively grasping 4-dimensional spacetime or quantum mechanical superposition or the absence of time. Mathematics compensates for this limitation to a remarkable degree. Mathematical formalisms allow us to reason precisely about structures that we cannot visualize, to derive correct predictions about phenomena we cannot intuit, and to connect different areas of knowledge in ways that intuition could never suggest. The unreasonable effectiveness of mathematics that Wigner noted is partly explained by this compensatory role. Mathematics extends our cognitive reach beyond the boundaries of intuition, but mathematics also has limits as a tool for understanding. Mathematical theories make predictions, and correct predictions are the gold standard for scientific understanding. But a theory that makes correct predictions without providing an intuitive picture of why the predictions are correct leaves us with something that works, but that we do not fully understand in the deepest sense. We can calculate the answer without understanding the phenomenon. This gap between calculation and understanding is present throughout quantum mechanics. The theory makes extraordinarily precise predictions, confirmed to many decimal places. But the interpretation of the theory, what quantum mechanics is actually telling us about the nature of reality, remains contested after a century. Different interpretations, Copenhagen, many worlds, pilot wave, relational, give different accounts of what the calculation means. They agree on the predictions, but disagree on what the predictions reveal about reality. For quantum gravity and the early universe, the gap between calculation and understanding is even wider. We have partial theories with some calculational power, but we lack the comprehensive framework needed to make reliable predictions about the Planck regime. And even when we have the calculations, the interpretation of what they mean for the nature of reality will be contested. The history of quantum mechanics suggests that having the correct theory does not automatically provide philosophical clarity. This brings us to a question that is rarely asked explicitly in discussions of cosmic origins, but that is central to the whole enterprise. What would it feel like to understand the origin of the universe? Not what would the theory look like, not what predictions it would make, but what would it feel like from the inside, from the perspective of a human mind that had genuinely grasped why the universe exists and how it came to be. There are at least two very different possibilities. In the first, understanding the origin of the universe would feel like understanding anything else. It would produce the familiar satisfaction of a puzzle solved, the sense of pieces fitting together, the feeling of clarity where there was confusion. The mystery would dissolve, replaced by knowledge, and the knowledge would feel complete in the way that understanding how to solve an equation feels complete. The question would be answered, and we would know it. In the second possibility, understanding the origin of the universe might feel radically different. It might require concepts so foreign to our intuitions that having the theory would not produce the familiar feeling of understanding, even if the theory were correct. We might have the mathematics right, making correct predictions, resolving the singularity, explaining the initial conditions, without ever feeling the click of genuine comprehension. The theory might work without feeling understood, the way quantum mechanics works without feeling natural permanently. The history of physics suggests both possibilities are real. Sometimes new theories bring conceptual clarity as well as technical power. Newton's mechanics, whatever its limitations, gave people a clear picture of the solar system as a clockwork governed by universal forces. Maxwell's electrodynamics gave a clear picture of light as electromagnetic waves. Darwin's evolution gave a clear picture of species as products of descent with modification. These theories are genuinely comprehensible even if they require learning. Other theories, particularly quantum mechanics and general relativity, are technically powerful but conceptually alien. After a century, physicists are still debating what quantum mechanics means. Spacetime curvature can be calculated, but cannot be visualized in any genuinely intuitive way. These theories work, but they do not fully satisfy the human need for mental models. A theory of quantum gravity and cosmic origins is more likely to be like the second kind than the first. If spacetime is emergent, if time is not fundamental, if causality is approximate, if the universe's wave function is described by a mathematical object with no intuitive interpretation, then the theory might be technically complete without being intuitively satisfying. We might solve the scientific problem without resolving the psychological experience of the mystery. This is important to acknowledge, because it means that even a complete scientific understanding of cosmic origins would not necessarily make the universe feel less mysterious. The mystery might persist not because we lack knowledge, but because we lack the cognitive architecture to feel at home with the knowledge we have. The universe might be completely understood in the theoretical sense and remain experientially enigmatic. Whether this is a limitation or a feature is a matter of perspective. One view is that it represents the alienation of human understanding from human experience, a tragedy of the scientific enterprise that produces knowledge without wisdom. Another view is that the persistent sense of mystery is appropriate and honest, a genuine reflection of the strangeness of reality that no amount of calculation should dissolve. The universe is strange. It should feel strange. A theory that made it feel ordinary would be suspicious. Let us now think about what the investigation of cosmic origins has revealed about the nature of scientific explanation itself, because this is one of the most important lessons of the whole enterprise. Scientific explanation has a structure. It involves showing that a phenomenon follows from a set of laws and initial conditions. To explain why the apple falls to the ground, you show that Newton's laws of gravity applied to the masses of the apple and the Earth and the initial conditions of the apple's position and velocity, imply the observed trajectory. The explanation has two components, the laws and the initial conditions. Neither component is itself explained by the physics that explains the phenomenon. The laws are assumed. The initial conditions are given. This structure is very powerful within its domain. It has been applied to explain an enormous range of phenomena, from planetary orbits to chemical reactions to the structure of proteins. The domain in which this kind of explanation works is vast, but it has an obvious limitation. It cannot explain its own components. It cannot explain why the laws are what they are, or why the initial conditions were what they were, without invoking a higher-level theory with its own laws and initial conditions, and this regress cannot continue forever. In practice, scientists do not worry much about this limitation, because within the domain of everyday science, the regress terminates at a level of basic physical laws that are taken as fundamental, or at initial conditions that are treated as given parameters to be measured rather than explained. The regress is real, but it does not impede scientific progress in the domain where the explanatory structure works. Cosmic origins is the domain where the limitation becomes acute. Here we are trying to explain the initial conditions of the universe itself, not just the initial conditions of some subsystem within the universe. The laws we would invoke to explain those initial conditions are the laws of quantum gravity, which are themselves part of what needs to be explained in any deep account of cosmic origins. And the initial conditions of the quantum gravitational state, if there are any, need their own explanation. One response to this limitation is to argue that explanation must eventually terminate in brute facts, things that are simply the case without any deeper reason. The laws of physics, or the initial state of the universe, or the mathematical structure from which everything follows, are brute facts. They are not explained by anything deeper. They just are. This response is intellectually coherent, but psychologically unsatisfying. Brute facts feel like explanatory failures rather than genuine resting points. The human mind, or at least the scientific mind, seeks explanations in terms of deeper principles. Accepting a brute fact feels like giving up. Another response is to argue that the explanatory structure of science can be extended to explain its own foundations through some kind of self-explanation or circular justification. Perhaps the laws of physics, properly understood, explain why they had to be exactly as they are. Perhaps mathematics explains itself. Perhaps existence explains its own possibility. These self-referential explanatory strategies have been explored in philosophy and formal logic, and they are fascinating, but they face deep problems. Self-referential systems tend to produce paradoxes rather than explanations, as Gödel's incompleteness theorems demonstrate for formal mathematical systems. A third response, perhaps the most honest, is to accept that explanation has limits, and that these limits are not failures but features of what explanation is. Explanation is a tool for reducing mystery by showing how one phenomenon follows from others. It is extraordinarily powerful within its domain, but it cannot reduce all mystery without circularity, because every explanation requires an unexplained framework. The regress terminates somewhere, not because we have found the deepest truth, but because we have reached the limit of what the explanatory tool can do. At this limit, the appropriate response is not to invent explanations that go beyond what the evidence supports, and not to pretend there is no mystery. The appropriate response is to acknowledge the limit with intellectual honesty, to continue pushing the limit as far as evidence and reasoning allow, and to remain genuinely open to the possibility that new conceptual frameworks might change what the limit is. This is the scientific spirit applied to its own limitations. There is a powerful temptation, when confronting the deepest questions about cosmic origins, to turn to narratives that go beyond what science can support. The universe came from nothing because God created it. The universe emerged from a perfect mathematical structure because mathematics is the ground of being. The universe is a simulation created by a more advanced intelligence. The universe exists because existence is its own justification. These narratives are not all equally unsupported. Some engage with the philosophical depth of the question more seriously than others, but they share a common feature. They go beyond what the evidence supports. They provide the closure and the sense of understanding that the genuine scientific and philosophical situation does not provide. They satisfy the psychological need for a complete story, even when the actual state of knowledge does not support one. The temptation is understandable. Incomplete answers are uncomfortable. Living with uncertainty is psychologically demanding, especially about questions that feel fundamental. The mind seeks closure. It prefers a story that ends to one that trails off into acknowledged ignorance. And when the question is as deep as why the universe exists, the pull toward complete narratives is especially strong. but yielding to this temptation does a disservice not only to intellectual honesty, but to the genuine drama of the actual situation. The real story, the story that science and philosophy together are piecing together at the frontier of human understanding, is more interesting than any premature narrative. The genuine uncertainty, the genuine open questions, the genuine possibility that entirely new concepts are needed to make progress, these are not failures of understanding. They are the marks of a question so deep that it pushes human thought to its absolute limits. The appropriate response to the deepest questions is not premature closure, but sustained, honest engagement. It is the willingness to sit with uncertainty, without either collapsing into comfortable falsehood or retreating into cynical dismissal. It is the recognition that some questions are worth living with for a long time, perhaps forever, because the living with them, the careful thinking, the patient investigation, the honest acknowledgement of limits, is itself a form of understanding even when final answers are not available. This is not a counsel of despair. The investigation of cosmic origins has produced real knowledge. We genuinely know things about the early universe that nobody knew a century ago. The knowledge is increasing. The tools are improving. The theoretical frameworks are becoming more sophisticated. Progress is real, but progress does not require pretending that the frontier does not exist or that the deepest questions have been answered when they have not. Now let us address the future of this investigation, because the investigation will continue, and the tools available to it will improve in ways that are already visible. In observational cosmology, the next decade will see a new generation of CMB experiments designed to measure the polarization of the cosmic microwave background with unprecedented sensitivity. The primary target is B-mode polarization produced by primordial gravitational waves, which would be a direct signal of inflation and would constrain the energy scale at which inflation occurred. The Simons Observatory and CMB-S4 are among the most ambitious planned experiments. Their sensitivity, if achieved, will either detect primordial B-modes or push the constraints down to levels that rule out a large class of inflationary models. The detection of primordial B-modes would be one of the most important discoveries in the history of cosmology. It would confirm that inflation occurred at a specific energy scale and would give us direct information about the energy of the inflatoned field, something we currently infer only indirectly. It would also strengthen the connection between the observed large-scale structure of the universe and quantum mechanical processes in the very early universe, making the claim that quantum fluctuations seeded cosmic structure more direct. Non-detection, pushing the upper limit on the tensor-scalar ratio significantly below current bounds, would challenge the simplest large-field inflationary models and favor either small-field inflation or alternatives to inflation. This would not rule out inflation entirely, but would significantly narrow the parameter space and put pressure on specific models. The scientific outcome either way would be valuable, which is a sign of good experimental science. Beyond the CMB, the large-scale structure of the universe is being mapped with increasing precision by surveys like DAISY, the Dark Energy Spectroscopic Instrument, and Euclid, a European Space Agency mission. These surveys measure the three-dimensional distribution of galaxies across billions of light-years, providing information about the growth of structure and the expansion history that complements and cross-checks CMB measurements. They can test the predictions of inflationary models for the large-scale structure and probe the nature of dark energy with greater precision than currently possible. Gravitational wave astronomy, opened by LIGO's first detection in 2015, is expanding its reach. The next generation of ground-based detectors, Einstein Telescope and Cosmic Explorer, will detect gravitational waves from much farther away and with much greater sensitivity, probing the population of compact binaries throughout the observable universe. More relevantly for cosmic origins, the pulsar timing arrays operated by Nanograv, the European Pulsar Timing Array, and other collaborations have detected what appears to be a gravitational wave background at very low frequencies. The nature of this background, whether it comes from supermassive black hole binaries, from cosmic strings, or from some primordial process in the early universe, is currently being determined. If any component is primordial, it would be a direct window into the early universe complementary to the CMB. The Space-Based Gravitational Wave Observatory LISA, planned for launch in the 2030s, will probe gravitational waves at frequencies between those accessible to ground-based detectors and those accessible to pulsar timing arrays. It will be sensitive to gravitational waves from phase transitions in the early universe, from cosmic strings if they exist, and potentially from other primordial processes. Like CMB B-modes, these would be direct signals of physical processes in the very early universe. In theoretical physics, the development of quantum gravity continues along multiple fronts. Loop quantum gravity and string theory are both active research programs. Holographic approaches to quantum gravity are producing rapid progress in understanding the connection between quantum information and spacetime geometry. The amplituhedron program, led by Nima Arkani-Hamed and collaborators, is reformulating particle physics scattering amplitudes in terms of geometric structures that do not obviously involve spacetime as a starting point, hinting at a description of physics that is more fundamental than the spacetime-based formulation. These developments do not yet constitute a complete theory of quantum gravity, but they are changing how physicists think about what a such theory would look like. The connection between quantum information theory and quantum gravity, exemplified by results showing that entanglement structure determines spatial geometry in holographic systems, is being developed rapidly. The emergence of spacetime from entanglement is being studied with specific models that allow controlled calculations. Understanding how this emergence works in more detail may provide clues about how time and causality emerge from a more fundamental description, which is central to the question of cosmic origins. Theoretical cosmology is also developing new frameworks for thinking about the multiverse and its observable implications. If different regions of the multiverse can collide, leaving observable imprints on the CMB, those signatures could in principle be detected or constrained. The search for such signatures, called bubble collisions, has been ongoing for several years with null results so far, which constrains some versions of the multiverse. More stringent constraints, or a potential detection, would significantly sharpen our understanding of whether eternal inflation and the multiverse are correct. The development of new mathematical tools for quantum cosmology, including approaches to defining the path integral over geometries more precisely and calculating the wave function of the universe more reliably, is an ongoing technical program. Progress on the mathematical foundations of quantum cosmology would help resolve the debates about the no-boundary proposal and related ideas, clarifying whether these proposals make definite predictions and whether those predictions are consistent with observation. Beyond the specific observational and theoretical advances, there is a broader intellectual frontier that is harder to map but perhaps more important. This is the frontier of conceptual innovation, the development of genuinely new ways of thinking about space, time, causality, existence, and explanation that may be needed to make real progress on the deepest questions. The history of science suggests that conceptual innovations are at least as important as observational discoveries and technical advances. The development of calculus by Newton and Leibniz was a conceptual innovation that made modern physics possible. The development of statistical mechanics by Boltzmann and Gibbs was a conceptual innovation that connected the microscopic and macroscopic descriptions of matter. The development of information theory by Shannon was a conceptual innovation that has transformed multiple fields including physics. The development of quantum mechanics itself was a conceptual innovation of the first order, requiring a fundamental revision of what we mean by state, measurement, and probability. Each of these conceptual innovations was not just a new technique for solving old problems. It was a new way of thinking that revealed old problems to have been poorly framed and opened up genuinely new questions that could not have been asked before. The innovation was not just incremental, but transformative. The deepest questions about cosmic origins almost certainly require this kind of conceptual innovation. The question of what time is in the regime where it is emergent rather than fundamental cannot be answered using our current concepts of time. The question of what spacetime is when it is not fundamental cannot be answered using our current concepts of space and time as basic ingredients. The question of what causality means when it is not built into the fundamental description cannot be answered using our current concepts of cause and effect. What conceptual innovations might make progress on these questions? This is genuinely hard to predict because innovations by definition are things we have not yet thought of, but there are hints. The development of quantum information theory has already produced new ways of thinking about the relationship between information, entropy, and physical processes that are proving valuable in quantum gravity. The categorical and algebraic approaches to mathematics that have been developed over the past century provide tools for describing structures without specifying their elements, which may be useful when the elements of the theory, the points of spacetime, are not fundamental. The philosophical analysis of what it means for something to be fundamental, what emergence means, and what the relationship is between different levels of description is providing conceptual tools that physics needs. The most important conceptual innovation may be one that we cannot currently specify, precisely because it requires thinking outside the frameworks we currently have. This is not mystical. It is the honest recognition that breakthrough understanding sometimes requires concepts that do not exist yet, and that will only be developed when someone has the right combination of technical knowledge, philosophical clarity, and creative insight to see past the current frameworks. What we can do in anticipation of such innovation is maintain intellectual openness. This means taking seriously proposals that challenge current frameworks even when they are speculative. It means being willing to question assumptions that are so deep we have forgotten they are assumptions. It means engaging seriously with the philosophical dimensions of the questions, not as a distraction from physics, but as an essential complement to it. And it means maintaining the discipline of evidence, always asking what observation could in principle confirm or refute any proposed innovation. Let us now think about what the investigation of cosmic origins means for how we understand ourselves and our place in the universe. This is not a tangent. It is the human dimension of the whole investigation, the reason why the question of why there is something rather than nothing is not merely an abstract puzzle, but a question that touches something deep in the human experience of existence. We are part of the universe asking about its own origins. Matter that constitutes our bodies was forged in stars that lived and died before our solar system formed. The atoms in our brains were synthesized in the nuclear furnaces of stellar interiors, or in the brief, intense nuclear reactions of the Big Bang nucleosynthesis era. The energy that powers our thoughts ultimately traces its origin to the nuclear reactions in our sun, which is itself a product of the gravity that assembled interstellar gas over billions of years of cosmic evolution. In a very real physical sense, we are a portion of the universe that has organized itself into a form capable of reflecting on its own existence. The universe has produced, through billions of years of expansion and cooling and gravitational collapse and stellar evolution and chemical complexity and biological evolution, structures that can wonder about the universe. We are those structures. This is not merely poetic. It is the actual physical situation, and it means that the question of why the universe exists is not separate from the question of why we exist. The two questions are connected through the physical processes that connect the very early universe to the present moment. The initial conditions of the universe determine the possibility of stars, which determine the possibility of heavy elements, which determine the possibility of planets, which determine the possibility of chemistry, which determine the possibility of life, which determine the possibility of consciousness, which determine the possibility of asking why the universe exists. This chain of connection does not resolve the question of why the universe exists, but it reveals something important about the relationship between the question and the questioner. The questioner is not separate from the questioned. We are not outside the universe asking about it from a neutral vantage point. We are inside it, made of it, products of its history, asking from within it about its origins. Our ability to ask the question is itself a consequence of the very processes we are asking about. This self-referential structure is genuinely strange and genuinely wonderful. The universe is a system that has produced within itself the capacity for self-reflection. It has generated minds that can model the universe and ask about its nature and origin. Whether this is a coincidence of cosmic history, a consequence of the specific constants and laws that allow complexity to develop, or something more significant, is itself part of the mystery of cosmic origins. The anthropic principle captures one aspect of this self-referential structure. We observe a universe compatible with our existence because we could not exist in an incompatible universe. This is a selection effect that explains why our observations are biased toward a universe that allows observers, but it does not explain why any universe allows observers, or whether observers are necessary for the universe to be fully real in some sense, or what the existence of self-reflective minds means for the universe's self-understanding. These are questions that physics alone cannot answer. They require the intersection of physics with consciousness studies, philosophy of mind, and perhaps new conceptual frameworks that do not yet exist. The origin of consciousness is itself one of the deepest unsolved problems in science, and it connects to the question of cosmic origins in ways that are currently only dimly visible. What we can say is that the existence of minds capable of asking about cosmic origins is one of the most remarkable facts about the universe. It is not a fact that any current theory predicts or explains. It is a brute observation that demands incorporation into our picture of what the universe is. A complete account of the universe would need to explain not only how it came to be, but how it came to produce beings capable of asking how it came to be. We have been on a long journey. We began with the everyday image of nothing, the dark room, the empty void, and showed how that image smuggles in assumptions that the physics does not support. We traced the expanding universe backward through billions of years of confirmed history. We examined the cosmic microwave background as the oldest light we can directly observe and the richest source of information about the young universe. We followed the theoretical trail past the observational horizon into the era of inflation, the quantum vacuum, and the Planck scale. We confronted the singularity as a breakdown of classical theory rather than a physical fact. We surveyed the candidate theories of quantum gravity and what they suggest about the earliest moments. We explored emergent time, holography, quantum information, and the possibility that spacetime itself is not fundamental. We asked what kind of explanation would genuinely resolve the question of why there is something rather than nothing, and we found that no current proposal reaches that level of resolution. Throughout, we maintained a discipline that is harder to maintain than it sounds, keeping track of what is observed, what is inferred, what is hypothesized, and what is speculated, and not conflating these categories even when the subject invites it. What have we learned? We have learned that the question of cosmic origins is genuine, specific, and technically demanding. It is not a vague mystery that dissolves on inspection. It sharpens on inspection. The closer you look, the more precisely located the genuine unknowns become. We have learned that the quantum vacuum is not nothing. Every serious proposal for the universe's origin starts from something, a quantum field, a mathematical structure, a quantum gravitational state, and derives the universe from it. None of them start from absolute nothing, and none of them could, because starting from nothing in the absolute philosophical sense is not a physical operation that physics can perform. We have learned that time may not be fundamental. May be emergent from a more primitive description, and the question of what came before the Big Bang may be malformed in the same way that asking what is north of the North Pole is malformed, not because it is trivial, but because it applies a concept outside its domain of validity. We have learned that the singularity is a warning, not a fact. It tells us that classical general relativity is being pushed past its limits, not that the universe literally began from a point of infinite density. What lies at and before the Planck scale is genuinely unknown, pending a complete theory of quantum gravity. We have learned that scientific explanation has structure and limits. It explains phenomena by deriving them from laws and initial conditions. It cannot explain its own foundations without circularity. The deepest questions about why those foundations are what they are currently sit beyond the reach of physical explanation, though they may not always do so. We have learned that the mystery at the beginning is real and precisely located. It is not ignorance masquerading as mystery. It is a genuine frontier where our best theories break down and our best concepts strain. It is the place where physics becomes most interesting, most honest, and most humble. The final thing to say is about the value of the question itself, independent of any answer it may or may not receive. Questions at the frontier of human understanding are valuable not only because they might be answered, but because of what the attempt to answer them produces. The attempt to understand cosmic origins has produced quantum field theory, general relativity, the standard cosmological model, inflationary theory, and the beginnings of quantum gravity. These are among the most significant intellectual achievements in human history. They were produced by the attempt to push understanding to its limits, to follow the evidence wherever it leads, and to be honest about where it stops. The attempt to understand the origin of the universe has also produced conceptual clarity about what time is, what space is, what causality is, what existence is, what explanation is. This conceptual clarity is not merely useful for cosmology. It is useful for all of human thought. Understanding what the concepts mean when they apply and when they do not, how they relate to other concepts and to evidence, is the kind of understanding that makes all rigorous thinking more powerful. The question of why there is something rather than nothing, pursued with honesty and discipline, is a machine for generating understanding of the deepest kind. Not understanding as the comfortable feeling that everything makes sense, but understanding as the precise knowledge of what we know, what we do not know, and what questions would need to be answered to know more. This kind of understanding is less comfortable than premature closure but far more valuable. It is also, ultimately, more honest to the actual situation. The universe is not simple. Its origins are not obvious. The questions it raises are genuinely hard. And anyone who tells you otherwise, who claims the mystery is solved or the question is settled, is either mistaken or not taking the question seriously enough. The universe has been expanding for nearly 14 billion years. It produced stars and galaxies and planets and chemistry and life and minds. Those minds can look back across all that history and ask where it all came from. The asking is remarkable. The question is genuine. The answer, or the understanding that comes from honestly confronting the absence of a complete answer, is among the most important things human minds have pursued. We do not know what came before the Big Bang. We do not know whether that question makes sense. We do not know what nothing really means at the level where the universe began. We do not know why there is something rather than nothing, but we know more than we did. We know what the question means with more precision than ever before. We know where the boundary of our knowledge is and what kind of physics would need to be developed to push it further. We know that the quantum vacuum is not nothing, that time may be emergent, that spacetime may not be fundamental, and that the singularity is a warning rather than a fact. We know that the universe, whatever its origin, produced us, that we are part of its history, that our wondering about it is one of the most extraordinary things in the observable cosmos, and that the wondering, disciplined by evidence and honest about its limits, is what being human at the frontier of knowledge looks like. The investigation continues, the frontier moves, the mystery deepens as it clarifies, and the question, precisely because it is so hard, remains the most important question we can ask. Why is there something rather than nothing? We do not know. But we know, with increasing precision, exactly what we would need to find out. And that, for now, is the most honest and the most valuable thing that can be said.